be here, should stand here, here, here and up to this much, right? Okay, 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 okay. Okay, good morning to everybody, and so okay, so yesterday we stopped here. So we are giving a concept that shielding, de-shielding effect. Now, if you have, let's say, if you have applied magnetic field, you know magnetic field induce electrical field, right? Okay, and electrical field induced magnetic field, and they follow the right hand rule direction, right? Now, if you have this applied magnetic field, now let's look at benzene ring. Okay, this is another example I'm giving. If you have benzene ring, benzene has how many sigma bonds? 6, right? And each carbon of benzene has sp2 hybridization, right? And then the pz electrons are perpendicular to that, right? And that is unhybridized, but they can undergo a side-on collision, right? And they can therefore, and that is delocalizable. So you have a pi electron cloud above the benzene ring, below the benzene ring, right? Now, if you have benzene ring, and then if you put a magnetic field, then what will happen? The pi electron cloud is there, so electron basically will move, right? So if applied field is there. So this is the direction of magnetic field. Induced electric field will be like this, right? So basically that will be going like this. It's clear. So electrons are moving, pi electrons are moving this way, based on the right hand rule. Then current will be opposite to the electron movement, right? So this is the current moving. Now that will induce magnetic field, right? So then this will be like this. So basically, because of pi electron cloud, you induce the magnetic field within the benzene ring, they will be opposing the applied magnetic field, right? And outside the benzene ring, they are basically adding to the applied magnetic field. Is clear to all of you? Now, if you take a molecule, this molecule, and this is a benzene ring at the center, and then let us say this is the molecule. Now, this molecule, which proton will be shielded? Which proton will be shielded? Because this is sitting just here actually, or any molecule sitting here or here will be shielded. Any molecule sitting here will be de-shielded. De-shielded means you need to regenerate, you need to give less field, because suppose it regenerates at say 10, at 10. Now you added already 1, so this will regenerate at 9. So that means de-shielding means it will be down field shift, because instead of 10 it is regenerating at 9. So de-shielding means it is down field shift. In this case actually you apply 10, now you are basically counteracting by say 1. That means you have to put extra 1 here, means you have to apply 11 to regenerate. That means to see the regeneration signal from here, you have to apply instead of 10, 11. So that means you have to increase the magnetic field. This is upfield shift. So shielding will lead to upfield shift, de-shielding will lead to downfield shift, and shielding will increase due to electronic environment. If you have more electronic environment around the nucleus, you have more shielding. If you have less electron around the nucleus, you have less shielding. Now if you have carbon and proton, and this carbon is connected to keto group or C double bond O, and then something else is there. Now this proton will be more de-shielded compared to compared to another one, we put CH3 group. Okay. Okay. So can I go to that side a little bit so that you can? I'm going to that thing. So let's say you have C say something R. Look at this and then you have so which proton is most shielded between these two? Okay, because you have plus I effect. In this case actually you have basically pulling out and therefore minus I effect, you have plus I effect. So this has more electron density around this proton. This has less electron density because of minus I effect from the keto group. So therefore electron density is less, therefore you will have, it will be more deschilded, it will be downfield shifted and it will be upfield shifted. Okay, it's clear to all of you?
Sir, in number 1, along with minus I, there is anisotropic effect also.
Anisotropy? No, this is, we are just simply focusing on the electron density. Okay. Now let's say if you take, say, let's focus on this. Focus on this and then okay. So you have 4 hydrogen, okay. So basically methane, monochloro, dichloro and trichloro, okay. Which hydrogen will be highly deschilded? Okay, because this has minus I effect, so basically you have triple pulling, right? In this case you have 2 of minus I effect, you have double pulling. So bond pair electron is moving towards the carbon, okay, because of, you all know what is plus I effect plus minus I effect, okay, because say this is a bond H, say X. Now if you have hydrogen, because your bond pair electron will be at the center because it is homo, okay, both are same. Now if you have this case one, they are different atom, this bond pair electron will go to the towards one side, the one which is more electronegativity, okay. Now so if his basically bond pair electron goes this way, then you say this is minus I effect, right? Okay, if bond pair electron goes this way, you say plus I effect. So when you have minus I effect, means you are basically removing bond pair electron towards this side, you are decreasing electronic environment around this proton, right? So that's why you are decreasing electronic environment here most, then this, then least. Is clear to all of you? So this will be very useful for analyzing in our signal. Okay. Okay. Let me just tell one more thing here. So now if you have a nucleus, right? And now if you have a lot of electron cloud around this nucleus, so this is the nucleus, and you have electron cloud. And you put this nucleus in the applied magnetic field. So applied magnetic field in this direction, okay, and therefore it will basically say exactly the same concept. It will basically allow the electrons will be spinning this direction, right? Right? They will spin this direction, and therefore current will be in this direction, and then you have the induced magnetic field will be in this direction. Because this is not a benzene ring, just atom. Okay, so therefore the center of the atom has nucleus, proton. Therefore proton will be shielded. This is a single, but that was a ring, benzene ring. Okay, is clear to all of you? So basically you have a nucleus at the center, and if you have more electron cloud, electronic environment, the electron will spin, that will generate the electrical current, and that current will induce the magnetic field, right, this way, and that induced magnetic field will oppose the applied magnetic field. Is clear? So suppose you need 10 and this induced magnetic field is 1. Okay, so net magnetic field actually when you apply this, net magnetic field is becoming 9. But this will resonate at 10. So that means you have to apply magnetic field little more to get this thing. That means that it will basically resonate at 11. So basically you have to shift the field towards high field. So upfield shift. Is clear to all of you? Now in this case actually, in this case you have, because of minus I effect, bond pair electron is moving towards carbon. So in this case you have proton and very little of electron. Okay. Therefore the electrical current is much less compared to this one. Therefore, okay, this is, okay, this will be kind of, what is it? This this is the way, right hand rule. Okay. So this will be 1 or less than 1. The induced magnetic field will be 1 or less than 1 or more than 1, less than 1, because you have less electronic density. Therefore you induced magnetic field will be less than this. So let's say 0.7. Okay. In this case you have to basically apply 10.7 to see the things, right? It's clear. Now if you have a benzene ring, so it's different, right? If you have benzene ring, and as I said that these are all sp carbon, 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 and then you have and they undergo side overlap, right? And at the same thing at bottom. So you will have benzene ring and pi electron cloud on top, because this, as you all know, these bonds are like highly delocalized, right? Because they can overlap either way. So in next moment you can write like this, they undergo resonance, right? So that's a pi electron cloud. And once you put in applied magnetic field, okay, then what will happen? So this is applied magnetic field, so electrons will move this direction, right? It's clear? And therefore induced current will be opposite direction. And therefore it will have induced magnetic field will be like this. So it's clear? Okay. So therefore in this, in case of benzene, anything, if you look tryptophan, okay, anything sitting above tryptophan in a protein, they will be, if you look at protein, in the protein folded in such a way that some proton is sitting or coming above tryptophan. So that proton which is coming above tryptophan, let me just clean it. Do you have the duster?
I don't know. Right. This is also understood.
This one?
Yeah.
Okay.
Yes.
I see. So this concept is clear, right? Because then we'll go back to the 1950 stories. Okay, thank you. Okay, so basically, so this will be electronic movement and current will be this way. Okay, and therefore your induced thing will be, induced magnetic field will be like this. Now anything is sitting, if your protein is folding, anything sitting above, just above the tryptophan, that protein will be upfield shifted or downfield shifted. Upfield shifted means shielding, upfield, because it is opposing, right? And anything, some amino acid came and sitting somewhere here, downfield shifted, right? Okay. So this concept is clear now, right? So now we'll go back to the alcohol story. So you have ethanol. In this, which proton is most deshielded? Okay, this is most deshielded. Okay, this will be basically, that means it will be most downfield shifted, right? Okay. Now when you record the spectrum, this side is upfield, this side, because when you shift, you scan it, this is upfield, this side. So that means this will be coming this side. Yes? And then next one, between these two, why CH? This one? Yeah, because that is close to oxygen, right? Okay. This is connected to oxygen. Immediately next one is oxygen, but for this next one is carbon. So, okay. It's better, right? Okay. Okay. Therefore, this will come here, and then next one. Okay. Now I will say that when it was recorded, they only saw 3 lines. Now you can see if we increase the magnetic field, you can see many more lines. Then I will discuss very soon that by increasing magnetic field, you can increase the resolution. We will discuss very soon. Okay. So when this experiment was done, it's a very low strength magnet. So, but at least you saw 3 lines. So that basically gave the concept of the chemical shift, because depending on the chemical environment, you see the protons are regenerating at different magnetic field strength. And this is, before the concept was there, all protons will regenerate at one particular frequency. But when you put non-water, you saw 3 lines. And then because then you collect, because they have different chemical environment. And once you know that thing, therefore, if you take different molecules, and in different molecules the environment of protons will be different, therefore, you can use NMR to characterize chemical compound. So that's the time in 50s people thought, okay, we can use NMR for characterizing chemical molecules. Forget the biology that time, there was chemical molecules that time, right? So, okay. Is clear to all of you? Okay. Then I will go next. Okay, so whatever I said, they are all written here, right? Okay, electronegative groups are deshielding and tend to move NMR signals from neighboring proton further downfield shift to higher ppm. I will talk about ppm very soon. And protons on oxygen and nitrogen have highly variable chemical shift, which are sensitive to concentration, solvent. This also I will talk. Temperature, solvent, they have huge impact. Okay. And also another thing, when you look at the NMR signals are very sharp. Okay. But if you look at the fluorescence signals, very broad. Okay. But signals NMR is very sharp. Also, I will be talking that. If you look at absorption spectrum, quite broad, right? Okay. But I will talk about those, because it does not, it follows different lines of Lorentzian things we will be talking. Okay. The pi system of alkenes, we talk about aromatic compounds. Alkenes also have, like if you talk about the alkenes, you also have this thing. Maybe I can go a little bit that side. Okay. So if you have alkenes, you have, say, so this is pi, right? You have pi, right? Again, in the same way, you basically deshield it, right? Because these protons are actually this side. So these protons will be deshielded, alkene protons, right? And if anything coming here, actually in the proton folding, something coming here, they will be more shielded. Okay. And the carbonyl also strongly, we discuss carbonyl, right? Keto groups. Okay. Now, the same thing has been shown. Now, in old days, there is no Fourier transform in NMR. What you do? We know that in a compound, that proton will not resonate at one frequency, because some will be uphill shifted, some will be downhill shifted. So, if you want to record a proton NMR of a compound, then you basically sweep the field, okay, within a range, because they won't come exactly at one position, right? So, how will you sweep? Basically, in one example here, you sweep the field from 2.3487 Tesla to 2.3488 Tesla. And what is the corresponding hertz? We have here corresponding hertz. Okay, so 100 megahertz. Okay, so if you do that thing, and basically moving from slightly from left to right, you are basically sweeping only small area, because this is the area proton resonate at this in this magnet, right? In this magnet, so therefore you are not using this one. Basically, if you do water, just you can use that thing, but you are basically looking at the different protons in the compound. Therefore, some will be uphill, some will be downhill shifted. So basically, choose the range, go from this range to this range, small range, right? And then sweep the magnetic field. Is clear to you? So, and then sweep it, and what will you see? Okay, that's the thing. See, water is here. Okay, and so now if you see this thing, this is a high magnetic field and low. And now by doing this thing, one second, by doing this thing, you get different things. All the things you get, right? Now, if you look at the whole thing, look at different compounds. Okay, if you look at different compounds, you can see that this we already discussed. This will be highly shielded, uphill shifted. Okay, coming right side, and if you look at the benzene, because they are outside the ring, they will be highly deshielded. They are downfill shifted. Now, if you look at alkene, although has 2 chlorine attached, but still it is not as much as downfill shifted is here. They are close actually. Now, if you between these two, compare between these two, these two are identical. Only it has extra thing is not exactly identical. Extra this pi bond is there. So there are two things working actually. Right? So minus I effect is here, plus pi electron cloud, because it's further shifted. But here actually slightly uphill. But if you look at, it's much more downfill shifted compared to this compound. Is clear? Now, if you look at these two, because keto is again more minus I, and also it has pi electron cloud, so it is further downfill shifted. Is clear to all of you? Now, if you look at this compound, both are ring structure, but this does not have pi electron cloud. Therefore, that kind of deshielding is not there. The deshielding you are getting because of this oxygen. So that's why it is definitely downfill shifted compared to this one. Now, if you compare this, again because of this SO is downfill shifted compared to this. Now, if you do this between these two, here actually proton is directly connected to keto group. Here it is connected to carbon, then keto. So it's 2 bonds there. So it is not as deshielded like this one. And then you have this compound. Between these two compounds, both are ring structure, but these hydrogens are connected to carbon, that is connected to oxygen. You have some deshielding, but here it is connected to carbon. So therefore, it is uphill shifted compared to this one. And then you have this. Now you go to this thing. This is further uphill shifted because of silane. Okay, is clear to all of you? So this is how you do it. Now after doing this thing, so you can see proton NMR resonance signals for some different compounds, and they are coming in different positions. Okay, so therefore you have to sweep the field. Okay, now you have to basically, once you do this thing, you got a compound. Now you need to report them. That okay, this comes this position. This compound comes at this position, this proton comes this position, this proton comes this position. You have to report that, right? If you put a compound in a NMR tube, record the spectrum, you get different proton peaks. Now you want to report this proton comes here, 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 but you have to give some number actually, right? Okay, so basically you have to use some reference and use basically trimethylsilane as a reference. So with respect to that, you tell where the things are coming. so which is shown in the next slide. You can use TMS, time oscillation as a reference signal, and with respect to that, this is coming, say, this is coming here, 215 megahertz up, and this is coming about 530. We are look at this one first, because we are sticking to 2.34 Tesla. Don't look at this, we will get back to that later. Just focus on this part. Next one is coming at 530 hertz. Next one is coming at 734 hertz. Okay? So basically, this is your reference. With respect to this reference, we just report that this is coming at this position, this is coming at this position. How to do that thing? So basically, and this difference is hertz, very small. And what is your magnetic resonance frequency? Let's say 100 megahertz. Because 2.34 Tesla, we discussed 100 megahertz, right? Okay? So resonance frequency is 100 megahertz. But these differences are very, very small, right? So which is basically 1 in million. Yes, okay? 1 in million, right? Is clear? Very small changes are you seeing. Shifting, upfield shifting, downfield shifting is very, very small. 1 megahertz, 100 megahertz means 100 million, right? Out of that, you see change is only hertz. So it's a parts per million, right? How will you get that? So basically, this you get the frequency of the sample. So sample is coming here, right? Minus frequency of the reference. So that difference you put it here. Okay? So that difference is basically say 215 hertz. Divided by the reference frequency is how much? Say 100 megahertz, right? That's reference, because that's the reference, 100 megahertz. So put that in 215 numerator divided by 500 megahertz, and then you multiply by 10 to the 16 parts per million. They get parts per million. So do the calculation, 215 by 100 megahertz multiplied by 10 to the 16. How much you are getting? Calculate how much you will get. Because if you go that way, they will understand. Okay? Yeah, it's very simple. Say sample minus reference, how much coming to be? This difference 215 hertz, right? And then this magnet is how much? 100 megahertz, right? So 215 by 100 megahertz means 100 multiplied by 10 to the 6. 10 to the 6, 10 to the 6 gets cancelled out. So what we are left with? 215 by 100, 2.15, and that should be parts per million, right? Right? So that is 2.15 parts per million. That's why you have to use the reference and give, okay, this proton is resonating at 2.15 ppm, parts per million. Is clear? Now anything is coming at 1 ppm, that corresponds to how much? So 215 megahertz corresponds to 2.15 parts per million. Now do proportional reached. So 1 million corresponds to how much hertz difference? 215 corresponds to 2.15. 215 hertz corresponds to 2.15 ppm. Okay? And how much hertz will correspond to 1 ppm? 100, right? 100 hertz. So this will be 100 hertz. So that means 100 hertz corresponds to 1 ppm. Now for proton, if you go to 10 ppm, for 100 megahertz NMR, how much will be this distance? 1 to 10 ppm? 1000 hertz. So window is 1000. So if you use 100 megahertz NMR, your 1 to 10 ppm window will be 1000 hertz, right? Okay. Now let's increase the magnetic field to 11.75 Tesla. And 11.75 Tesla corresponds to what? How many megahertz? Let's go back to the table. Okay, 500 megahertz. Now yes, so the point I am trying to show that by increasing field, you can increase the resolution. Yesterday we discussed the sensitivity. That's the point I am trying to show now. So now you go from 100 to 500. Let's see what is going on. Okay, now increase the field and look at, okay, now for this field, when you do the same experiment using this magnet, okay, now what is the difference coming? 1075 hertz. 1075 hertz. So your numerator becomes 1075. Denominator is 500 megahertz. And can you calculate 2.15 corresponds to how many megahertz? 1075 hertz. Okay, now calculate 1 ppm corresponds to how many hertz? Just 500, just 500, because if you have 500 megahertz NMR, it will be just 500 hertz. So 500 hertz corresponds to 1 ppm. So 10 ppm will corresponds to how many hertz? 5000. So when you use this one 100 megahertz NMR, this was like how much? 1000 megahertz. So all things are coming in 1000 megahertz. Now use magnetic strength to 500 megahertz. Now this window became 5000 megahertz. So you increase the resolution. How many times? Okay. Now you go to 900 megahertz. It will be kind of 9. Okay. How much is going to be? 9
times.
Yeah. Okay. So 9000. So it's much more resolution, right? So it's clear. That's how you can, by increasing magnetic field, you increase the resolution. And also we discussed yesterday, by increasing magnetic field, we increase sensitivity. Okay, it's clear to all of you. And so because just to recapitulate that thing quickly one more time. Okay, so basically we already discussed this thing. Now if you increase the magnetic field, you are increasing the denominator, therefore you increasing the ratio. So that means you will have, that means net ratio will be decreasing by increasing magnetic field. So that means you have more in the ground state, less in the upper state. So transition sensitivity will be more or less. Okay, if you have more transition, you have more signal coming out, right? Now if you have like 10 here, this level, and 9 here, so population difference is very small, 1. That means 1 transition happening. Now if you increase the gap, you have like 5 here and 5 there. Now how many transitions happening now? No, sorry, you have 10 here, you have 5 here. How many transitions happening? 5. So you have more signal coming, right? Now if you increase the state difference further, that means, right, by increasing the difference further, you are basically having 2 here and 8 here. Sorry, 10 here and 2 here. So that means 8 are going, so you are increasing intensity. So basically by increasing B0 magnetic field, okay, you are basically decreasing this ratio. That means less is in upper state, more in ground state. That way you have more signal intensity is coming. Is clear? So 2 things. That's why you have to. Now that's the time you have to decide what kind of band you make, so that you can go very high frequency. Okay, electromagnet. So that's why in early 60s electromagnets are coming actually. And how will you make electromagnet? How will you make electromagnet? Electromagnet. Okay. Now, basically, all earlier magnets are kind of a magnetic pole you are using. Okay. But by using that, you cannot go so high actually. But if you make some electromagnet, basically the concept basically you can use superconducting wire, which will not have any resistance. So start with some metal, and the some metals are superconducting at low temperature. Okay, so they will, once you start the current and make sure you have low temperature around that, and then it will continuously going on. It will not stop as long as you have maintained the temperature low. Okay, then you have your electrical current going. Okay, and then you induce the magnetic field. Okay, and induce magnetic fields up. So that's that way it has started in early 60s. Then they are developing further to get a better magnetic strength by using different alloys. Okay, so now we have 900 megahertz NMR. So how do they do? So basically, they put like a wire and put liquid helium below 6 Kelvin, and so it is superconducting, but that is very, very expensive. So you do not want the helium to basically evaporate. Around that you put liquid nitrogen, so that helium does not get evaporated, because helium is very expensive, liquid nitrogen is very cheap. So then you put after that liquid nitrogen, okay, and after whole thing is put in a flask. That means you put a air gap. So much protection giving. So that means there should not be any heat conduction going out. So you put air, and then after that your whole chamber is there. So if you look at a huge magnet, okay, so it's a this kind of thing, and that is put in a flask, and after that you have liquid nitrogen. After that you have helium, and then wire in that, and so as long as you are maintaining that temperature, there is no resistance, constantly current going. So the cost of the magnet is basically nothing, right, except liquid helium. Okay, that's the expensive part. Okay, and other hardware things, once you buy it, the maintenance actually is your liquid nitrogen. So that will maintain it, and then in the center actually it will be very cold, but you want to do experiment at your temperature. So then you put a tube and measure the temperature there actually. So inside actually, and then tube is there, and inside the magnet you have magnetic. You can see this. We just saw that thing, right? So magnetic lines are going like this. So it will be going all the fields, applied field this way. Okay. So that's the center. You put your NMR sample, and then you record the spectrum. We'll talk that. So that's how actually see, based on the need. Theoretically these are possible. Then experimentally these instruments are developed, and now we have 900 megahertz NMR. People go by ladder, go and put the sample. So big actually, right? Okay. If you look at the 500 small, 6 bigger, and 900 is quite big. Actually, they use the ladder and go up and put the sample, right?
For 500 you have to use a radar also.
No, 500.
There is one platform.
No, I think we used to put like this actually.
500 to 600.
Yeah, we have to have small stool and go. But if you go to look at the picture of a high field magnet, it's much bigger actually. Okay. Okay, so it's clear to all of you. So basically, there's a need for that to get better resolution and better sensitivity. And then after that, the cryo things came, because the RF coil, you can cool down, you can get better sensitivity and processing. So there's a cryo thing came much later actually. Okay, so how we can basically, the problem there in 90s, people got stuck, that you can, how much resolution you can go. Okay, so you got 900, and after that what? Then okay, can you basically use a radio frequency coil in cryo temperature? So cryo RF coil, so that can also increase the sensitivity. So you can still go slightly bigger actually. That, and then still you have problem. Now you go for 2 dimension to 3 dimension, okay, and then that you can get it. But still you have a limitation. You can go quite big molecular. You have a limitation. Okay, as you can go from 50 to 100 to 200, 250. After that, you will stop, right? Because you cannot go, because your photon NMR window is pretty small. It comes between 1 to 15 ppm. In that window, you cannot accommodate so many protons, right? So you have proton, then go 2 dimension, then go to 3 dimension, and then do triple resonance. So that's how you can get information. And then after that problem, resolution with the bigger molecule. So you have a limitation there. Is clear to all of you? Discuss. So the separation resonance signals in Hertz increases with increasing field strength, which I discussed already. Okay, if you look at the 300 megahertz NMR, this is basically 3000 window. If you take 10 ppm, if you start with 500, it is like 5000 hertz. If you do 900 megahertz, 9000 hertz, so much more resolution, right? Okay. Now the solvent. What solvent will you use? Initially, people use if you use organic compound, you can use organic solvent. Now, okay. Otherwise, you use the deuterated. Okay. Is why you want to use deuterated? That also is deuterium is NMR active. Yes, then that will interfere with signal. Okay, then why do you use that? Huh? Any answer? Deuterium also will interfere with the signal. That also regional, right? But why do you use deuterium? Okay. Okay, magnetic and then gyromagnetic ratios are different, and therefore precession is different. So they won't come in that window of proton, right?
Spin is also different. 2I plus 1 means.
Yes, one. So that's why you go back to the first slide. You can see that all different actually. In fact, it's pretty weak actually. Okay, look at the deuterium. NMR active, spin is 1, magnetic moment is also small, and gyromagnetic ratio is also very, very small compared to proton. Therefore, now if you do calculation, you take 100 megas NMR and do the calculation, how much, where it will come. So basically do the calculation here. Use this thing, okay? Okay, put this calculation. So nu equal to gamma B0 by 2 pi. How much it will be? You did calculation yesterday, right? So how much it will be? Let's say you have 2.34 Tesla. That you know this 0.86, and divided by 2 pi will be the frequency. So how much can it be? It will be, if you like 100 megahertz NMR, 100 megahertz NMR, definitely much less than 100, because if you see the major thing is here, so much down here, right? Magnetic moment and both. It will be very much different, right? So it will not come into that signal, because where you are basically doing. So basically, if you do deuterium NMR, it will not be 100, it may be 20, 30 megahertz, right? In terms of deuterium. Okay, is clear? Okay, so people use chloroform also depending on your sample, and D2O, and sometimes actually when you study, you don't use 100% D2O. When you do DNA structure or protein structure, you don't use 100% D2O. Why? Okay. Yeah, proton, and also I'll show you. You have to have, if you want to look at the hydrogen bonding, that means you have to have good hydrogen acceptor. Okay, so for that you don't do 100%. It keeps some water, but that water can give huge peak, which can suppress your signal. So therefore, you have a program, by using program you can suppress the water, and then you can look at other things. Okay. So these are the various solvent people use. Okay. Now this is another one example how things are coming. We didn't talk about acid. Acidic H will come further downstream. Okay, and this is this one we talk actually. This also we talk. So you can look at if you look at the spectrum, how protons are coming at different position based on the discussion we had. You can make out. I think most of the things we discussed actually. Right? Now, why I want to discuss this one here, because we will be talking about DNA NMR. So DNA NMR, when you do that, you have two things you look at. First, immunoproton is there, and aminoprotons are there. Immunoprotons, if they are hydrogen bonded, they will be very much downfield shifted, right? So because you will see most of the immunoprotons coming this side. When they are not hydrogen bonded, they will be not be so much downfield shifted. And second thing, if you have exchangeable protons are exchangeable very fast, lines will be very broad, sometimes you may not see the signal also. By decreasing temperature, you can make the line sharp. We will be talking that, how you do that thing, okay? So just to have some idea, again we will be talking those things when we talk about the structural study, like DNA NMR, we will be getting this thing. So this is alcoholic OH, these are kind of like simple molecules, and you can see they are coming in different positions, okay?
In case of alkyne, there is a shielding due to orientation. Alkynes.
Alkynes?
Triple bond.
Which one?
Triple bond is
here.
shielding region.
No, this is actually, this one, anything here, this is not shielded actually. This is not shielded.
Okay.
This is not shielded because we discussed there actually. Just now we discussed that. Okay. Yeah. Okay. Let me just one more time. Just See, you have okay. Now you have one sigma bond and 2 pi bond, right? Okay, so basically you have one and you apply applied magnetic field, right? Okay, and then your current will be in this direction, right? So basically you are de-shielding actually, right? This proton, right? Even if now protein is getting folded, something getting folded, something is a big molecule, something got folded and came here, some proton. That will be shielded, but this will be de-shielded.
Parallel to the plane of the applied magnetic field, sir.
No, this is
Applied magnetic. No, the orientation of the molecule.
Orientation of molecule is at, you can rotate it by
In a vertical position, not in a horizontal. Sir, alkene orient itself perpendicular to the direction of the applied magnetic field, but alkyne orient itself parallel to the direction of the applied magnetic field. That is the main reason for it.
just rotate the molecule like this.
why?
Orientation remain is
Why this will be in that direction?
planar.
No, because you can make plane this way also, right? Why it has to be this way actually? This molecule is tumbling. At some moment, at this moment is like this. Next moment this thing, but it is a planar molecule. This is planar. This is 180. 180 is planar, right? And then in this orientation actually, you have, because you have sp hybridization, right? That means it is sigma bond, sp sigma bond, sp. Then you have a py and py and pj, right? Let's say, okay. So you have a pi electron cloud lot, right? And then now when you apply magnetic field, the electrons will be basically moving this way, right? Because moving like this electron. So electrons are basically moving this way, and the current, electrical current will be opposite direction, right? So that means right hand rule. That means this will be like this. This is the direction, right? So that means this hydrogen will be de-shielded.
There are two double bonds, two pi bonds in the inside.
Mm-hmm.
And over
I want the 90 degree angle, no?
Okay. So you are talking about this one actually.
Yes.
Okay.
One is X,
Mhm.
one is Z.
Okay. Yeah.
This is the
Oh yeah. Oh, you are talking other one. Okay.
So then
Okay.
actually,
So we are talking about the PG things.
PZ.
Okay.
No, actually it is something like this.
Yeah.
Pi cloud.
Yeah.
So one is on this and
This way, other one will be
secondary magnetic field.
Yeah. Other one will be in XY plane.
Yes.
In XY plane.
So
Yeah.
it will definitely going to shield it.
Now the one one in this direction, but I'm talking about PG actually. Yeah.
So actually because the huge secondary magnetic field would be generated out of the orientation of this cloud.
Yeah.
Because you have a two cloud,
Yeah.
one is a PZ orbital, the other one is a PY orbital.
Yeah. That's the one.
So one is in this way,
Yeah.
another one is in
Yeah,
this way.
in this
Then
plane.
you have a 90 or 90 degree
Yeah.
secondary
Yeah,
magnetic field
yeah.
would be generated. So whole of this area
Mhm.
that would be covered, means protected.
Mhm.
Protected in the sense the V0 minus V1.
Yeah. So that is basically this one. You are talking POI will be this one.
Yes.
This one.
This one and
Yeah, because they are in same direction.
yes,
Okay.
and this side. So this is going to protect, will shield the electrons of the hydrogen.
Yeah.
That is why it is having a upfield.
Now uphill, but if you compare with the methyl, if you look at this, it's definitely downfield shifted.
Down.
Because if you are comparing these, we are comparing these three things. So if you look at this, okay, and then second one is this.
due to hybridization, basically sp hybrid.
Yeah, and then third one is basically you are doing this. So you are comparing. So this is the most uphill shifted, okay, and then this will be this and then this. That's the comparison actually. Okay.
So one is the hybridization. The second explanation if you give in terms of this is what I say in terms of magnetic field. Secondary magnetic field generated by the acetylene would be more stronger than the ethene.
because you have only this one I'm talking, this is more downfield shifted.
This is more down.
Yeah, because in this case you have the PY is there actually, that's here actually, this is here, okay, that will have some shielding, but definitely it will be deshielded compared to this one. So that's the yeah, yeah, that's why it is coming not exactly here, it is coming where is that? Yeah, it is coming here actually. That's the point I'm making actually. Now if you go this one further down, have you seen this thing? So that's the thing I'm giving actually. Okay. So it's clear? Any other question? And same thing as S stars, all the things you can work on that, right? So all these things are possible based on accidental, okay, experiment, right? Okay. Now go back to this compound. So in this compound, what do you see here? This is a benzene ring, and this will be basically all, because these are PZ, that means again same concept is talk, and this will be all deshielded. This will be all deshielded, and this will be further deshielded. Because deshielding is the, on top of that you have minus I effect. Okay. So if you look at the spectrum, so this is the one here, and then you have, okay, so this is like this is area under the peak. This is a ppm. So you get one here, 12.6 ppm, and these two deshielded also close to OH, so they will be here about 7.73, and this one actually is here. Again, it is definitely less deshielded compared to this, but it is here. But these two are methyl, carbon. Next to after the carbon, then methyl. That's why it is further upfield. Is clear to all of you? Now, if you look at the intensity, this is very high intensity because 6 protons, and here you have 1 protons, and here you have 2 protons, and here you have 1 proton, right? Now, this line is bit broad. Okay, why line is broad? Okay, broad. Okay.
Inter or intramolecular hydrogen bonding and then no, acidic.
Okay. Okay. Yeah. So exchanging.
Acidic.
Okay. So basically, this OH does not always stay there. Sometimes it exchanges the water, right? At this moment here, next moment here. If you have fast exchange, okay. Let me just write this here. So basically, when it is with completely bound, you have signal here. Okay. Oh, T has come. Oh, so quickly. Okay. 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 So yeah, we have T and then continue. Yeah. Okay. 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 Now I have to get your feedback. Based on that, I have to plan. Okay. Okay. Yeah. So. Okay. So this actually line is broad because of exchange, and if you have fast exchange, it will be much more broad. You won't see it also. Okay. Now by increasing temperature, you have fast exchange, line become broad. While we are talking that broadening signal, things I can get back. Now if you decrease the temperature, you decrease the exchange, line become more and more sharp, and the position will be further moving left side. Okay. Why? It will be clear here. Say this is the proton, say this proton, say is exchanging with the water. This proton is basically exchanging with the solvent. Okay. at time t equal to 0, this proton is here. Okay? Time t equal to 1, this proton is here. So when proton is here, that is different microenvironment, right? So now if you look at the, you should have two bands, right? Two peak, same proton, because that is getting exchanged. Okay? Now, because it is not like a staying in this form, right? So you get basically get a peak. This will get, because of exchange, this is getting broad end, this is getting broad end, right? Both. And then finally you get a like broad peak here, right? This is clear. This is the exchange thing, means you broad. Now, if you increase temperature, it will be much faster exchange. That's why it will be somewhere here in the middle actually, right? It's clear. Now, if you basically decrease temperature, by decreasing temperature, you are basically decreasing exchange. Therefore, you are populating this form, right? That means you are basically getting this signal. It's clear.
Yes, sir.
So by decreasing this temperature, you can basically get a peak. So that peak is basically left side of this peak. This is the peak you are seeing there. So actually, if you decrease temperature, peak will be shifted to the left side, because this peak came from these two different things, right? And if you further increase, temperature, this will be further broad, right? So therefore, depending on the temperature, you can see that signals are getting broad. And if it is exchangeable proton, you should do the experiment at low temperature. Okay, then you can at least see the signal. Okay, if you further decrease temperature, you can get distinct peak here. Okay, so we'll be showing some of the example there. So okay, this one we will talk. Now let's talk about this molecule. So if you look at this molecule, again we said that carboxylic OH, which is exchangeable, which can exchange. Okay, this is this phenolic. This will be more acidic, right, compared to this one, right? Because the corresponding anion will be resonating corresponding anion. Is it? No, because it will come here and then stop. Because this is on there, right? It's not like phenolic OH, phenol. That will be more resonating, right? Okay, and okay. Now look at this one. If you look at, there's a chloro group is there, there's a minus I, and also keto group is there, so it's acidic. So this is basically coming at 11.4, like 11.4, and these are basically again much distillate compared to methane, right? Which is basically here 4 point something. Again, this line is a bit broad also, right? Okay. Now you can look at the tautomerism. Okay, same way, because if there is tautomerism, you can see all the signals. So let's look at this thing. Actually, you can have very fast here. So you can see this signal, because this signal is 14.5 and is again forming the hydrogen bond. If a proton which is forming hydrogen bond gets further deshielded, and you can see very high here actually 14.5 you can see here. Now you can look at these things actually same way. You can look at these things 2.05 this methyl, which is here, and then you have 5.50 which is this one, 5.50 this one, and then this is here actually. Okay, and this one actually is most one, right? 2.24. Okay, this is 2.24 here, and then you have the 3.60 this one. Okay, so it's exactly the same concept whatever we discussed, right? I think I forgot. I think I put one thing at low temperature for this one. I'm just thinking. I think I put one low temperature. Let me see whether it's there or not. Yeah, it's here actually. Yeah, it's coming here. So if you, as I said that, if you have hydrogen bond, you can have much down precipitate, right? OH is low already down precipitate. You would hydrogen bond further down precipitate. Now if you have a compound put in a solvent, that solvent should be more favorable for hydrogen bond, should be hydrogen bond acceptor. Then you can see more downfield shifted. Okay. Okay. So one example is shown here, like methanol. If you put methanol in CdCl3, that this will be basically 3.40, you all know. This OH will be 1.10. This is a chemical shift. Okay, this is in this middle. Now once you put in DMSO, it will form. It's a strong hydrogen bond acceptor. So you can see very much downfield shifted, and then this and then this. Okay, so basically depending on the if you have hydrogen bond acceptor, it will further downfield shifted. When you do DNA structure, all the hydrogen bonded immunoprotons are very much downfield shifted. Okay. Okay. Now same methanol. If you look at the methanol, same one. Same one. If you look at this thing, you have 3.35 and 4.80. This is 4.80 at 30 degrees centigrade at 6 megahertz. Now at 30 degrees centigrade, the line is coming where 4.9 or so. 4.9. Okay, yeah, 4.8 and 3.5. Now exactly same NMR, decrease temperature to -45. You see that line basically exchange is going down because this can exchange with solvent. See? Okay, line is exchange is going, the line is moving to left side. Okay, 5.5, exactly same thing, and this line remains same because this is not exchanging border. So okay, it's clear, and lines are becoming more sharp. And also we will talk to you very soon why you are getting also multiple lines. We will be talking soon. Okay? Because there is a spin-spin coupling through bond. We will be talking that now. Maybe very, very soon. I think maybe next slide we will talk. Okay. Any question you have? Lines become sharp by decreasing temperature, and you have basically decreasing the exchange, so you get the other one. Okay. Which is left side shifted. Okay.
So that is why cyclohexene is taken at low temperature to differentiate axial and equatorial protons. Cyclohexanes. The signal are taken at low temperature so that equatorial and axial protons are differentiated.
No, because this is exchangeable border. We are talking exchangeable border. Hexane has exchangeable proton?
Cyclohexanes.
No, they don't have. This is actually proton which can exchange with solvent. Okay. Like OH can exchange, carboxylic OH can, carboxylic OH their proton can exchange, NH proton can exchange, right? NH2 proton can exchange, right? So we are talking about exchanges proton. When you do room temperature, if they exchange, line will be broad. If those NH or NH2 are forming hydrogen bond with another bases, then they won't be able to exchange because they are only hydrogen bonded. Those bands will be, lines will be sharp and will be downfield shifted. Is clear? Okay, now if you take this molecule, in this molecule, which proton is more downfield shifted? This one, right? Because they have 2 chloride, and that's downfield shifted. And if you record the spectrum, for this one you are seeing multiple lines. It's a fine structure, multiple lines. Instead of one signal, you are getting multiple signals. But you didn't see this thing in 1950, okay? Because the resolution is very poor of the magnet. Now if you increase the resolution, you can see the fine structure of that signal, and that center is the 5.8, this center. If you use a low field magnet, you will see only one line which will center at 5.89. Now same thing in low magnetic field, you see one line at 2.1 OCs, but you are seeing 2 lines, and those lines basically are 2 sides of this splitted. This center of those 2 lines. Clear? So why is that happening?
Spin-spin coupling or spin-spin.
Okay, and what is spin-spin coupling?
The splitting of a signal by neighboring protons due to the combinations.
How? Because neighboring protons can be, say these 2 protons can be interacting through space. Okay, and this one is basically through space or through the 2 things. These 2 spin can interact through dipole-dipole coupling through space if they are close, less than 5 angstrom. Okay, around 5, and if you go beyond, it's almost negligible. We will talk soon. Or these two spin can also interact with each other through bond. Okay. Now tell, we are talking the spin-spin coupling through bond. How two spins are coupled to each other through bonds. This is also known as J coupling or scalar coupling. Okay, how it is happening? But why you need the bond? Because you just can just do dipole-dipole interaction. Okay. Because if you have, suppose you have a geminal, there are two things can happen, geminal and vicinal. Okay, let's look at this one. So this is geminal, right? I'm not putting other things. Let's say other things are there. So vicinal, right? So this proton can undergo spin-spin coupling with this and so also. But why this spin-spin coupling requires the bond? They can do through space also, right? So the one we are talking, that is J coupling or spin-spin coupling, which splits the line. Okay, but dipole-dipole interaction does not split the line, right? So this J coupling is scalar coupling. So why you need the bond to have this coupling? What is the role of this bond here? Yeah. Okay, in this case there is no dihedral angle, right? Okay, let's focus on this. Why we need the bond for spin-spin coupling? Okay, in the beginning I talked about the nuclear spin and electron spin go in that direction. Okay, so you have how many electrons are there? You have 2 electrons, right? Here to form the bond. So this nuclear spin will polarize the electronic spin here in this bond, and there is again that polarization of this bond will polarize the electron in this bond. So basically you are polarizing the electron in the adjacent bond, and that will polarize the electron in the neighboring interesting bond, and that will basically, that polarization will be transferred to this spin, nuclear spin. That's why through nuclear spin to electron spin to next electron and nuclear spin. That's a spin coupling. And this kind of thing cannot go for long. You can go to geminal, which is more, because you have 2 bonds, and here is vicinal. You have 3 bonds, right? Okay, you cannot go for like 10, just vicinal, geminal, right? So this is very close, therefore maximum spin-spin interaction, and here is a less compared to this one. Now again it depends on the orientation things. So basically this is called dihedral angle, right? Or phi, right? What is dihedral angle? Say this is one plane, this is one plane, this is another plane, right? So this carbon proton can be part of one plane, and this carbon proton another plane. So the angle between those 2 planes is known as dihedral angle. So if they are facing, both are same plane coming, so and then opposite plane, this plane, so therefore the spin-spin coupling also will be affected based on the orientation. Is clear? Therefore, if you find the spin-spin coupling constant, you can calculate how much is the dihedral angle. Therefore, you can get the conformation of the molecule, right? Is clear to all of you? The vicinal coupling is very important to give information about the conformation of the molecule. Okay, you understand my point actually? So not whole molecule, you can get the conformation of this bond. Similarly, you can have another one. You can do same thing for this and this. You can get this dihedral angle, right? Similarly, you can do the next one. You can get the dihedral angle for this one. That's why you can get the conformation of a molecule, right? Is clear to all of you? Because because the spin spin coupling is a function of dihedral angle for vicinal coupling or scalar coupling or JJ coupling. This is geminal. Is clear to all of you? So therefore spin spin coupling or J coupling, scalar coupling is occurring through bond, and you get the splitting. But in nuclear Hausser effect, or let's put it this way, also this spin can also interact with this spin through space without going, and that is called dipole-dipole coupling. One dipole, this is a magnetic dipole, right? As we discussed in the beginning, that you have a nucleus, this is spinning, and then that joins the magnetic field. So it's a magnetic dipole, right? And you have, this is a proton, you have another magnetic dipole very close. You have another magnetic dipole in the same molecule. If it's a different molecule, and in solution they are undergoing Brownian motion. So at this moment is here, next moment somewhere else. So that will develop the fluctuating current, right? Because this moment this dipole will be here, next moment it goes here, 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 here. So that will develop the fluctuating current, fluctuating field. But and that kind of dipole orientation you may not be able to pick up in your experiment, right? So if these two protons are in same molecule and molecule folded in such a way, then these two protons came very close within 5 angstrom, then they will show dipolar interaction, which you can detect by NMR. But we will be talking that after I talk about the J coupling or scalar coupling. Is clear? Any question on this? Okay. So we will be now talking about the J coupling, how it occurs, and how many lines will get it, and what should the intensity of those lines. We will be talking those. Okay. So in this case, this proton will basically have JJ coupling, because through this to this bond there is a 3 bond coupling, right? Okay, and these 3 protons are kind of identical protons. Okay, so they can be considered as one. So basically it's a 2 spin coupling. So this is one spin A, and these 3 protons are same as spin B. So the 2 spins are interacting, and for this actually how many lines will get, and for this how many lines will get. Let's discuss that. Okay, so instead of going this way, I'll just go one slide, 2 slides forward, and again I'll come back. Okay. Okay, let's talk about this thing, 2 spin state. Remember yesterday I talked this thing that okay, maybe okay, let's start from here actually. So if you have 2 spins and they are basically coupled through bond. So there are 2 spins. So spin 1, let me just write here, it will be much clear here, then we will go back there. So this spin A, say AX system, 2 spin. Okay, this is proton A and proton B, right? Okay, focusing. Okay. So basically you have 2 spin alpha, beta for A, and also you have same alpha, beta for this. So this can happen with this and this. So what do you get? You get alpha, alpha, and alpha, beta, and then this and this, then beta, alpha, and beta, beta. You get 4 different combinations in this couple. Now let us look at the energy. How will be their energy? Okay. So, as I said yesterday, energy basically E, so this is M I, right, alpha and beta. So, E M I M j equal to M I nu 0 I, because this is the Lamar frequency, right, we discussed yesterday, because we discussed yesterday W0 equal to gamma B0, okay, and then it is equal to 2 pi nu equal to gamma B0 nu equal to gamma B0 2 pi, right, is clear. And then you do same thing for j gamma 0 j, then plus I think j I j, I think half or 1/3 is there, or 1/3 half is there, I think. Yeah. So j and then so same equation m I m j m I v Lamar frequency into 1 plus 2 and j 1 I j, you to j I j and m I and m j. Okay, just 1 second. I want to look at the first slide. Okay, m I m j j 1 2. Okay, if you do alpha, E of alpha alpha, you tell me how much is going to be E alpha alpha? Alpha alpha. So basically alpha means is a half and half. So this is say I, this is j. E I first one alpha, half and then this will be alpha will be again half nu j plus this will be, and then plus half minus half, right. So plus half minus half should be minus, okay, 1/4, right, right. So that way you can calculate all of them. Okay, it's clear. So half mi of this half, the first second one is half plus plus, right, and then first spin frequency of first spin 0 is basically Lamar, the frequency 1, frequency second spin 2, and then half of this first one half, so 1/4 and 2 spin coupling constant J1, this is splitting. Is clear to all of you? Okay, and you do same thing for second one, alpha half nu 0 1, then second one mi is minus half nu 0 2, and then m plus half minus 1/4 j1 2. Same thing you do for beta alpha, all the 4 states I wrote there, for all the states you are doing. Then you do exactly same thing. Okay, so beta is minus half first spin, second spin is plus half second spin, and then plus m1 m2, which is plus half minus half, so minus 1/4 j1 2, and do the last one. So you have half minus half and then again minus half for second one, and then for this m1 m2 minus half 1/4, and then this. Is clear to all of you? That's how you get the energy after coupling. What is the energy? What are the energies of those 4 states? Okay, so you got the energy of 4 states. Now if you go back, okay, okay, now you got 4 states. Now if you look at the 1 and 4, they are different, very clear, but between these two states, so between alpha beta beta alpha, do you see much difference? Okay. Okay. So basically, for homonuclear system, these two are very close for homonuclear because they are protons. They will be very close, right? So if they are very close, these two will be almost same. This and this almost same, right? Clear? Because the moment you put exactly same, these two, so basically alpha beta beta alpha will be same. Now if you go to heteronuclear system like carbon proton coupling, will they be same? Because these numbers are different, therefore it will be different. So I think for a heteronuclear system in which the Lamarck frequencies differ significantly, the 4 levels are all at markedly different energies. Okay, it's clear to all of you? Okay. Okay. Yeah, this is the for carbon proton. I say that this is the thing. For proton, when one proton is coupled to another proton, alpha beta beta alpha have same energy just because their Lamarck frequencies are very close. So they will be pretty close, actually, almost close, right? Now when you have carbon proton, the alpha beta beta alpha will be much different because their Lamarck frequency will be different, right? Because we discussed why they are different, because we already discussed multiple times, right? So therefore we have 4 different states. Okay. Now let's talk about the proton, these 4 states. Okay. Now there is a selection. Do you think we can have all transition? You get 4 states. These are the 4 energy states you plotted. So this is the energy axis. Okay. So how many transitions you can have? So basically now this you can go this way, or this way. This can go this way. So how many possibilities will be there? Which is allowed transition? So for allowed transition, net change in M should be 1. Okay. So it is written here. So net change. So net M is M1 plus M2 is a net M. The net change should be 1 plus minus 1 for this is selection rule. Okay. Now if you look at this, we have 4 states. When a couple, so scalar couple, we have 4 states alpha alpha. Now for this, what is the M? M1 is plus half, M2 is plus half, right? So half plus half 1. For this one, plus half and minus half 0. For third one, minus half plus half 0. For last one, minus half minus 1. So how many possible ways you can have transition? So definitely you cannot have 1 to 4 transition. Why? Because the difference is going to become more than 1, right? 2. How about this to this? 1. This to this, and this to this, no, this to this, second to third, 0. Okay. So only delta equal to plus minus 1 is allowed. So that means you can have 1 transition, 1 to 2, 1 to 3, and 2 to 4, and 3 to 4. These are single quantum transfer, right? Because single delta M is 1, single quantum. Okay. Is clear? So therefore you can have this transition allowed, compression 1 to 2, 3 to 4. Okay, and these are things. Now let's see how much energy is needed. So that's the thing is shown here. 1 to 2 allowed, this to this allowed, this to this allowed, this to this. So this to this is not allowed, right? That's because delta M is basically 2, which is called double quantum coherence, double quantum transfer, and this to this actually difference is 0. So it's 0 quantum transfer, right? Transition. So these are not allowed. So only these are allowed, which is discussed. Now we want to see how much energy, if they transition, how much energy is needed to resonate. Okay, and that will tell that's the resonance frequency. That's the place where a signal will get, right? Now if you look at this thing, in this case, what is happening? Alpha for spin 1, alpha is fixed. Only spin for second spin, alpha is getting converted to beta. So in this case, first spin is passive, second spin is flipped. So second spin is active. Therefore, this line it corresponds to which spin? because you have two spin, they are coupled, right? Okay. So the first spin remains alpha, no, not flipping. Second one is second spin. Second alpha, this is first spin, second spin. So second one, this is good actually. Okay, I'm going to touch actually. Okay. So this is first spin. So first spin stays alpha to alpha. Second spin goes from alpha to beta. So which one is basically transitioning in this case? Because alpha goes to beta is just transition. So which spin is getting alpha to beta, first or second spin? So therefore this line corresponds to the peak for the second spin. So this line will come at the second spin, nu 2, okay? It won't come exactly nu 2, it will come right or left, we will discuss that. So this transition corresponds to the second spin, and therefore second spin is active in this transition, first spin is passive, okay? Now again this also same thing here, beta to beta, so first spin is remaining same, not flipping, same state. Second spin is going from alpha to beta, okay? So this is again corresponds to which transition, first or second? Second spin, right? So these two lines belongs to second spin, and now if they have identical energy, then they will come at one position, okay? If they have different energy, they will come at two different positions, okay? So therefore we will see what is the energy gap this to this and this to this that will calculate. Now let us look at this one. Here actually first spin is changing from alpha to beta, second spin is doing same. So that means which spin is getting transferred here? First spin is active, second spin is passive. So this line corresponds to the first spin. And this similarly here alpha to beta, first spin is changing, flipping, second spin is not flipping, same. So again this is a transition of which spin? First spin, right? So therefore you have two spins and you are supposed to get two signal at for the first spin one signal and second one signal. But after coupling you see that there are two transitions for the first spin, that means, and two transitions for second spin after coupling. Before coupling you have one transition for one spin. If you look at this thing, before transition you had, if you have before spin coupling you had alpha to beta one transition, and if they, and here also one transition alpha to beta for second spin. If these two spins are not coupled, you will have one transition for alpha spin 1, you will have only one transition for spin 2 if they are not coupled, okay? Now if they are coupled you got 4 different states, and also for each spin you got 2 transitions, right? If those 2 transitions are identical, the energy gaps for those 2 transitions are identical, then there will be those 2 transitions signal will come at one position. If they are not identical, they will come at 2 different positions. If they are coming at 2 different positions, that means that spin signal from spin 1 got split into 2, okay? So that we can tell only looking at the energy gap. If they have identical energy gap, those 2 lines will come at same position. They have different energy gap, they will come at 2 different positions. Is clear to all of you? So let us, with that view, we will now calculate the energy gap of those states, okay? So we got this thing. Now let us look at the energy gap from 2 to 1. We will do first 2 to 1 and 4 to 3. So that will tell whether this line second transitions are coming from one position or 2 positions, right? So 2 to 1 and 4 to 3. Okay, 2 to 1 transition. This is the new 1 to 2 to 1 transition. That means there is transition for second spin. So E2 minus E1. So we are doing, what is E2? E2 is basically for this, E2 minus this, okay? So E2 will be basically, E2 is basically half nu 1 minus half this and minus this is for E2. We have done this all the calculation in this previous slide here. This one exactly put the same thing here, right? Okay, it's clear. And then E1 is this, you put exactly same thing there. Okay. After that, what you got? You got this. So first transition, that this transition is coming, see, coming for second spin. The signal will appear at the second spin, but not exactly at this frequency, that frequency minus half of J1 by 2. Is clear? So that one. So this signal is coming at, this is for spin 2, it's coming at frequency of spin 2, but not exactly at that, minus 1/4 of J1 by 2. So they're not, it's shifted. Now let us look at this one. Okay, so whether that is also shifting or not, and if it shifts, which direction? Okay, so basically do 3 to 4. See, it was exactly same thing. So you have 3 in the previous slide, 4, you subtract and you get this number, right? So now again, this time is again centering here, but this is basically moving to plus something. This is minus and this is plus something. So you have center. Initially the signal was coming before splitting at nu2. Now when they are spin coupled, you are seeing two transition. One line is moving to this side, other line is moving to that side. Those two lines centering at nu2. So which is basically shown here. Okay. So 1, 2 and 3, 4 for spin 2. Center is this. And 1, 2 basically moving to left side, minus, other is just adding plus. Because when adding plus means you have to go right side, right? Minus means left side. Is clear? So this is basically center. From here to here basically 1/4 J12, and this is 1/4. So therefore this is basically half of 1/4 this side, and this is 1/4. That basically becomes half of J12. So that's how you get this coupling constant. Is clear? So any question on this part? Now you do exactly same thing for this, you will get exactly same thing. So you do again 1, 2, 3. This is for spin 1. You get this one, exactly same thing. Put this energy which you have done in the previous slide, and put the energy this, and then you get this number. And 2 to 4, this one. So you are doing other two. You are doing this and this. Okay. So what you get? Those that are in two lines, but they are centering here, and one is going to left side, one is going to right side, minus and plus, half and half. Is clear to all of you? So basically, you get here. So this is center, and then this becomes minus half J2, and this plus half J2. So what is the difference? Basically, half J2 left side, half J2 left side, half plus half 1. So this is basically coupling constant. J is total. This difference between this peak is basically J12 coupling constant. Here also half. So 1. So looking at that, you can, and that is center here at this position. If you don't have, if you have low field magnet, you will see the peak is coming here. Okay. Okay. Now the one point you should remember: by increasing magnetic field, you do not change the coupling constant. Remember that thing. You saw this signal because you increase the resolution, as we discussed, right? Because it was compressed. The moment you increase the magnetic field, you could basically see this difference. But remember, increasing magnetic field, you do not increase the coupling constant. That is already there, but you could not detect because of poor resolution at low magnetic field. Is clear to all of you? So if you use low magnetic field, you see the signal here. Once you increase magnetic field, you can see the difference. Okay? Any question on this? So basically, when two spins are coupled, you can see two signal. Okay, so that's why in this case, if you go back to that slide, if you go to this slide, this one, this is basically having two spin coupling, right? Right? This one. Okay, that's why you got two line. Okay, and this is basically J2. This to this. Okay, now we'll see what is happening for this side, this one. That means we have to go for 3-spin system. So all the things. See, this is how we got J12, J12. Now we'll go to 3-spin system. When you have 3 spins, because then what will happen? So that is basically coupled to that and another one. Then how the numbers will be. Okay. So it will be exactly same. We'll just quickly go over it. So this 2-spin system. Okay. And we also talk this. If you have proton carbon 13, that will be much better splitting because you have all 4 different states, right? And you can see the difference is much different actually. That's why when you put carbon 13 MR, you decouple the proton. We'll talk that thing. When you talk about metabolism, we'll talk. So because this is how do we talk? This is a homonuclear coupling. Heteronuclear coupling, all the 4 states are quite different. Okay. And also I'll be talking actually when you look at the transition. So these are allowed, but also these to this transition called double quantum transition, and this called zero quantum transition. Why? Because delta M in this 0 is level 2, which is not allowed. But when you excite, molecule can relax through that pathway. That's called cross relaxation, and we'll be talking that when we talk about the nuclear Hauser effect. Okay. So because NO is basically because of cross relaxation through this pathway W2 and W0. It's clear? We'll be talking that once we get into that pathway, dipole interaction. So now let us focus that if you have 3 spin, how it will be. Okay, 3-spin system. So let's see how it will be. So this is 3-spin system, 3 spin, spin 1, spin 2, spin 3. So exactly same thing. You have M1 nu of 1, M2 nu of 2, M3 nu of 3, and then M1, M2, J12. Now M1, M3, and M2. So you have all combination 1 to 3, 1 to 2, 1 to 3, 2 to 3. Okay, 1 to 2, 1 to 3, 2 to 3, and corresponding coupling constant. This is the equation. And now how many states will get it? Okay, how many states? Let's do that quickly. Let's say you have spin 1, and alpha, beta. First is coupled to spin 2. Okay. This is not working, right? Okay.
This is new ones.
Okay. Thank you. And then you have alpha, beta. Yeah, this is good. So when they undergo spin coupling, you get states like alpha alpha, let's say alpha beta, beta alpha, and beta beta. Now this will again couple to 3rd spin. Okay, say 3rd spin is basically right. So how many things we are getting? We are getting basically, and then you do this also. This also. Is clear to all of you? Okay, that's why it's coupling. All states are coupling. So basically, you will have how many states? You will have alpha, 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 beta, alpha, then beta, alpha, alpha. Then you have beta beta alpha, and then you do same thing for other one. So alpha alpha beta. So the first one is spin 1, spin 2, and spin 3. So therefore, the reason I am putting that alpha beta alpha, alpha beta alpha is not same as beta alpha alpha, right? Because here actually, although this is same 2 alpha 1 beta, they are not same, because here beta alpha alpha is not same as alpha beta beta, because this is spin 1, here spin 1 is alpha, and here spin 2 is alpha, spin 2 is beta, and third spin is same. So they are not identical. So that's the point of saying that it is not like a permutation combination. So they are basically this first spin, second spin, third spin. 3, 4. Then you do alpha alpha beta, alpha beta beta. Then alpha beta beta, beta alpha beta. Then beta beta beta. Okay. So how many states you get? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. Question. Okay. Now let us look at all the states and what are the transition allowed and what are the energies for those transitions, and let's see how many lines will get it and how will be the intensities. Okay. So we'll use this equation and to get all the energy levels and transitions. So these are the all 8 states which I wrote, and total M will be alpha alpha alpha, half half half, plus half 3/2. Here plus half minus half plus half, so it will be half, and minus half plus half should be half, and minus half plus half should be minus half, and plus half minus half is half, plus half minus half is minus half, and minus half plus half minus half, and then minus half minus half minus. These are all M. Now let us do the calculation for allowed transition, and wherever you see plus minus 1, they will be allowed. We will see those things in next slide, and then you do the calculation for energy. M1 nu 1 plus half, M1 for this plus half nu 2, for this plus half nu 3, plus M1 M2 plus half 1/4 J12, M1 M3 J13, and plus half 1/4 M23 J23, and exactly same I do for all of them. You get this number. Okay, you can do yourself, very simple, right? Okay, and then let's look at the how many transitions we can get. Let's focus on this way. So basically, what we are doing, we are putting in all the things in this way. Okay, and now this is homonuclear, so some are basically almost identical in energy because homonuclear, right? So, but if you do heteronuclear, they will be again different. Okay, clear? So now you just put them in 2 groups actually. So they can be divided in 2 sets of 4. Those with spin 3 in alpha state, okay, and those with spin 3 beta state. So in this group, all spin 3 is alpha state. Okay, why we did? Because of so that we can basically use the concept of 2 spin system. Because once you make this, you club them all spin alpha state, that means put it off. Now we can allow the same way, right? Okay, now it becomes 2 spin system. That's why we keep the third spin same. Here we keep all third spins beta state. Because once you keep third spin same, that means you have 4 states under when third spin is alpha. Once you put third spin beta state, again you have 4 states. And that by doing that, it will be easier to understand how many transitions will be there. That means you can have one transition this will be same, right? This will come from this, and you will have another transition. You have same thing, and same, and this. You can quickly do that, right? And also you can look at the things corresponding M. If you look at the M for this to this to plus minus 1, and this to this is plus minus. You can look at that thing. This is, which is I think is shown here next slide. Yeah, so this is shown in the next slide. Okay, so here one more thing. So rule is there, but one more thing you have to think here also. So you have to apply one more rule here. Only one, when you have transition, only one spin will flip, not more than 2, more than 1, only one spin. So, when you have 2 spin system, you do not worry because only once, because if 2 spins flips, that means your delta m becomes 2. Okay. Now, here actually you have 3 spin, you have some possibility can be there that 2 spins can flip, delta m can be plus minus 1, but under that condition you can also have 2 spin flipping. 2 spin flipping will not be allowed, again selection says okay, only one spin. Okay. So, you have to keep that in mind, that is the thing written here. Okay, this is the thing. The selection rule is as before, m can only change by plus minus 1. However, in the case of more than 2 spins, there is additional constraint that only one spin can flip. Applying these rules, we see that for spin 1, you can have 1, 2, 3, there is this one, okay, 2, 2, 4, 5, 7, or 6, 8. So, therefore, for spin 1, you can have 1, 2, this, and this, because you have 8 spin, right? Okay, this is for spin 1. Why? Because in this case, only alpha is flipping. For all these, actual delta m equal to plus minus 1, but only the first one is flipping for spin 1, others are not flipping, they are fixed. So, this is the transition for spin 1. Again, for alpha to beta, transitions for spin 1. Again, here alpha to beta, other two are same. So, transition for spin 1, and again first spin going from alpha to beta, other two are same. So, therefore, for spin 1 you are getting how many lines? 1, 2, 3, 4 lines theoretically. Right now we do not know whether they will come at same position or different position. For that we have to look at the energy gaps. Is clear to all of you? Okay. So, when 3 spins are interacting through bond or J coupling, okay, then you get for each spin you get theoretically 4 transitions. And now we will see whether what is the difference, whether they are coming same position or different positions. Is clear? So, for that we need to look at the energy gaps. So, let us look at the energy gap. 1, 2, 3, spin 2 is alpha, and same thing, and spin 3 alpha state, and this is the energy gap. So, therefore, that spin will come at this transition, will come at this and minus, so that will be moving left side. So, look at this is the location for new one, for first spin location. Without, if you take very low field magnet, it will come here. If you use high field magnet, you can separate the line, you can see fine structure, and then this will come minus. So, it will come this one, 1, 2, 3 is coming here. Okay, is clear? So, this minus half J12 and minus this. Now, if you look at the this, now if you look at the corresponding 2 to 4, where it will come? 2 to 4 will be this one. So, this plus J12 minus J13. So, this is the one, 2 to 4. Is clear? Okay. So, here spin 2 is beta alpha, is whatever written, beta alpha, same thing written. Okay. Is clear to all of you? And then 5 to 7. For 5 to 7, again same position center, and minus J12 plus 13. So, this is the one. Is clear to all of you? So, this actually the coupling constant between 1 and 3 spin, first and third spin. And from this to this actually, from this to this actually, half of J2, from this to this, from this center to here. Okay. And then last one 6 to 8, this one. You look at the energy is this plus J12 up to this, here to here J12 plus 13. Is clear? So, you can see that all 4 different transitions, they have all different energy level, energy gaps. Therefore, they will come at different positions, and they are all centering at this. Okay. So, from this fine structure, you can look at, you can get the value of J13, okay, and also you can get the value of J12. What is J12? From, you have to take from this end to this. So, you get the, or you can get this end to this will be J12, and you can get from J13 from here. So, this we did only for first spin. Now, if you do this transition, this to this, what is flipping here in this case? Which spin is flipping? Loudly. Second spin, right? So this will be the transition for second spin. So that way you can get second spin. And for third spin, so again you get same 4 lines for second spin at different somewhere here or here, depending on the new position. Okay, 4 signals, right? So what about third spin? Third spin? Which one will be third spin? Because single flip, which one should be third spin? Because you already have used, these, and this. So what should be third spin? So first 2 are same, this to this, yes, this to this, because first 2 are same, alpha is going to beta. Yes, and 1 5, look at 1 5. Okay, now look at 1 5. 1 5, 1 and 5. What is delta m? 1. So that is allowed, and 1 spin is flipping also. Okay, if you go from here to here, 1 spin is flipping, right? Now this is the first one from third spin. It will come at new 3 plus minus something, right? Now how about this to this? Again, on a single flip, third spin is flipping. And halt is 3 to 7. Look at the delta m. 3 to 7. 3 to 7. What is delta m? Half minus half. So minus plus 1. So this is again allowed. 3 to 7. Okay. So 3 to 7. Okay. How about this 2 to 6? Again, first 2 are same, not flipping. Third one is active, alpha to beta. So 2 to 6. Let's look at the corresponding delta m. Two to 6, right? 2 to 6. So yeah, half minus half minus plus 1. And then also you have 1 flipping. Okay. So 2 to 6, and then how about this thing, next one? 4 to 8. So first 2 are same, third spin is changing. Okay. What is corresponding delta m? 4 to 8, right? Minus half, minus plus, so it will be 1. Okay. So therefore that will give you the transition for spin 3. So that's how, and then corresponding energy you can calculate, you can get exactly same way. So basically you get 4 for 1, if you have 3 spin you get like 4 lines, and you get 2 coupling constant. One is basically showing is 3, one is 2, and also you will get for others, here you are getting 1, 2, 3, also 1, 2, also you will get 2, 3 also. So that will be coming here, let me say. Okay. So if you, for other transition you will get 2, 3 also. Have you seen? So you 3 spins working. So you need to know 1 is basically coupled to 3, 1 is coupled to 2. That you are getting from the first one, and from other transition you are also getting 2, 3. So 1 is coupled to 3, 1 is coupled to 2, and 2 is coupled to 3. So you should get all. So by looking all lines, you can get all 3 coupling constants. Therefore, using the coupling constant, you can get the diagonal angle. Okay, it's clear. And these are all we're talking 3-spin system. Okay. Okay, so that's the thing. 1 is coupled to 3, 1 is coupled to 2, and 2 to 3. So we get all the coupling constants. Okay, and that's the thing. Whatever I said. So in case of other spin 2, 1 to 2, 3 to 4, 5 to 6, 7 to 8, and for spin 3, 1, 5, 3, 7, 2, 6, 4, 8. Whatever I said, they are all written. Okay. Okay, so same thing we talks. Yeah. Just forget it, and I'll few more things I want to show here. What is time now? This spin system, this already talk. So now how the lines will be, because so let's talk about that quickly. Okay. So if you have two spin system, you get two lines. Okay. So there will be 1:1 ratio, exact identical signal, right? If you have 3 spin system, you get 4 lines. But sometimes if the two coupling constants are same, the middle lines will be merged, you get 1:2:3. Then you have one more spin, you get this line 1:3 into 3 1. Then you have 1:4. So as you increase the spin numbers, you have more lines, and you can basically calculate the intensities also. And then, as I said, that the coupling constant for vicinal, not geminal, vicinal. So when those two spins are like the same plane, and that means dihedral angle is 0, then you have one J coupling constant. When they are like this 180, right, the 2 plus 180, you will have different J coupling. When it's like this, different J coupling, like this, different J coupling. So looking at the J coupling, you can get the torsion angle. So this is the equation actually. What is the equation? Should be there. Yeah, this is the equation. So coupling constant A minus B cos phi, C cos 2 phi. So basically you have to get the value A, B, C. So you know known structural molecule, from there you know phi, you get the value of J. Okay, you know the value of J, you know the value of phi for the known molecule. For X-ray crystallography, you know some molecule, right? And then you get the value of those A, B, C, and that's the, from known compound you get the A, B, C, and then you use the equation. So you know, and then what you can do, you experimentally find J and can get the value of phi. Is clear? So these are two plane. You can see this plane belongs to this, and this plane belongs to this hydrogen. So this one plane passing through this carbon hydrogen carbon prime carbon hydrogen, this plane. Other one is going through carbon carbon, this hydrogen, this plane, two different planes. So the angle between these two planes is phi. As you increase or decrease phi, then your J coupling is changing. So this is the thing. You look from this side. If you look from this side, your bond CC bond is here, right? And then one hydrogen this side, and other hydrogen this side. So basically, and then that means the dihedral angle is this one is dihedral angle, right? Because you're looking from one carbon and through other carbon. So what you can nicely view that one plane this side, the hydrogen is here, other hydrogen is here, so other plane this side. That angle is dihedral angle, right? It's clear to all of you? Now if you plot the dihedral angle, you can see when dihedral angle is 0, you have this much high coupling, JJ coupling. As you increase and goes close to 90, you have minimum. Okay? And when again you go back to 180, again you have maximum. So if you keep on, so depending, that's how using this you can get the value of dihedral angle that will help you to understand the conformation of the molecule. So that's the one of the very important parameter in NMR which will help you to get the dihedral angle and which will help you to solve the structure of the molecule. In addition, there will be another parameter will be finding for NMR. The other one we talk dipole-dipole interaction, which will basically tell that this how the molecule is folded and how protons are coming close together. That way, you also can get lot of information regarding the structure. We'll be talking that soon. Okay, any question on this coupling, spin coupling through bond? Any question? Likewise, you can keep on going for 4-spin system, 5-spin system, exactly same logic. You can keep on doing that same way. It's not difficult. Okay, is clear? Okay, same thing what I talk. Same. Now, in this case, 3-spin system, okay, you can have this also. If they are kind of merging, same, then it will be kind of going up actually. Right? Okay. Now, here I said this thing again. What have I told? The magnetic. If you see that these two lines, you have two spin, nu1, nu2, right? And if you have high field magnet, you can have you have nice resolution, you can see two different lines, and this also you can see. If you decrease the magnetic field, they can be coming very close, so the fine structure cannot be seen. This is technical. Second part is inherent. Suppose nu1 and nu2 are very close, because although these two protons are coupled through bond, but their microenvironment is kind of close, very close. Then the nu1 and nu2 will be very, very close, right? Right? So in that case, what will happen? So you will see this kind of scenario. As nu1 and nu2 getting close, they kind of become like this. Even though you have J coupling is same, but distance decreasing, because if the coupled protons microenvironment is getting closer, almost getting closer, that means you are decreasing this nu1 minus nu2, right? Here is 10, so this is basically coming to this stage. Okay, is clear to all of you? So sometimes, even though you are using 900 megahertz NMR, sometimes you cannot detect coupling between two protons if they have exactly identical microenvironment. May not be exactly same, but very close to very close. Then they are basically coming resonating almost close to two frequencies. They are very close. If two protons have close microenvironment, they are resonating at two frequencies which are very close. And now, if two close lines are now splitting, so everything gets mixed up, right? Is clear? So this is the thing, point here. So okay, this thing I showed in the beginning, then I switched. So basically, this is when your chemical shift, your delta, and then things are changing up and down. You don't worry about that. We already discussed a lot. So basically, when you have shielding, deshielding, those news are changing. We discussed that also. Okay, so those things we discussed nicely. So you know now. Okay, you know this thing. You know this. Know this. Know this. Okay, we talk about active spin. Only one is flipping. So that is the one which is flipping called active spin, or is passive spin. Right. This is okay. Is clear? Who is talking? Okay, these I will talk. The carbon proton also is very good one. Three spin system. We talk this. We talk this. Talk this. Talk this. This we don't have to worry about this. Okay. So far we talk about the how two spins are coupled and how many lines we expect and how they are basically generating those lines we talk. Okay. So and now actually we can see that we can use that information to get the structure or torsion angle. Now you can also do some kind of decoupling experiment. Okay, suppose say this molecule, if you look at this molecule, okay, in this molecule which one is highly deshielded? This one, right? So that is coming here. Okay. Sorry, this yeah, this is the one. Okay, 4.35. Okay. Now this is somewhere middle, that is coming here, right? And then this is methyl is coming here, right? 1.02. Okay. Is clear to all of you? Now if you look at this couplings, this one, this is basically undergoing how many spin? Because one is proton here, two proton here, so this will basically have 3 spin system, right? And 3 spin system means you get 4 lines, right? And middle lines are getting merged, so you're getting here. Okay, is clear to all of you? So this is the 3 lines you'll get for this one. Now for this one, how many will be there? How many spins will be there for this one? Again, this will see this proton, these 2 protons, right? So a 3 spin system you will get 4 lines, but middle one is basically kind of same, right? It's clear to all of you? So you get 1:2:1, that ratio. Now let us talk about this one. This will basically see this is 2, right? So how many for this? How many spin? 1, 2, 3 spin. Again, this will see again here 2 also, right? So how many? 5 spin, right? Okay, and so how many? Yeah. So yeah, 1, 2, 3, 4, 5. So how many lines will you get? 6 lines. Okay, and then you go back to the plot and how. Okay, so let's go back to the table. We have that. Okay, So 1, 2, 3, 4, 5. Okay. Now how many? 1, 2, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I think this is kind of when a lot of identical things are. But there is another Pascal chart in some other book. Yeah, that rule is there, because when there lot of things are merging, this is a different one because they are kind of same. But there is this Pascal thing you can find all textbook. So you can look at the ratio actually. I have that book actually. Okay, do you have this book? This is a very good book. Okay, this book has that table. Okay, you can look at this book. You can find. Okay. Okay, this is the one you actually have this table. Okay. Harris. Yeah, very good book. Robin Harris. Okay. But there are other books also. There are several books on there actually. This is written. No, this is like a more like coincides, like a not. This is for like any layman can do, but if you want to do really, there's a Gunter's book there. There's several very good books are there. Okay, and I was basically preparing in that way, but I was told not to go in that way. Okay, so that's why I doing this so that you can understand. And this is the basic concept you should get it, because how J coupling happening and dipole coupling, and based on that we will do the experiment and analyze the data. Okay, Noji, Koji, Toxi will be using those. Roji. Okay, so basically right now, what's time now? Yeah, Roji, Koji, then you have Sexy, okay, Spinico, okay, and then you have Helco, lot of things are there. So we'll be talking those, okay. But before talking, you should know at the basic level, because all of them, these are the basic concept you should know before going to those things. Okay. Yeah, because different, basically it's a pulse sequence. You just change the pulse sequence and look at what is your aim. Helco, you want to look at the DNA backbone. You are using P31, right? Okay. And Noji is basically big molecules like a small. Sometimes you don't get Noji peak. You have to put in rotating frame. So you have Noji in rotating frame. Okay. So Raman is a different thing actually. Yeah. Okay. So that's completely Raman. Here actually whole phenomenon is based on nuclear spin. Okay, so you are basically all looking at nuclear phenomenon. If you do ESR is much more sensitive than NMR, right? If you ESR is more electronic splitting, right? That is much more sensitive. Okay, this is nuclear spin. And I think yesterday we started in the afternoon, maybe towards evening time. This one we had talked about 30 minutes. So there we talk only nucleus spin will be is their phenomenon. Okay, Raman is different, ESR is different, and fluorescence is different. They are all different actually. And
with different techniques, we can characterize the same. We can come to the same conclusion.
Yeah, but like NMR can give you solution structure, dynamics. X-ray cannot give. Okay, your CD cannot give. CD can give. Okay, this protein has 60% beta seed, like one thing that won't tell the atomic what is at the atomic is nothing. CD says okay, this molecule has 60% beta seed or 40% alpha helix. You just get this and 2 peaks, 222, 230. That's all you can tell. That may be the starting point. You purify the protein, makes your protein is folded before putting NMR. Nowadays, actually, you do not have to do CD. Just put the protein in NMR. If protein is folded, you can get very high dispersion. Okay. Sometimes you look at the DNA structure, quickly see how the DNA is basically forming structure. Do CD. Nowadays, you don't need to do that. You can put the DNA in the NMR tube. If you see nice dispersion of the immunoprotons, that means hydrogen bonds are formed. It must have adaptation of secondary structure. Okay. So for instance, therefore you can bypass easily the circular dichroism. Okay. Now, if you want to do study dynamics or different conformation, you cannot do those things from X-ray. So therefore, it's not that you are basically some cases you don't get same conclusion from two different techniques. Okay. So after what is now? Okay, let me see how much I can go. What is the next? Yeah. So basically the decoupling. So in this case you have all the things. Now what you can do, you can decouple. If you decouple, that means suppose you are basically decouple this one. What is this one? This is this one. If you basically decouple this, that means this one will not be coupling this. Basically it is only doing this. So this pattern will be, okay, which is, what is this one? Yeah, this one. Now which one you are decoupling? Because this is this one, right? If you decouple these, what will be affected? This will be affected, both will be affected, right? Okay. So you can see that this is middle one, right? See. So now you have 6 lines became 4 lines. Okay. So because this coupling is still there, on this is not there anymore. You decouple it. Okay. Now if you do this one, if you do the middle one, if you do couple the middle one, then this will not be coupled to anything, right? Because this will be geminal. HH is geminal, right? So it will be singlet. And this will be again geminal, single. Right? See. Now if you do this one, so this is off, okay? So this is off, that means again, but this will be there with this, right? And this will be still with this, so that is there, okay? So that's how you can do decoupling experiment. And now when you do heteronuclear decoupling, carbon, I have carbon and proton. So heteronuclear decoupling is very important for carbon and NMR spectroscopy, because carbon and proton, because when you see that in NMR, then carbon proton is there. So therefore they are actually need to decouple because other carbon will be affected. I will be talking those things when you talk about the NMR of for studying metabolism. Then I will talk those things. Okay. So all the things I talk. Okay. Now you can, this one I will talk, right? No, I talk this also. Okay. Now this one also I mentioned that this is the, if you take 900 megahertz NMR spectrum, then this is the thing. You see that thing coupling, but they are very almost overlapping. The coupling constants are not changing, but because of resolution, those lines are all overlapping. Now you do the same thing sample in 400 megahertz NMR, you increase the resolution, you can see those lines separate. You see? Here they are all sitting on top of each other, right? So you do not basically increase the coupling constant. This is inherent property. Coupling constant is inherent property. That's why you can basically use the coupling constant to get the dihedral angle, get the conformation. You don't change that. But you increase the window resolution, therefore you can see the fine structure. Okay, which I already told, right? Okay, same thing here. If you use 500 megahertz NMR, so nice thing you see. If you do 100 megahertz NMR, you won't see that thing like it. Okay. Okay. Now, as I said in the beginning, those lines, NMR lines are not like fluorescence, right? Fluorescence you get broad line, right? Broad line. You don't get same thing in here. Why? Just looking at without looking at that, why you don't see that thing? And also in electronic transition, you need very small amount of sample, right? And here you need lot of samples. You need millimolar quantity. When you go to 900 megahertz, you may be needing much less, 0.2, 0.3 millimolar can give signal, right? Because by increasing the magnetic strength, you increase sensitivity, therefore small amount of sample will be fine. That is good, because if you use high concentration, they can precipitate, or sometimes they can increase viscosity, and viscosity has a lot of problem of the line shape. We will be talking that thing. If you increase the viscosity, the line shape will be changing, and if a lot of protons, so you can decrease the resolution. So therefore, it's always good to use the less amount of sample to avoid aggregation, to avoid the viscosity. If it's DNA sample, you cannot use too much, right? It can be viscous, right? So we'll also talk about solid state NMR. Okay. Also, we'll talk about MRI. Okay, we have still today whole day and tomorrow and Saturday morning. Yeah. Because if you, I think you are not there yesterday, or I think you talked in the beginning that NMR was basically developed by physicists up to 1950. They are doing, physicists are working on that. They accidentally put the alcohol, and that's how the whole NMR changed the whole thing, right? Now chemists got in, and I'll so very soon biologists will get in when we'll do trip NMR, and then to pulse 2D NMR, then it will become more application in biology also. Right now we are at the level of chemistry, okay, in early 60s or 50s, okay. So yeah, you can do NMR for any molecule which is nuclear active. Now you can do solution NMR, you can do solid state NMR also, MRI, but their philosophies are different also. Okay. Sometimes people are using NMR to detect the dangerous material in the airport also. No, suppose you want to do NMR of a protein, and that protein will not be dissolved in liquid or toluene or, okay, because it has to be hydrophilic. Because putting amphiphilic molecule, you have to do water with salt. Maybe you have to put some salt also, because pure protein and pure water, they won't mix actually, right? Because if you have you take a protein, right? Can you dissolve protein in water? Because amphiphilic molecule, and you need to have salt in that, okay? And some proteins actually, too much salt is not good, because some proteins folded like this, and there's salt bridge also, right? If you use too much of salt, that can break the salt bridge also, right? You can destroy structure. So you have to have minimum some concentration. Similarly, when you put DNA NMR, you cannot just do DNA NMR in water. You have to put DNA, you have to put salt around, salt also, right? Is clear? So therefore you cannot use inert solvent. First of all, you cannot dissolve the amphiphilic molecule or hydrophilic molecule in a solvent. So you cannot do the experiment, right? Okay, we can talk more during lunch time. But can you just quickly tell why NMR signals are so sharp? If you really do good experiment, make the magnetic field homogeneous, and you can get very sharp line. And if you do fluorescence or absorption, you get very, very broad line. And why is that? Less. Okay. 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 So I think so. You have three things actually. So you say that relaxation is very fast. Okay. In electronic transition, right? In NMR. Okay. Yeah. So relaxation constant is very important. We'll get in that. Okay. So in fluorescence, relaxation is pretty fast. So that's why, and I'll talk about that. And you said that excitation thing. Okay. Okay. So yeah, towards that direction. We'll go in that direction. So let's talk about that, and then we can go for lunch break. So if you look at the fluorescence, we'll talk about the relaxation lifetime, and then we'll talk about the excitation, and then we'll talk about this. Because it is very important when you do NMR, make sure you make your field homogeneous, and make sure that you don't have any paramagnetic materials. Okay, and also make sure the solution is not very viscous, and temperature should be good actually. So then you seam the magnet and make it highly homogeneous, and then you record the spectrum. You will get a very, very sharp signal. And if you don't get a very sharp signal, like so before setting the experiment, you have to make sure you put the sample, and then do seaming, make sure your magnetic field becomes homogeneous, and then you get very sharp band, and then you have better resolution. That's very, very important technical part. But now question, why NMR signals are low, so like line, and fluorescence signals are like this, absorption signals are broad actually. So if you look at the fluorescence,
Electronic transition are accompanied by vibrational transition, and vibrational are accompanied by rotational transition. So there will be a three transition in a electronic spectroscopy leading to a broadening of signal.
Okay, so they're getting close, but almost getting in that direction. So we are getting in the same direction. So let's for the whole class, let's do this way. Okay. This is the electronic state, ground state, electronic state 1, excited electronic state, right? And each electronic state is associated with vibrational state, right? And then each vibrational state is associated with rotational state. So this is continuum, right? Continuum, right? So it's not like distinct, so all continuum, because each vibrational state is rotational state, right? Right? So now say in electron sitting here, okay, and then you excite the electron, some goes here, that won't be come. So let's say you excite this electron, it goes this energy, it goes. It has to go to lowest vibration state before it emits. So you excite this thing here, and this relaxes to lowest vibrational state, and then from there it is emitting. You get H nu, right? And so whatever which is basically, now here you give this energy, so say this energy E equal to H C lambda excitation, lambda emission. It's clear? So lambda excitation will be definitely higher than lambda emission. Okay. Now then it has to relax. So basically it stays in this state some time. So this time is known as lifetime of the fluorophore, lifetime. Okay, fluorescence lifetime. And you measure the fluorescence lifetime using laser spectroscopy, right? Like you have picosecond laser, femtosecond laser, you can that way, because the laser, because you have this short pulse and see, because you cannot give pulse for 1 second, because the pulse has to be shorter than this. Okay, and then you see that's how you can measure the lifetime. So picosecond is, it can be smaller depending on the molecule, how fast it's tumbling, because that is also playing very important role. So molecule is very big, and actually so many things are playing role. Tumbling, rotational correlation time, tumbling time, all are playing role here actually. Okay, so the lifetime of a fluorophore will be different depending on the microenvironment, molecular size, viscosity, so many things are there, right? And then it comes back, and then it comes back here. Now some you excite like this, some electrons sitting here also exciting, right? So all coming back. So basically if you excite this thing, and then they will come back, they can come here, here, okay? So you get basically what? You get basically the broad things, right? Okay? Okay, in NMR what we are doing actually, you are basically the exact whatever regenerating, you are getting that one actually. And when you do Fourier transform also, you are basically going from time domain to frequency, you will get single peak. We'll be talking that soon actually, okay? Is clear to all of you? Okay. So in NMR actually you get this kind of signal, which is basically Lorentzian line. The equation, because this is a equation for the line y is this as a function of x. So y is this as a function of, so y is basically a Lorentzian width at half height. Okay, so that's the at half height square. Lorentzian width at half height square plus 4 x0, where the peak is coming, minus x, where x. So you can see maximum y when x equal to x0. When x equal to x0, that means this part becomes 0, right? And that means this gets cancelled out. So y equal to a. Is clear to all of you? No, backside is not clear? No? Okay, basically y is this is a Lorentzian function. So y equal to a multiplied by the half width of the peak at half height square divided by width of the peak half height square plus 4 x0 minus x square. When x equal to x0, that means when x is 0, that means this part becomes 0. So you are left with this one. Then this gets cancelled out. So you are left with a. So this is basically height. So at x0, you get maximum height. Okay, clear? Now when x equal to say 3, then when x equal to 3, that is y becomes almost 0. When x equal to minus 3, y becomes 0. Okay, and so basically your x0 is basically around 0. Okay, that we can do calculation. That's why if you do Lorentzian, very sharp lines are very sharp. Okay, now you have to make sure this line, make sure line's width should be as narrow as possible. Now if this is like, so how much narrow you should go, and then you have to basically resolution you have to choose how much resolution you look at this thing. So when you look at, you don't get line like this, you get to take the data points. Okay, and that's a get analog, then you convert to digital, analog to digital converter, right? And then you get signal. So that means how many data points you should take it. Okay, that will tell a lot actually, because if you take data point, one data point here, one here, one here, one here, you will get sharp line. So that means your resolution has to be less than half of the width. If width is here, this, half of that is this, resolution has to be less than that. Then you can get very good quality data. Is clear to all of you? But that will be clear very soon in next few slides. Is clear to all of you? Any question on this? So also another thing, we talk on signal to noise ratio. So when you record the spectrum one time, okay, you get a lot of noise, weak signal. Sometimes signals can be very weak. Now if you record the same spectrum multiple times, you increase the signal, decrease the noise. So that means signal to noise ratio goes up. Okay, how? Because signal to noise ratio is directly proportional to the root square of the number of scans. Okay, so that is it. Let me write here. Signal to noise ratio is directly proportional to number of scan. Okay, number of scans. Okay, if you take one scan, your signal to noise ratio for one, if you take one scan, your signal to noise ratio will be proportional to 1. If you take number of scan 4, signal to noise ratio will be 2. If you take number of scan 64, signal to noise ratio will be yeah. Okay, so that's it. As you increase number of scan, you can increase signal to noise ratio. Otherwise, here so weak, your signal very weak. So that's why you do multiple scanning. Number 1. Number 2, signal to noise ratio is equal to the 2.5 amplitude divided by NPP. What is NPP? This is the thing. Basically, if you have noise, maximum noise, and this side. So basically, you have baseline, maximum point of the baseline, minimum point of the baseline. That's the thing. So basically, peak to peak noise means exactly that a measure from the most positive to most negative position of the noise. That's the thing. If this goes high, your signal to noise also goes down. Okay, it's clear. So and this amplitude of the signal. So if signal, say suppose amplitude of signal is low, that signal to noise goes down. If this noise is more, then signal to noise goes down. So basically, what do? You basically increase the number of scan, 64 scan or 100 scan. You increase the signal to noise ratio. This goes down. You can see very nice peak. Okay. Now, if you do continuous wave NMR, that means you have to sweep. Suppose you are doing say proton NMR, you have to sweep from say from this field to this field continuous wave. If you go to this one, this slide back again. Yeah, if you're sweeping the field here from here to here, so you have to, when you sweep, you have to go slowly, because you have to allow to regenerate, right? Slowly. So each sweeping will take some time. Okay. Now you do 100 of them. So each sweeping, say, let's say it takes say 5 minutes, let's say, or maybe say 10 minutes. Then hundreds of them, how much? 100 into 10. Okay. Okay. So long, right? Okay. Now it is a very difficult to do continuous wave experiment and it's very difficult, right? You have to finish one experiment, you spend so many hours, and then after that you get the data. So that's the time people found it's a real bottleneck. So how field develop actually. So people, it's a really problem. So we should we should not stick to this. We should find something so that we can do the experiment much faster. So in early 60s, Richard Ernst, who got Nobel Prize in 1991, 91, 92, or 92, 91 I think, right? 91, I just showed in the first slide. 92, yeah, because he came to TI for when I was a PhD student, I have a picture with him. Immediately, I think around the time he got Nobel Prize, I think within a year. Okay, so yeah, so he thought that instead of doing this way, what you do basically, you get the, what you do, you flip the magnetization to XY plane. Earlier it was like precessing around Z axis, right? Okay, you give a pulse so that it goes in the XY plane. And then you put a detector here in the XY plane. And once you put the pulse up, then this pin will again relax back to this position, right? Because once you put pulse, it came here. Then put the pulse up. Then every system will go to its equilibrium state, right? Its equilibrium is here because magnet is applied. So it will try to go back. So it is going like this, right? So as you going back, in XY plane, your magnetization is going down, right? So therefore, you can get a signal like you can plot in mx, magnetization in XY plane is going down as a function of time. So you get a signal as a function of time. Now in math, there is an equation called, there is a transformation in math called Fourier transformation. You can basically go from one space to other space by Fourier transformation. Now you are in, your data is in time space. Now you can apply Fourier transform to the time space data, and you can go to another space which is frequency space. So therefore, that's that equation was there in math, but he applied that thing and it worked very nice. So instead of looking at those that way, you look at the magnetization. So you can say free induction decay as a function of time and apply Fourier transform and get quickly the signal. So this will not take much time, very fast you can, right? Okay, you don't have to sweep slowly this field. You just flip the magnet, put the pulse off, goes back, and they get then do Fourier transform, and quickly you can do, right? So that way you can do same experiment much faster. That's in 60s people are switching from continuous wave to Fourier transform NMR. Okay, so before I show that thing, or I can talk those things after the lunch. What is the time now? 1:20, 1:25. Yeah, maybe just a few things. Then I'll just maybe we'll go up to 1:30, and then we can go for lunch. So is it clear to all of you? This part is clear, yeah. So basically, okay. So what he did actually, you basically get into XY plane same way, and then you go from time space to frequency space by Fourier transformation. What I said. Okay. So which is shown here. So this is XY plane. This is this plane. Okay. So you basically put a pulse. The pulse has to be suppose you are putting pulse in x axis. Okay. So therefore, the moment you put pulse, basically all spin go there and species around there. As long as pulse is there, the spins are speciesing around that x-axis. Then put the pulse up. This is 90-degree pulse. If you do 45-degree pulse, it will come somewhere middle actually. So 90-degree pulse will get into that plane, and along x-axis, it will precise along x-axis. And put the pulse up, and then after that, what will happen? Next moment, it will go here, here, here. First, it will go same like. Next, it will go slightly back, again goes. It's like initially it will going like this. And then next moment going like this. Then going like this, going like this, going like this, right? So you can look at the mx actually, here actually, when your detector is here. So here actually you have at 0 point minute, you will maximum here. Okay, and at that time y component is 0. And then next moment it is coming here, it is here. Okay, and y is increasing now. Okay, because you have cos theta sin theta component, right? Okay, and then next part actually 90, this component is becoming now 0. Okay, the detector is here. and this became maximum, and the next moment is going here, okay, and then this is going down, and this is going, and then next moment here, you are here, and then here, that's the goal. So first one actually you get maximum peak here, right, and the next next moment is slightly relaxed back. Now this, okay, so going like this. So if you look at the whole thing, okay, this is the thing, whole thing I'm showing here, and then, okay, so this is first one, and then next one goes, right? So that's how we get the pre-induction decay, because it's pulse of pre-induction decay, and then you do Fourier transform, okay. So basically what I'll do now, how the Fourier transform is done, I'll not go too much of math, I'll just talk for your understanding in a very physical way, physical concept I'll provide after the lunch from here. We'll continue from here, okay. So we'll show that why it was needed, and this is a major things in that time. So it made the life much simpler. You can do NMR spectrum of any sample very quickly instead of continuous sweeping many times, even though you cannot do like 20 times, you cannot do 100 means so many hours, right? Okay, so this is very, very quickly, you can record a spectrum very quickly, in 5 minutes, 10 minutes, you can get very good spectrum with high signal to noise ratio. Now we'll discuss that from this point. Actually, you got this kind of pre-induction decay, how you can convert this signal from time domain to frequency domain, and how will be the shape of the line. Okay, we'll discuss after lunch. You can get that thing to Fourier transform and get the peak. Okay, so this is actually, look at the one thing, lower one, and this is the vector actually, magnetization vector is going like this, and this is the angle, okay, and the frequency is this one, and multiplied by t, that's angle, right? So we discussed that in the beginning, omega or 2 pi nu, so that frequency multiplied by t is the angle actually. Okay, now if you look at the component, S component will be, okay, m0 cos omega t, omega or whatever, okay. So that angle, the frequency into t, and you know that very well, okay. So you know from trigonometry, this by this equal to cos frequency t. So this will be S0 cos frequency t, this will be other one, right, sine, okay. So mx component x-axis, because is this m0 cos frequency t, and my m0 sine frequency t, okay. Now if you do as a function of time, because you look at only one time point snapshot. Now if you do as a function of time, you can do signal as a function of time is changing. So S0 is the signal which is basically signal, okay, multiplied by cos frequency t, and SYT will be signal, okay, which is basically original thing, and then you are basically, okay, this is the overall size of the signal, is like m0 is the overall size of the signal, and then what component of that, because if you look at this point, this is the S0 or m0, that's the, and then what, and looking at this component, and at this point you saw this thing. Now if you keep on changing time, then Sx will change as a function of time. At time equal t1, it is here, t2, t3, t4, t5, that's going on, right? We are looking at signal along x-axis as a function of time will be S0 multiplied by cos frequency t, and signal along y-axis will be S0 sine frequency t. Is clear to all of you? Okay, that's a thing written. Now if you look at the total signal will be Sx plus I Sy. If you look at, one will be real part, other will be imaginary part. Okay, so you look at the two component which is written to think signal arising from a vector length S0 rotating at frequency this, and x y components of the vector gives Sx and Sy, Now, if you put the vector together, total will be Sx plus I Sy. This is all vector things we have done, right? Okay. So, as a consequence of the way the Fourier transform works, it is also convenient to regard Sxt and Syt as the real and imaginary parts of the complex number. So, total signal St, some problem? Okay. Okay, the total signal St will be Sx, the x component as a function of time, plus imaginary number and Sy component. Now, now put the value of Sx, which is this, and put the value of Sy, which is this, and this second part is imaginary part. Now you know that this part, both part has what is common? Both part has common is S is common. Okay. It's not working. No, it will work. Oh, no signal. It will come. Is coming? Okay, it will come. The reason. Okay, just 1 second. 1 second. One second. No, it's not connecting actually. It's not connecting. You have to. No, let me see. No, it's not working. Sine frequency. So you know that exponential I frequency equal to cos frequency plus I sine frequency. That you all know, right? So that means you can write this thing. So signal as a function of time in this. Okay, can you? Yeah, slide at the bottom. Okay. Okay. So as this is moving, how the signal is changing as a function of time. So that is basically this. So as time changes, signal changes as a function of time. Okay. So basically, so this part, and second part is basically we need to know here. Second part we are adding. So basically, that second part actually there will be decay. Okay, whether signal will decay fast or slowly, because this came from, then it has to go back, relaxing back. So for relaxation, there can be two different types of relaxation. I will be talking soon. Longitudinal T1, which is spin lattice relaxation, and then transverse spin relaxation. We will be talking that separately. So basically, when it's going back to equilibrium, it relaxes. So that factor has to also be clubbed in this. So let's read. Okay. So now here, so that we are putting transverse actually. So because transverse actually is a relaxation, spin. Several factors are playing role that in that relaxation pathway. We'll be talking that soon. So let's say this is the time T2, transverse relaxation. So now you have seen that when you start with single substrate, okay, and it decays. So it's a first order or second order reaction. You flipped it and it is relaxing. Only once, first order kinetics, right? And if you do first order kinetics, what is the kinetics actually? First order kinetics. If you look at the first order equation, how does it work? Okay. Let me just quickly so you can tell. So basically, let's say in this case, actually, your excited state goes to relaxed state, right? Okay. So if you do this thing, how this C equal to, let's say A star, in this case A equal to A star e to the power minus k t. So this k is basically, this k is the rate constant. Okay. So which is basically, we can say, okay, if it is basically relaxing very fast. If it is relaxing very fast, that means denominator is small, and k will be, rate constant will be high. Okay, so then this is high. Now, once you do this thing, so this second part will be very small. If second part is very small, that means A will be very small. So that means you are decaying fast. Okay, so if relaxation is fast, signal will decay very, very fast. Okay, if signal decays very fast, what will happen? Okay, it will be showing very, very soon. Signal decays very fast, line will be very broad, will be showing soon. So if you have in a sample, if you have paramagnetic substance in a sample, or if you have magnetic inhomogeneity, that means relaxation will be very fast. Okay, that means T2 is very small. Okay, decay is very fast. Okay, and then we'll show that will be connected to line width. Line will become very, very broad. So for this thing right now, focus on that you have to consider T2, because the two things are going on. First, actually, it is going like this, and then it is relaxing, right? So spin, relaxation going on, right? Goes there. So that also has to consider. So second part, actually, I'm taking this. So exponential minus kt. K is the rate of decay, which is equal to 1 by T2. So rate of decay is inverse of T2. Okay, relaxation, transverse relaxation, right? So this is the part we are adding to that, because the two part, this part actually in plane and then relaxation, two things going on. Okay, a typical example is just in figure. Okay, so where this R2 is the rate constant, first order rate constant. Is clear to all of you? So S t equal to S0 exponential I frequency t exponential minus decay relaxation rate constant into t. Okay, the shorter the time T2 or the larger is the rate constant, the more rapidly signal decays. Whatever I said, that is written here, right? So you can see that there are two components here. In this, actually, the two components here, actually, one is sine component, one is cos component, because this is basically, this part is equal to the cos and sine component, right? Okay. So now, actually, the first part will be S0 cos frequency t exponential minus R to t. Second part will be I S0 sine frequency t and exponential minus R to t. The first part is basically is shown here. This is x component part. Okay, it's decaying, and this is the y imaginary part. Okay, if you have detector in the x axis, you will pick up this. If you have detector in y axis, you will pick up this signal. Okay. Now you want to do Fourier transform. This is a P in induction decay, showing real and imaginary parts of the signal. The signal, how do you get? You get two parts. One is real part, one is imaginary part. Real part is in x axis, imaginary part in y axis. If you have detector in the x axis, you will pick this real part. If you have detector in the y axis, you will get this signal, imaginary part. Okay. Now you do Fourier transform. Okay. So now if you take the real part, you will get the signal like this. We do Fourier transform like this. If you look at the imaginary part, you get dispersion. Okay. And now that is centering at frequency. So earlier your signal was in which domain? It is as a function of time. See, it is as a function of times, all time, right? Time changing, signal changing at some time. Now, okay, now that is you do two different things. Look at the x component, putting detector in x axis, you get absorptive line. Okay, and if you put it in y axis, you get imaginary component. After doing Fourier transform, you get dispersive line. Is clear to all of you? And dispersive line centering here in this position. Absorptive line centering at x0, Lorentzian shape. Okay, so whatever I said, that is written here. Lines are Lorentzian, and then you have dispersion mode. If you take imaginary part, and a real part will give you absorption mode. Is clear to all of you? Now, if you have small T2, that means you have fast decay. So signal is decaying very, very fast. Have you seen this thing? In this case, T2 is very small. That means fast relaxation. In this case, T2 is quite large, slow relaxation. So decaying slowly, right? Now, if you do Fourier transform of this, your line becomes more broad. If you take Fourier transform of this, line becomes very sharp. This is somehow intermediate. So you have get intermediate. So what is the difference between these three FID decay? So this is decaying very fast because you have small T2, that means relaxing faster. So you get this thing. So therefore, now let us see the correlation between line width and relaxation rate, which is shown here. So line width is inversely proportional to T2, which is shown in the next slide. Okay. In absorption, line shape has a width at half of its maximum height is 1 by pi T2. So when molecule is relaxing very fast, T2 is very small. Okay, T2 is very small. That means line width will become big, because if you increase the denominator, the net fraction is increasing. Is clear to you? So this means that faster the decay of the FID, the broader the line becomes. However, the area under the line, that is the integral, remains the same. Right? Line just become broad. Okay, so the height goes down. Is clear to all of you? So if signal decaying faster, it makes line broad. And when signal can decay faster, when you have more faster relaxation, you can spin relaxation. You can have if you put paramagnetic substance, if you put inhomogeneous magnetic, because if you put a sample, that area where a sample, you have to have highly homogeneous magnetic field. If you don't have, then also relaxation go on fast, and you decrease T2 lot, and FID decays faster, line width becomes big. So line becomes more broad, that will decrease resolution. Okay, is clear to all of you? Okay. Now, so far we talk only one. We talk an isolated case where you have only one spin. You flip it. Now you put a molecule. We have multiple protons. Let's say you put same ethanol. So you have 3 spins, and all three, when you give 90-degree pulse, all 3 spins will be flipped into XY plane, right? Right? Then you put up the pulse, and then they relax back. So now if you look at the signal, you have same X component and Y component for every spin. So that is shown here. So for spin 1, you have spin 1, S0 spin 1, exponential I, because this part comes from cos frequency t, I sin frequency t, and then corresponding relaxation of the spin 1. This comes from first spin. Ethanol has 3 different types of hydrogen, right? So methyl H, CH2H, and OHH. So let's say this is coming from CH3H. So first one. Then you also have second one. Also you have different relaxation rate, different frequency, because it has different chemical environment. And third one also will have same different frequency because different chemical environment, and different relaxation rate, spin relaxation rate. So therefore, in this case also, it is sum of all spins. If you have like 100 protons, it will be sum of 100. Okay, is clear to all of you? Then you do Fourier transform. Then if you do Fourier transform for x component, you will get signal from this. The signal will be centering at this frequency, and then second spin will be centering at this frequency. Third spin will signal at this frequency. Okay, so which is written here. We have allowed each line to have separate intensity S0 and frequency I and relaxation rate T2I. Now, the Fourier transform is a linear process, which means that if the time domain is a sum of function of the frequency domains, will be a sum of Fourier transforms of those functions. So as Fourier transformation of each of the term in ST gives a line of appropriate width and frequency, the Fourier transformation of ST will be the sum of these lines, which is the complete spectrum. Whatever I say, that is written here, right? Okay, so basically, if you have 5 spins, you will have 5 components. 10 spin, 10 components. When you Fourier transform, each of them will give lines. So, and those lines are centering corresponding frequency, appearing at that frequency. Is clear to all of you? And when you put the detector in x-axis, you get absorptive line. Okay, detector you put in x-axis, and that's how you measure the signal. So how magnetization? When you flip it, you have maximum magnetization. With time, it is decaying, decaying, decaying. Finally, spin goes back to its original state, speciesing around z-axis, or speciesing around applied magnetic field, which is in the z direction up. Is clear to all of you? Any question? Okay, so it's same thing. In this case, if FID for just water, let's say water, okay, you get single line. Here you get pre-induction decay of a molecule which has 2 different protons. So there's mixture of both. Okay, you flip all and then you have 2, and because that signal as a function of time has 2 different frequency because you have 2 protons, and they have to have different chemical environment. Therefore, once you do Fourier transform, you get 2 different lines. Absorptive mode, which you are looking at x component. And when you have multiple protons with different chemical environments, they will have different frequency of regions, different relaxation time. So some lines are broad, some are sharp, because they have different relaxation pathways. Okay? It's clear to all of you? So FID is time domain signal. Then you do Fourier transform, and then you get spectrum in frequency domain. Last one has many different protons. Yeah. No, it's same compound. Let's say you take one compound like ethanol. Ethanol has how many? Many protons, but you can classify those protons into 3 different types because they have 3 different chemical or microenvironment. Therefore, they have different electronic environment. Therefore, they will have different shielding or deshielding based on the discussion we had in the morning. Okay? So, therefore, they have different relaxation, they will have different resonance frequency. So, therefore, you will get this kind of thing. So, you have 3 different protons, you have proton 1, proton 2, proton. This will be methyl proton, CH2 proton, and OH proton. And once you
Technique is exclusively based on proton behavior under electromagnetic field.
okay, so 2 things actually. So yeah, I think yesterday you are not there. We discussed this to us. Yesterday, any nucleus with spin can have same resonance, nuclear magnetic resonance, and we are doing proton, and we can do for carbon 13, P31, also other nuclear other nuclei with nuclear spin. Okay, so it's clear.
Suppose the compound lacking protons. Can you go for any?
Yeah, if that compound contains any nuclei with spin, can be detected by NMR, and that may not be 500 megahertz, maybe different megahertz, because as I discussed yesterday, different nuclei will resonate at different position. Proton, if you use 900 megahertz proton NMR, that 900 megahertz basically resonating for proton. For carbon, it will not be 900, it will be less. Okay? So if that compound has P31, that compound has C13, or fluorine 19, that will show NMR signal. Not at 900 megahertz NMR, proton NMR, not that, but in that NMR machine you can see at different frequency. It will be maybe 600 or 700. You can say that instead of 900, you can say that 600 megahertz P31 NMR. Same machine you can call 900 megahertz proton NMR. Okay, it's clear. We discussed that yesterday. This one. Okay. Any other question? Okay. So here again, we have given this XY, and you flip it by pulse. You get this thing in XY plane, and it will basically relaxing. Okay, how we do this experiment? So we say pulse. Okay, this was done actually again by Utrecht. No, it's not this, Richard Rans. So he did a lot of great groundbreaking discoveries in the field, and without his lot of theoretical work, NMR could not have been to this stage. Actually, he has done a lot of work on this. And 70s, then 2D came actually. He's the person who will be talking that soon. So this is the pulse sequence. So right now, we are not doing any more continuous wave. We are not sweeping. Nobody does actually. Okay, so those are like in 50s, early 60s. And now you have to do pulse. So how will you do that thing? You basically give some pulse, and that will flip it. Now, if you look at the term called pulse width, so you give 90-degree pulse. So that pulse actually, you put that frequency in x-axis, towards x-axis. So and that is resonating frequency. It goes there, and then that nuclei will spin around that. Then you put it up, then you go back. So to flip it for 90 degree, you have to give pulse for certain time. So you give, that's called pulse width. You give for 10 microsecond or 5 microsecond. So 10 microseconds corresponds to 90 degree pulse. So you get into XY plane, and then after that you put the pulse up, and then those spins will go back. So then you get free induction decay. And that's the time your detector is on. In X, if you put x-axis, in x-axis detector is on. That is recording signal. You can put two detectors, one in Y, one in X, or you can put the Y-axis, so you can get dispersive signal. You do not want dispersive signal because you want more absorptive signal. So then you get the signal x-axis, and then you do Fourier transform. No, you get the analog. Then you have to convert to digital. So you have an analog to digital converter, which will convert to digital, and then you do Fourier transform, you get the peak. Okay, is clear to all of you? Now you are doing only one scan. As I told in the morning, if you need to increase the signal to noise ratio to get better quality, so you have to do multiple times. Okay, 64 scan, 128 scan. So you have to do many scans. So then you can get better signal. Okay, so for that means you have to repeat the same cycle multiple times, same pulse sequence. So that means, so how much time you will put for each sequence, each pulse? How much time? Okay, that depends on how the pulse width plus acquisition time plus delay. Okay, so this point is clear. So basically, you first you delay for some time, and then give pulse for short time, and then acquire the signal. But you don't wait till you don't put the detector on during this time, or you do not put detector on here also. I'll tell you why. You can record the signal only for certain time. After that, put the detector off. You don't record, because if you take the acquisition for long time, you can accumulate a lot of noise. And if you record acquire data for short time, you lose some signal. Is it clear? So that means you have to choose the acquisition time, how long you should wait. Okay, this one is clear. So basically, this is very important. Sometimes to be more safe, don't take too much acquisition time. You can get a lot of noise, and don't go too short. Then you lose some signal. You have to make something here, and sometimes people can do zero filling also. You do just to be safe, signal to get better quality. You can just take some up to this much, and then do the zero filling, so that you can have a nice FID. Okay, it's clear to all of you. So which will be clear. So in next few slides. So basically, this is the applied magnetic field. This is spin is precessing. Normal situation in the applied magnetic field. You give 90 degree pulse. For the 90 degree pulse, you basically apply the RF for 10 microsecond transmitter. Okay, so basically you get in XY plane. Okay, 90 degree. And then if you want to do 45 degree pulse, then you have to do 5 microsecond. It will not go there. It will go some halfway. Okay. Okay, many people also use a 45 degree pulse also for 1D NMR. I'll tell you why. Okay. So acquisition time is very important, that this part, because it's very important parameter. You cannot go for too much long, you get noise. You cannot go too short, you lose signal. So you have to choose how much you should wait, how long. Usually you should wait around the time of relaxation time. Okay, so that is kind of corresponding to relaxation time. So based on that, you can get some idea. Okay. Now, if you have in a sample, you have like hundreds of protons. You do not know relaxation time for each of them. You can get some idea. So what to do basically? So in that case, actually, if you use 45-degree pulse. I'll tell you that soon. So that sometimes that's better to use 45-degree pulse and then acquire the signal, which will be clear here. So what have I said? The decaying sine waves represents this process free, okay, which is a lot of, okay. The time it takes to acquire signal, the most nuclear interest, okay, yeah. So it's about 10 to, okay, 0.1 to 10 seconds, okay. That's the relaxation time, most of them, okay. And one of the most important concepts that chemists should learn, okay, question, primary goal. Natural to increase the acquisition time to maximize the amount, okay, to safe limit. However, increasing the acquisition time is only advantage up to a point. More it will determine what do I say? Because you get a lot of noise also, right? And if you have too little, also too long, and you will acquire noise unnecessarily. Too short, you basically lose some signals, right? So basically, approximately you can get some number which will be basically close to your relaxation time actually, okay. And I think it's written here, or maybe next slide I'll talk. Number of points. Okay, so as I said that you get analog to digital. How many points you are reaching, right? Now you don't get this kind of line. If you look at the Fourier things, you don't get signal. You just look at the record the points. Okay, how many points you are recording? Right? Number of points. So more number of points is better actually, right? You get better resolution. So that is another important parameter. So acquisition time important parameter. Okay, and then second one is number of points. So okay, in a tiny analog signal emitted from the sample, amplified, mixed, filter, whatever, and prior to digitization, and then you digitize using analog to digital converter, ADC. Okay, converts the analog FID into a series of discrete points along the FID signal envelope. That's why it's saying that here. Okay, and then you do Fourier transform. This is the number of points, NP. In general, the more points used to define the FID, the higher resolution, the number of points. So usually that's very important parameter. How many points you should use it, and there's equation you can use that to determine number of points. This is clear to all of you. Acquisition time has to optimize. Usually you take 0.1 to 10 seconds in that area, okay, and then number of points. How many number of points you want to acquire? If you take less points, then you have poor resolution, okay. So that will decide how to decide number of points, okay. So spectral width. So here actually we are using spectral width. If you use 300 megahertz NMR for 1 to 10 ppm, your spectral width is about 300,000 hertz. We talk in the morning. If you have 500 megahertz NMR, you use this spectral width, which is 5,000 megahertz, 5,000 hertz. We talk in the morning, right? Okay. So we talk that in the morning. Okay. So basically, for 300 megahertz, actually 1 ppm corresponds to 300 hertz. For 500 megahertz, 1 ppm corresponds to 500 hertz. Okay. So it's clear to all of you. Okay. This we already talk in the morning. So now spectral width and number of data points and acquisition time are related by the equation. Acquisition time equal to number of points divided by 2 into spectral. This is the equation. So then what will be resolution? Resolution will be equal to digital. This is digital resolution. Okay, is equal to 1 by acquisition time. Now put this thing here, which will be 2SW by data points. It's clear. And from there you can find what is the number of data points. So which is shown here. Let's go step by step here. So okay. 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 So we have to give number of data points will be 2SW by resolution. Okay. So what is the resolution you want to use? number of data points will be 2SW by resolution. So what is the resolution which is shown here? For example, if your peak width at half height, which Lorentzian peak width is 0.5 hertz, 0.5 hertz. That peak I showed in the morning, if width is 0.5, your resolution has to be, what should be a resolution? Less than that, right? Okay. So the resolution should be less than half. I told in the morning, right? So half of that will be resolution. Okay. So that means this is the whole width. Half of it will be 0.25, and then less than that. Therefore, if your spectrometer frequency is 500 megahertz or 900 megahertz, your total spectral width is 5,000 hertz. We talk about this. Okay, we talk about that. If you record proton NMR spectrum 0 to 1, this comes to 5,000 hertz. We talked in the morning, right? And for 900 megahertz, it should be 9,000 hertz. Okay, so that way you got spectral width actually 5,000 hertz. If you consider 10 ppm, if you consider 1 to 14 ppm, this will be more actually, right? Which will be how much? It will be little more. Okay, so it will be kind of 7,500, right? You know how to got 7,500 because 500 hertz multiplied by 15 makes you 7,500 hertz. Okay, and your required digitalization is less than this, but let's put this on 0.25. Less than, it should be less than that digitalization, right? 0.25 hertz per point. Okay, rearranging the equation 2, this one gives you the minimum number of points. So basically, what you can do, you can put NP equal to 2SW by resolution. So spectral width for 10 ppm will be 5,000, right? 5,000 to 2 will be 10,000. Divided by resolution will be 0.25 hertz. Okay, let's put that how much coming to be. So we get 2SW 2 into 5,000 hertz for 10 ppm, and resolution we are putting 0.25 hertz per point. You get 40,000 points. And when you set up this thing, you don't go by, you have to go near number like 64 or 32,000. That's how you should go. So because if you go to 32,000, you are decreasing the resolution. You should go high number actually. So which is because you don't go like 43,000. So you have to go by 8,000, 16,000, 32,000, 64,000, 128,000. That's how you should go. Now this number actually, if it is, you can go either 32,000 or 64,000, but going 32,000 you are decreasing resolution, so you should go to next number. Okay, whatever I say that is written here actually. Okay, so you can see that since the computer works most efficiently if the number of point is a power of 2, the closest larger power of 2 would be automatically be used, which in this case is 65,536 points. So the spectral width, number of points, and acquisition time can be specified when operating the spectrometer, usually by typing the appropriate mnemonic followed by an equal sign and the numeric value. So you set up 64,000. Okay, it's clear. And the spectrometer will set the units automatically. Generally, variance. Okay, these are all instruments. Okay, it's clear to all of you. So that's how you check the data point. So basically, you take your resolution less than 0.25 hertz per point. Okay, and if it's 500 megahertz, you should basically get this number. You should set up 64,000 data points. If you are using 1 to 10 ppm, if you are using 1 to 15 ppm, then number will be changed. If you do 15, that means this is going up. So this number also going up. That time you may have to go to 128,000 data points. Is clear to all of you? So these are the parameters actually you should consider when you are setting the experiment. So number of data points, spectral width, if you and resolution. These are very important things you should consider. Okay, and acquisition time. So basically, okay, so total how much delay, recycle delay. So if you have to do, let's go back to this pulse sequence. So basically, how much delay you should give before doing next one? Okay, so it should be 5 times of the relaxation time. So you have to make sure whole magnetism has gone back. You have to, even though you don't acquire data for that long time, but you should give enough time so that whole magnetism has gone back to equilibrium. So that should be 5 times the relaxation time. It's clear? And then see whether you can get the magnetism back to original one. Okay, so which is shown here in this slide. So then, okay, which is, so basically 5 times T1, which is basically Z magnetism will be 1 minus E elapsed time by T1, okay? And elapsed time is basically 5 times T1. So 5 and T1 got cancelled. So you have 1 minus the 5, which is basically 0.99326, okay? So that means elapsed time will be 5 times T1. Then you almost get it back to close to equilibrium value, right? That's the place you start, 0.99326, okay? If a pulse is less than 90 degrees, the total time can be proportionally less. And intensity distortion due to differential reaction effects can be minimized. This is the point I was telling actually. So here actually getting back. Now when you are doing actually, sometimes actually a lot of spin can be distorted also if you have 90 degree. But if you do 45, you will minimize the distortion of spin relaxation. So people use 45 degree pulse. Okay, so it's, which is written here. So this is one reason why the standard pulse width for 1D NMR experiments are in the range of 25 to 45 dB, right? Because that will basically minimize the differential relaxation effect. Because when I do 90, right? So then a lot of things problem, because how long you have to wait, you don't know, right? So some spins can be still there. Some can go to 1, some cannot still go to 1. Okay? But if you do some here, that is better actually. Yeah? You can minimize that spin relaxation distortions, right? Is clear to all of you? So the total time for each scan will be pulse width, acquisition time, and delay time. Okay? Okay, so this total time. Now if you look at this acquisition time is in the order of seconds. Delay time also will be order of seconds. And this pulse width is in the order of microsecond. So it's a huge difference. So therefore you can ignore this term is very, very small with respect to other terms. So the total time should be acquisition time plus delay time. Okay? So how much coming to be? So a few seconds, right? Like 10 to 15 seconds to scan one. If you do 100 you take how many seconds? 1000 seconds. So how long does it take? About like 10 to 15 minutes, right? That's maximum. If you don't have to do 100 scans. 50 or 64 scans will be fine. So in 5 to 10 minutes, you can get whole spectrum, right? With so many scan, high sensitivity, right? And if you want to do same thing for CW, so much time will take, right? So see how much revolution, okay? Whole things, it's a big thing happen, right? So that's why pulse, so basically say 600 megahertz or 900 megahertz proton FT NMR, pulse NMR, right? That's the pulse NMR. Okay, it's clear to all of you? Okay, so basically the optimal recycle delay can be computed by rearranging this thing. This is recycle delay, total time minus acquisition time. Okay, and as I said that where TT, total time is equal to 5 times, that is relaxation time. Okay, so must be at least 3 seconds to completely avoid relaxation based on distortion of the signal intensity, because must be at least 3 seconds. This one, and the total time. And T1 is 600. So 600 multiply by 5, so 3 seconds. Okay, so you want to make sure everything coming back. That's why you give 5 times relaxation time. Okay, so you do get minimum distortion, or you do 45 degree pulse, because this will go better, right? This will take longer time. Is clear to all of you? Okay, and this part I will talk. So how do modern NMR? So whatever I talk in the morning, electromagnet, okay, and that's how you get high magnetic field. In earlier days, people used to use the magnetic pole to do the experiment. Okay, that's how everything always start like that, right? Okay. And now we'll talk about relaxation. So how many ways you can relax actually? So you excite it and it goes to equilibrium, and you look at the FID decay. Now this relaxation path is very important. Okay. So how is getting relaxed actually? So let's talk about that. So there are two different ways you can relax. Okay, you have longitudinal spin lattice relaxation, transverse spin relaxation. Okay, in T1 relaxation, energy is transferred to the molecular framework, the lattice. Okay, molecular framework, as I call spin lattice, and is lost as vibrational or translational energy. Okay, the half life for this process is called the spin lattice relaxation time. Okay, and okay, let me check one thing. So you know, if you go back to the again fast order reaction, what will be the half life? By k. K is basically 1 by T. So yeah, 0.693 multiplied by the relaxation time. Is clear? Distributing the energy of NMR transition, which are tiny compared to the thermal energy of the sample, because I said the gap is small, right? Okay, so it's very tiny. Into the sample should not be a problem, but the process how it is getting transferred, that's the thing you have to consider. However, T1 values are often long, means slow relaxation, right? The problem arises not in where to send the excess energy, but the pathway along which the energy is released. Okay, which path is going, right? To the lattice. Contributing factors to this type of relaxation are temperature. Okay, if you increase temperature, you basically affect this thing, vibrational transitional energy loss, that path, right? Okay, if you increase temperature, also viscosity. Again, it's basically molecular framework, right? If you increase the viscosity, molecule is tumbling slowly. Okay, then spin lattice relaxation also will be affected. If you increase temperature, molecule will tumble very fast. Correlation time will accurately change. If your molecule tumble very fast, what happens to correlation time? Yes, next to you have some question, you are smiling or something? Okay, okay. So basically, if molecule basically tumbling very fast, okay, the correlation time will be also affected. So therefore, solution viscosity also has effect on that spin lattice relaxation. And structure, if molecule is too big, it tumbles slowly, correlation time will be different, and then relaxation, spin lattice relaxation will be also affected. Okay, is clear to all of you? And the molecular size, structure size. If you look at the big protein molecule or DNA molecule, if a single stranded DNA or duplex or triplex or quadruplex, that structure also plays very important role. If it's a beta chain structure or alpha helical structure, that also plays role on T1, spin lattice relaxation. Is clear to all of you? Now second one is not within the molecular framework. Second one is spin, transverse relaxation. Okay. Any question on this part, T1? Okay. Any question on T1? Okay. So basically T1 is controlled by temperature, solution viscosity, structure of the molecule, and size of the molecule. Okay, because that is basically dictate a lot about the molecular framework. Okay. Now transverse relaxation energy is transferred to a neighboring nucleus. Okay, this is just a spin. The half life for this process is called the spin relaxation time, or T2, or transverse relaxation, longitudinal and transverse relaxation. This process exchanges the spin of nucleus A with the spin of nucleus B. Mi goes from minus half to plus half, as B goes from plus half to minus half. One is relaxing, other is basically exciting. That's a spin relaxation, right? Therefore, there is no net change in spin for this process. Okay, one goes up, other goes down, no net change, right? Inhomogeneity of the magnetic field. Inhomogeneity, that's why you have to seem to make sure your field is homogeneous, or the presence of paramagnetic material which has lone pair electron, okay, that can also spin, that will have also magnetic moment, and this also has nucleus magnetic moment, that also spin relaxation can go on, right? That will basically promote the relaxation, therefore T2 will be small, line will be broad. So if you have parametric substance in the, or if you have the magnetic inhomogeneity, you promote the spin relaxation, that means T2 goes down, line becomes broad, because line width is inversely proportional to T2. T1 also contributes to that, okay, both T1 and T2. Okay, so that's why before starting NMR, you make sure your field is highly homogeneous. You sim it, and then look at the signal of water, make it very narrow. That's how you can do it, right? Okay, so this part is done. Okay. Okay, so okay, the peak width in an NMR spectrum are inversely proportional to the lifetime due to the Heisenberg's association principle and depend on both T1 and T2. What I talk is right. For most organic solution, T1 T2 are long enough to result in spectra with sharp lines. For most organic solution, T1 and T2 are large enough, okay, because they are relaxing slowly for organic molecules. And they relax slowly, that means line width will be inversely proportional to long T1 T2, line will be most sharp. Okay. However, magnetic field homogeneity is poor, or parametric material such as iron is present, the NMR signal can be broadened to the extent that the signal is destroyed or unusable. Okay. So that means if you don't sim very well, that means you are recording spectrum of your sample, within the NMR sample tube, there is a lot of inhomogeneity. That will broaden line, you won't see signal, oh, then you get frustrated. Now you give the sample to some expert person, technician, that person see the signal. Because the only trick that you did not sim the magnet very well, you had a lot of inhomogeneity in your sample, other person did not have. That's why other person got very, very good signal. So this is recording NMR depends on the how good you sim the magnet to get the uniform magnetic field within the sample. Is clear to you? Or if you have some iron parametric substance, that also can broaden your line also. Okay. Okay. So what is time? We can have now 3:56. What do we have? 3 now, right? Okay. So before I start, do you have any question? Okay. So let me just start. We have 4 minutes. Let me start another slide. Then we can go for T. Okay, fine. Okay. So before we do 2D NMR, we'll just do a few things. We'll talk another phenomenon called NOG, and then we'll get to 2D NMR. Okay. So in the morning, let's skip a few things and then we'll come back again. Okay. So in the morning, we talk actually the coupling of two spin through bond, spin coupling through bond, and that is called J coupling or scalar coupling. Okay. And in that coupling, you got a splitting of the band. Now there is also spin can also interact with each other through space, and that interaction is through dipole-dipole interaction. In case of J coupling, nuclear spin polarizes electron spin in the bond, that plus the next bond into spin, and then polarization is transferred to this spin. So that's why it is a 2 bond or 3 bond. You cannot go further actually. Right? But in this case, if you have two spin are very close, they do not have to be next to each other, or they do not have to be connected by 2 or 3 bonds. They can be far away, but protein or DNA got some structure, these two proton came very close within 5 Armstrong. And then they can undergo dipole-dipole interaction, because as we discussed yesterday, that if you have a nuclei with spin, we will have magnetic dipole, because spinning and generating the magnetic field, which is magnetic dipole. So two magnetic dipole coming close, they have dipole-dipole interaction, right? Is clear? So that interaction will be causing nuclear Husserl effect. Now we will discuss what is the molecular basis for this, okay? How they come close and what are the factors playing nuclear Husserl effect. In this situation, if you basically saturate this signal will either go up or go down. So you have two spin, they are coupled through space via dipole interaction. Okay? Now if you basically saturate the spin, this signal can go up or go down. If that is the case, that means these two protons or nuclei are interacting through space via dipole-dipole interaction, and they are within 5 Armstrong or so. Is clear to all of you? So that's the NOG. Now we look at the molecular insight of that NOG. Okay, so what we said that is a dipolar coupling, intermolecular distance and molecular motions. Okay, intermolecular. They can be on same molecule or different molecule. If they are different molecule, they have to stay together, because they are tumbling, you won't be able to catch it, as I told, because then that will develop the fluctuating field. Is clear? So basically, we will be talking that later. Let's talk about some of the background, then we'll get back to this more. Okay. So let's say you have two spin, homonuclear spin. Then we'll talk about heteronuclear. Okay, two homonuclear, okay, proton with proton. Okay, the two spin half nuclei I and S in the same molecule, and their coupling constant is 0. That means they are not undergoing spin-spin coupling through bond. They are basically far apart, but they came close. That's why they don't have J coupling or scalar coupling, but they can have dipole-dipole coupling if they are close. So let's see what is going on here. So now, if they have dipole coupling, you can have also same thing, alpha from first spin and alpha from second spin, then alpha from first spin, beta from second spin, beta from first spin, alpha exactly same way, and then beta. You have 4 states. Okay. Now look at the population. So, like not, you just assume that you have population n here. That means you have more than n here, and you have less than n here, right? We discussed that the energies are all same, right? So let's say you have n here. That means you have more here. Let's say n plus delta, and you have less here. Let's say n minus delta. This is just for, these are like for discussion. Okay, so it's clear to all of you. Now, if you saturate this signal, this S, then how that will affect the intensity of this signal? Okay, if you saturate this, if the intensities are increase or decrease, that means these two spins are coupled by this network, right? Right, because this we got this framework only when they are interacting through space via dipole interaction. Then you can have network. And in that network, if you saturate this signal, and then this intensity will be changing actually, right? If this changes, that means that these two spins are held together by this network. If you don't see any change, that means this type of network did not form between these two spins, right? Is clear to you? That's the logic we'll be using to understand NOE. Okay, T has come, right? Okay, maybe they are waiting for T. We can continue after T. Okay, here, right? Okay. Okay. Cellular metabolism. So what we did actually, after lunch, actually we have used one of the tutorial time to teach NMR, and so that tutorial will be pushed to tomorrow, and then we have to do one more tutorial today. So tutorial 1, and then I thought of doing some more NMR today. Then based on your request from you people, so what I am deciding that I will continue NMR in the morning. All the theory will be done before lunch tomorrow morning, and after lunch during tutorial time we'll be do data analysis. We'll pick up DNA, how to analyze DNA structure based on NMR data, how to do peptide, protein, and cellular metabolism. So all the tutorials will be afternoon time, and during that time we can do all analysis of protein, DNA, NMR, peptide, and cellular metabolisms. We can do in the afternoon, and then after that, if you have some time, we can look at the other applications of NMR. If not, we can do on Saturday. Saturday, I think you have 1 hour time. So we have tomorrow. It will be a bit lengthy day tomorrow. Okay. So we'll start in the morning 10:30. We'll finish by 1:30. Finish all the theory part. Then and we may meet a little early. So 3 o'clock we may meet a little early, maybe 2:30, and we can start doing as much as possible analysis. And try to finish most of it by tomorrow, and then after that, if you have time, we can do application. If not, we can do on Saturday application like MRI, solid state NMR, and few other applications. Okay, so that's how we will do. So today actually we have to do tutorial then. So tutorial actually, the tutorial 1, if you look at that outline, is focused on gene regulation, chromatin structure, okay, and clarifying concept. So what I think that actually, because we talk so many techniques, so many things, so maybe we can pick up some of the things actually. We can discuss more technically how things are done technically, maybe, and how to design experiments in those areas, and how to analyze the data. That could be the better way to do. Okay. So do you have any specific things to discuss? We can pick up that first, and then I can talk what I think may be appropriate for you to clarify the concepts. Now those will be tutorial. Now they will be coming for tutorial 2, 3, 4. So you have total 4 tutorial. First tutorial will be based on gene regulation, metabolism, okay, chromatin structure, and how to analyze, how to design the experiment, do the experiment, and how to analyze the data. So do you have any things to discuss in specifically? Then I can talk that, and then I can fill up something and add something on top of it. No? Okay. Nothing, right? Okay. Or do you want me to? Okay. Okay. So let's say how will you design an experiment? Say suppose how will you design an experiment to determine whether the gene is expressed or not? How will you design the experiment? Or whether a protein is expressed or not? Okay. 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 How about others? Okay. Okay. Any other answer? Okay. Now, okay, there are 2 questions. How will you analyze the gene is transcribed or not? You can look at the RNA level, and also look at the gene expression to protein. You can look at the protein level. So now you are answering the how to detect protein level. Okay, the one answer was that you can tag the protein and see in the confocal microscope to see the protein is expressed or not. And then another answer that you can run the gel. Okay. Yeah, you can detect and then you can quantify. So these are the answers from you. But so usually, classically, this is a very old technique known as Western blot, right? You basically make the whole cell extract. Okay, let me just show schematically here. Actually, we can. Okay. So you have a cell, okay, and you have so many genes, and you have another cell. So many genes are there, right? So this is cell A, this is cell two different cell types. Say you took cell say from liver, one cell from heart, okay, and then we want to see whether the gene, particular gene, say this gene is a G, this gene is G, whether it is expressed or not. You will check it. How will you check it? So you took liver, whether the gene is expressed or not. The question is basically you took the liver, you took the heart muscle cell, and you want to check whether this particular gene is expressed in this cell or in both cells. So you have done in the whole lecture that gene expression means gene is expressed to what? Gene is expressed to? No, in the whole learning, what do you learn? Gene is, we spend so much of time to understand which process? Transcription. So gene is transcribed to what? Yeah, what RNA? If you do RNA pol 2, so this is the RNA pol 2 genes. RNA polymerase 2 regulated genes. So what will get from here? Which RNA? mRNA or G. Here, if this is not expressed, you won't see anything, right? Okay. In this cell, this is liver cell, let's say heart cell. So in this case, you get mRNA. Here, you won't be expressed, or it can also express. Then, how will you detect this mRNA? Southern blot. Okay. Okay, loudly. Yeah. What is there? Poly is there. So there is a poly is there at the end. Okay. Chromatography. Chromatography uses Southern blot, and how do you? And backside you are saying that clone it. Okay. Yeah, PCR and clone it. No. Which one? You basically clone it, amplify, run a gel. So will that tell you whether gene is expressed or not?
If gene is expressed, then ultimately protein should do it.
And I get the question first. Question is basically whether you are making RNA from this gene or not. Okay, RNA is making RNA from this gene or not. Answer 1, you said that you clone this thing, do PCR. Will that say whether the gene is expressed? You basically clone the gene and do PCR and clone it. Will that tell the gene is expressed? No. Now you are saying that Southern blot. Southern blot basically, what is Southern blot? Southern is basically for DNA. What? Okay, Northern blot. Okay, Northern blot. And then third thing you are saying that, okay, we'll get to Northern blot. We'll discuss. And third thing you are saying that, both of you are saying that you have a poly A tail, and then you do something, chromatography, and you said something. You said chromatography, right? And you said something.
Adenine is there, so we can check the pH here, simple experiment if we want to do. So it will be more basic.
Okay.
Or we can check for the presence of adenine.
Okay. How will you check for the presence? Because this kind of adenine presence will be found in all mRNAs. How do you know this mRNA is coming from this gene? Because this part is from this gene. This is basically from coding sequence. This poly A tail is for all mRNA. So if you check that, you know that mRNA is there. But how will you know that this mRNA corresponds to this gene? How will you know that? RNA sequencing. Okay. Okay. So by putting pieces from different answers, yeah, we are getting something. We are getting in the direction. Now I will just flash it out so that your concept gets clear. Okay. So basically, what you do after that, you have here RNA. You basically lyse the cell. Okay. lyse cell. Once you lyse the cell, what happens? So all mRNA, this part is different, then you have poly A tail, all mRNA will be A. Okay. Okay, they will all come out, right? Okay. Now what you do? What is the thing?
एक question है इससे जुड़ा नहीं है but इस topic से कि why adenine is used for
Okay, same question he asked here. He is doing quadruplex. Okay. Okay.
there are other nucleotides also in the cell. Why cell is using adenine? Why specific preference for adenine?
Okay.
And same is the case if there is a capping
Yeah.
for capping. C and yeah.
G. Yeah.
Why these two nucleotides are specific?
Okay.
for this
Okay. So there are two things actually. Number one, that this basically this is a chemical reaction. This chemical reaction is catalyzed by enzyme poly A polymerase. That enzyme is there. Cell produce the enzyme that's catalyze. And for capping, you are putting you have to put guanine. So that reaction is catalyzed by guananyl transferase. Cell has their enzymes. Okay.
दूसरे enzymes नहीं होते ऐसा तो नहीं होता कि कहीं कुछ fractions में
No, but that means if you have the enzyme, that means you should have that gene actually. We should have cytosine transferase, guanylyl cytosine transferase, or that kind of transferase to be there to put it there, right? You should also have poly T polymerase has to be there, right? Yeah, so that has to be there actually. So that means that gene has to be there, that gene has to be expressed, and then you can think of those, right? Okay.
it happens during evolution, during the molecular evolution. This type of things must have happened during evolution.
Yeah, because I think you are not. We discussed so many things. Our whole body is so nicely made. If you are in trouble, our body try to compensate, right? We discussed a lot of examples yesterday, right? Okay. Is clear? So let us have some idea here. How technically how do you study gene regulation? So you have to detect this mRNA. How detect it? One way is northern blot. Other way basically take the advantage of poly A, but chromatography and other part actually not may not be right, may not be more advantageous. Okay, we can do it, but we can better. We can do little more quick way. We can do that thing. So let's talk about the take the advantage of poly A. So what you do? You have RNA. You do oligo DT. You take a oligo DT, TTT oligo DT. This kind of oligo DT you can buy commercially. So make wholesale extract, put the oligo DT, that will go. This part is one gene, a G. This is coming from different gene K. Okay, this one is coming from different gene L. Is clear? So what you do? You put oligo DT, which is about 50 nucleotides long, and that will go and bind to all of them, all RNAs. And they have this 3' and 3' OH. Is clear? Now your template is RNA. Now you want to make cDNA. So you are using template RNA. You have to make cDNA. So you put nucleotide ATGC. It will basically put the nucleotide. This is a chemical reaction, and you have to catalyze this chemical reaction by some enzyme. What will be the enzyme name? Reverse transcriptase, which use RNA as a template and makes DNA. Okay. So basically you make this, you just copy this RNA, copy this RNA, copy this. So basically you make the DNA. This is known as cDNA, complementary DNA. This complementary DNA does not have introns because this mRNA is already processed. So cDNA does not have intron. So you get how many cDNA? You get cDNA for all different mRNAs. Okay. So you also got, if G is expressed, you will have cDNA for gene G. Right? If G is not expressed, you won't have this cDNA. Okay, clear to you? Now you know the sequence of G. You know the sequence of G. So you design the primer, 2 primers, which will go and use this as a template. Is clear? And then you do PCR. By PCR, you can amplify the cDNA and run the gel. So PCR using the primer pairs, which is specific to the coding sequence of gene G. So that way you can amplify the cDNA and you get the, this is basically corresponds to the fragment of gene G. Okay, it's clear to all of you? And then you run gel, say agar gel, run agar gel, load this sample, and says the size say 300 base pairs. You can see the band of 300 base pair here. Okay, if you see this band, that means that G has been expressed to corresponding mRNA, which was converted to cDNA by the help of reverse transcriptase, and then cDNA got amplified by using primer pairs specific to the G coding sequence, and you run the gel, you get this band. If you see this band, that means this gene is expressed. Now you make a wholesale extract from, but you did not amplify these genes because you have used the primer specific for this. This mRNA coming from some other gene, so therefore it won't be amplified. Will it be amplified? Will this be amplified by this primer?
We will be taking primers according to the end sequences of G.
Yeah, because you want to see whether G is expressed or not.
But sir, what if the G gene contains intron on both sides, which have already been removed?
Now that's why you have to take from exon. This primer has to be from exons. Okay, because this mRNA is already processed. There is no introns, so these primers have to be located on exons.
Before conducting this experiment, the experimenter must know the sequence of the genes.
Yeah.
This is the
Yeah.
essential condition.
Yeah, essential condition for this, because you must know the sequence of the genes. Okay, and then you can do this thing. Okay, if you don't know the sequence of the genes, then what he said that do sequencing. Okay, RNA sequencing you can do. Okay, but that is actually expensive process. If you know the gene, you can quickly test it. This whole thing will not take a day. Basically day. Actually, you make the cell, grow the cell, lyse the cell next day, and then you get the RNA, put oligonucleotide and DNA reverse transcriptase, you get the cDNA template. PCR amplify using primer pairs specific to the gene G, basically coding sequence or exons, and then you get PCR product, run on gel, you see the band, the gene is expressed. Okay, and you do same thing from here. If you see the band, that means that this gene is basically expressed in both cell types. If you don't see the band, you can say that this gene is expressed here only, not here. In cancer cells, some gene is overexpressed, right? Okay, so you can take the cancer cell and normal cell. This normal cell, let's say cancer cell, here this gene is overexpressed. So in this cell, you can see very strong band. Okay, or in cancer cell, this gene is not expressed. You won't see signal here, right? Is clear to all of you? Okay, now here actually you are taking targeted approach. You are taking targeted approach. Now suppose you are taking some 2 cells, one is a normal cell, one is disease cell. And how many genes are up and down? Can you do this approach? Suppose you have a 2 cell, one is normal cell, one is cancerous cell. So we want to know how many genes have been upregulated, how many genes are downregulated in cancerous cell. How will you do this thing? Will you look at each and every gene like this? Because there are 30,000 genes, okay, in this cell. So are you going to do same thing for 30,000 genes like that? 30,000. Microarray had a problem we discussed the other day, right? Microarray is very good technique. It was like in late 90s, early 2000, but we also discussed that other day. That technique has a lot of other problems, right? That's why new technique was developed. What is the new technique? But how will you do cryo microscopy to look for expression of 30,000 genes? Cryo-EM does only structure, right? You want to see how, because this cell expresses 30,000 genes. Now this cell has cancer. That means this cell is not expressing all 30,000 genes. So some are upregulated, some are downregulated. So that means some RNA is going up, some RNA is going down. So what technique will you use? RT-PCR you did here, reverse transcripted PCR you did when you know the gene. But here actually, yeah, you know the genome sequence, you know genes, you have 30,000 genes. So are you going to do same thing RT-PCR for all 30,000 genes? You cannot, you can do, it's very laborious, right? Why? To do that you have to do 30,000 PCR and you have to buy 30,000 primers. Okay. So one of your colleague already said this thing, you do RNA sequencing, and we discussed the RNA-seq when you're discussing gene expression. That time we discussed RNA-seq, right? You get the RNA, all the RNAs you get, you sequence them. Yeah, that's a very hot technique we discussed, right? You basically get all RNA from here, all RNA from here, and sequence them. So by sequencing, how many RNAs are present here, how many are not present here, that we can find out, right? How many are up and down, RNA-seq analysis. Okay, which is very, very good way you look at the transcript going up and down, right? Okay. So now let's get to this. If you look at the selective gene, you can do RT-PCR, number one. Number two, you can do northern blot. That is also you people told northern blot. So basically you get the mRNA, this sequence, plus poly-A tail, right? Now also you get many other mRNA. Many other mRNA. Now we have to check by northern blot that this RNA is getting expressed or not. So what you do, you get all the RNAs mixture. You lyse the cell, make the whole cell extract, isolate the mRNA or all RNA, and run on gel. So different size of mRNA or RNA will run differently. Then transfer on the nitrocellulose membrane. That transfer is known as what is the transfer called? You transfer all, you just run the RNA, and then on top of that you put nitrocellulose membrane and transfer this RNA from gel to the membrane. That process is known as blotting. What is the name of blotting? Yeah, that's a blotting. What is? Yeah, you don't know. Now you are complimenting. Okay, so northern blot. So by doing northern blot, you get everything on the paper. Okay, but these bands you don't see by your eye. Okay, then what you do, you basically take the multiple fragments, make the oligos which complements this sequence G, and then label those oligos by radioactive phosphorus. Okay, then put that probe, first wash and put that probe here. So this radioactive probe will go and bind where? All of them? Yeah, that means the complementary sequence is basically this one, G, right? So let's say this is G. So it will go and bind here, right? Not anywhere else, right? Because the complementary sequence is here. Okay? Then you wash the probe and then put it under visualizer or under dual document system, or put the X-ray film, put X-ray film, and then this radioactive light will hit the X-ray film and then develop the film. What you will see? You will see what do you see in this location? Yeah, spot you see, right? Okay, if you see this spot, that means this gene was expressed. So you could see this process is known as northern blot. Okay. Now northern blot actually is done this way. Now, if you do northern blot and the earlier was RT-PCR, which is faster? Which one is faster? Faster. And northern blot, which one is faster? Faster. And which could be more sensitive? Yeah, because you are amplifying by PCR 1000-fold, right? Okay, so that is more sensitive, right? Here actually you have to transfer, okay, and then hybridization. Do you think you get 100% hybridization? Okay, so there are a lot of things not right, but definitely northern blot is better than another technique I am going to talk, primary extension. Is clear to you? So how many different ways you can analyze the expression of gene? Okay. So number one, you can do RT-PCR. Number two, you can do northern blot. Number three is primary extension. These are all gene selective. We will go and talk how you do primary extension. The number and global, if you do genome-wide, people used to do DNA microarray sometime back. That's how genome-wide expression analysis was done. We discussed in that I think day one, and that has a lot of problems. That's why now people are doing RNA-seq analysis, RNA sequencing, and finding global genome-wide. Is clear? So let us talk another technique by which also you can see whether gene is expressed or not. So basically you got this RNA. This is gene G, and also you have another, so you have mixture of mRNA. You have, say this is A RNA, you have another RNA, so Y. Now you want to see whether G is expressed. So what you do, you put a primer which complements this sequence, coding sequence, only coding sequence, and then you label this primer by radioactive P. So this is the enzyme, by use enzyme you can put radioactive P at this primer. Then extend the primer putting reverse transcriptase. Reverse transcriptase will copy, this is the DNA primer, DNA. This is RNA. Put reverse transcriptase, that will basically copy this thing and make DNA from RNA. So basically that way you can extend the primer. And if you can extend the primer, then the size of the, because this primer comes here and this primer will come here. If you see this band, that means primer got extended. Okay? So based on this is known as primer extension. Primer extension, because you extended the primer. If you see the primer extension, that means this RNA is there. If you don't see primer extension, this means RNA is not there. Now this primer extension is less sensitive than northern blot because it depends on the hybridization and then extension also, right? And in this case also, sometimes what happens, we have very strong secondary structure here. If you have that thing, primer may not extend. So therefore you have to put primer towards the 5' end. If you put primer here, you may not get extended primer because this RNA can form secondary structure, right? So therefore it cannot go far. So usually put primer towards the 5' end and you get the product. That means this RNA is there. But this primer will not bind here, So therefore this primer only detect a particular primer of your interest. So how many ways you can determine whether gene is transcribed to mRNA? By northern blot, by RT-PCR, by this way, okay, extension. If you can also do global genome-wide expression for all genes, do DNA microarray. Nowadays people don't use it. People use RNA sequencing or RNA-seq. Is clear to all of you?
PCR in two ways. One is the reverse transcriptase PCR that is understood. We are applying the reverse.
Yeah, there you are not doing PCR actually. The first step is basically making cDNA, that's not PCR. Second step is the PCR.
And the second step is, second technique is the real-time PCR.
Mhm.
What is the difference between these two RTs?
So these RT is reverse transcriptase, RT,
One stands for reverse transcriptase.
yeah,
And second RT stands for
real time,
real time.
yeah,
What is the real time?
okay.
साथ साथ में मतलब अगर कर रहे हैं उधर आपको रिजल्ट
Mhm. Okay, just it will give some idea.
बिल्कुल सर जैसे सर की रिकॉर्डिंग कर रही है सर और यूट्यूब पे लाइव
Okay, yeah, can. Okay. So basically in that case, if you do this kind of PCR, normal PCR, what you do, you basically take a DNA, you basically use the primer, you amplify, right? This goes and this goes, you amplify, you get amplified DNA product, right? And then you run the gel, and the DNA is here, but you cannot see by your eye. Then you put Ethereum bromide will interact with DNA, and that is become fluorophore now. You transmit by UV light, you can see the emission light. That's why you see that thing, right? Okay. Standard PCR. So you can see here actually you have to do so many things. In the real time, actually you are putting the fluorophores. That thing is already fluorescence level. So that has a detector. Okay. As PCR going on, you are detecting a signal. So first cycle signal is weak, second cycle, third cycle, fourth cycle, fifth cycle. So that's the thing live going on, right? That's a real time. So first cycle you have less because they are already labeling it by fluorophore, right? And you are looking at the fluorescence intensity. So
Fluorophores are added in the beginning of the
yeah, because here actually you are just using ATP, just ATP nucleotide mixture. The nucleotide mixtures actually you have a fluorophore actually is there. So basically, first cycle you get very small amount. Each signal is like second, third, fourth, fifth, sixth, 7, 8, 9, 10. That's why going on, right? Okay. So it's real time. Okay, that's all real time. Yeah. That's why it's a real time, right? Okay. It's clear. So now this is actually going this way, and you're going this way. This is a quantity because you get everything quantitatively, numbers coming out. Okay. And here you see, and then you can basically make sure this signal is not saturated. Here there is no question of saturation because you are doing that way. Look at cycle and you can make out why it is getting saturated. Here actually you don't know how they get saturated or not. You have to basically dilute, keep on you have to do the same PCR at multiple dilution to show that you are doing PCR under a concentration which is not saturated. Okay, if it's saturated, then if you compare two signal, you will say, oh, there is no change because you are doing PCR using template which is basically saturating the signal. Okay.
standard PCR is more tedious than RT.
But you have to be careful about the saturation. If you know how these two assays are working, and you know what are the limitations of this technique, if you take care of the limitation, should be fine. Many people actually they don't know what is the basis of this; they just blindly do the experiment. Okay, but if you know the limitation, you take care of the limitations, fine. That's why people generally say, oh, it is better to use real-time PCR because many people may not know all the basics. So just blindly doing this thing, okay, putting this much template, and from 2 cells, there is no change. They are very happy. There is no change. Now, if you do dilute the samples, template, you can see huge changes coming. Okay. Now, if a layman who did this experiment did not take care of this, did not understand anything, did not take care of it, he got this result. The same layman, but here he didn't see any difference. Somebody know the limitation, that person can dilute the template, can see the difference. For now, same layman who he does this experiment using this machine, he or she can see the difference. So that's why it is safe to use for everybody, user friendly actually. Okay, you don't have to do anything. Just put the sample in machine, you get the result, right result. Here actually, you put the things in your experiment, you may get right result, may not get right result. If you are using concentration which is saturating concentration, you won't get right result. If you are using things, a layman is using less concentration get right result. So we say now in that case actually somebody knows this thing very well. So he knows that okay, when you do this thing, make sure there is no saturation. So do the same experiment at multiple different dilution, see what is going on. Okay, and as long as you take care of that, then it's fine. You don't take care, it can mislead you. That's why this technique people are using blindly, not blindly, especially very safe and quantitative. You get all the numbers from machine. Here what you do, you basically once you make sure it is done under saturation limit, then you will quantitate by program called NIT image program, and then in the program you quantitate that thing. So here you are doing all other way, multiple ways you are doing, and this is you are doing much quickly. Machine is doing for you.
जब भी कोई हमें बोले RT-PCR करिए तो पूछना पड़ेगा कि is it reverse transcriptase or real time PCR उसको बिल्कुल जब से फिर इसको क्वेश्चन तो स्टूडेंट्स हैं
Yeah. So RT is basically this RT is called reverse transcriptive PCR, otherwise real time PCR. Okay. Yeah, real yeah. Yeah, or you can say reverse transcriptive PCR and other real time. And if somebody you ask this question in the exam, better to spell the whole name rather than doing RT, because RT can say multiple things, right? Okay. So this tells you a lot actually. So we got from the first part tutorial 1, you learn how to analyze the transcript by multiple ways, northern blot, primary extension, and RT-PCR or reverse transcriptase PCR, and also you can do global genome expression analysis of mRNA by RNA sequencing, or old technique called oligo DNA microarray. Is clear? Now second part actually, once RNA that now you should look at the protein part. How we analyze protein? Suppose this gene is expressed, this gene G is expressed to mRNA, should be expressed to protein, right? How will you analyze the protein level? Analyze protein level. Whether gene is expressed to protein or not, how will you analyze? I think you mentioned in the beginning. How will you do that? So answer was you said you will run gel, and you said you will do confocal microscope. Okay, okay, yeah, yeah, Western blot. Say simple, just Western blot. Okay, so basically whether this protein is expressed or not, you just exactly the same thing that northern blot, you do Western blot. So basically you lyse the cell, everything comes out, you lyse the cell. So all the proteins, RNA, everything comes, all the proteins come out, all mixture, A protein, protein B, protein C, and protein D. You get all the proteins. And then you run the gel, okay, and all the proteins are here, you don't see them by your eye. We want to see whether protein D is present in this, we don't see by your eyes. Again, you put the membrane on that, you transfer all the proteins to the membrane, and that process is known as blotting. What is the blotting called? Western blot. Okay. So you get the membrane, and all the proteins are there, you don't see that. Then you block the membrane by milk. Milk has a lot of protein, so they will bind everywhere. After wash it, then you put the antibody against this protein. Say anti-protein D. This will go, suppose this is a protein D. This will go and bind this band. Is clear? But still you cannot see that thing, right? Then after binding you can wash it, and then you have to see that band, because you know that protein has gone and bound, is bound there, but you cannot see by your eye. Now you put secondary antibody which is linked with enzyme. Enzyme links secondary antibody. So horse redox peroxide link secondary antibody. Okay, another antibody. This will go and bind here, and then that has HRP, horse redox peroxide. This is the okay.
Some dye-linked antibody which will produce color.
Yeah, you can do that also. Yeah, you can do that. Also you can do that also either way. And then you put the substrate on this membrane. So then the substrate actually will be converted to the fluorescence product or chemiluminescence product, and then put the membrane, or you can use the gel lock system, and then you can look at the light, or you can put the X-ray film and then develop. You can see black spot there, right? If you look at the X-ray film, you will get a black spot. If you see black spot, that means protein is present here. So that's how you can look at the protein level. Is it
You know the type of protein we can also go for electrofoxing.
electro?
Foxing.
Yeah. Now here actually we are not characterizing. We want to see whether protein is there or not in the extract. Okay, it's clear. It's clear. So basically, you have to do Western blot to see whether protein is there or not. Okay. Now second thing actually, suppose you don't know which proteins are expressed. You don't know, right? Which proteins are expressed. So what will do? Okay, what is the so what is the technique called? The same year, the year NMR technique application Utrecht got Nobel Prize in 2002 or 3 for application of NMR for solving biological structure. Same year, another person got Nobel Prize for Ramachandran plot will tell you sequence of the protein. I gave the clue actually. The year Utrecht got Nobel Prize, around the same time another person got Nobel Prize for analysis of proteins. What is the analysis? MASS. Fill out the second one. Yeah. Okay. Okay. So you can sequence the protein, right? And that was a big thing in the field actually, because that's why you can pull out a complex and see what are the factors are bound to that. You don't know that. You just pull out a complex and you don't know what the proteins are bound to that. You can do sequencing of all proteins. That's why you can characterize the whole complex. A lot of complexes are discovered because of that actually, right? Mass spec analysis. It's clear to you? So you can. This is how you can detect the protein level. You can detect the expression of gene to RNA, and also you can, if you want to genome-wide RNA analysis, you can do RNA-seq. If you pull out, if you want to identify new proteins, you just sequence it. Okay, how? Mass spec analysis, right? Is clear? So you have also learned what is northern blot, also western blot, and also there is southern blot. Suppose there is some gene is knocked out, can be sometimes some gene can be completely knocked out. So you can basically take a normal cell and mutant cell and just look for the gene. So basically make the DNA and transfer the DNA on the membrane, and that process is called southern blot, right? Okay. So then you can do hybridization to see if the fragment is there or not. Okay. So these are very important things when you do gene regulation thing, right?
Chromatin, sir, chromatin is a very long structure.
Mm-hmm.
Chromatin is a very long structure. And how a person can work out where a particular gene is situated?
Okay. Chromatin.
अब ये कैसे पता लगाना कि ये gene इधर मान लो इसे इतनी लंबी साइड नीला
So basically you are asking what is chromatin immunoprecipitation, right? Cheap. So let's discuss. So basically so far we talked how to analyze gene expression at the level of protein and at the level of RNA. Okay, and so we learned so many techniques. Okay, now the next question that how you will do chromatin IP assay, chromatin IP, right? So this is a chromatin. Okay, the nucleosomes, and say your protein bound somewhere here. This is the protein of your interest bound. This is the protein of your interest bound to this place. When the process is going on, the protein bound here in the living cell, and add the formaldehyde. Formaldehyde structure is What is the structure of formaldehyde? Okay, and this formaldehyde will go. What it will do? It goes into cell. What it will do? How does it cross link?
DNA to the
Okay, amino group. So it attacks amino group. Say you have a amino group in DNA. So let's say DNA has amino group. How does it attack? Who attacks whom? No, because it says that formaldehyde reacts with amino group of DNA. So how does it happen? How does it attack? How does it react? Oxygen is hydrogen, like this.
And double bond CH.
No, okay, so one question you are saying this is attacking this. Okay, this attacks this. Okay. Okay, so how nitrogen attacks the C? How does it attack? Huh? Yeah, so how nitrogen attacks carbon?
Nucleophile attack on the electron.
So because which one in nitrogen is attacking carbon? Nucleophilic attack, right?
Nucleophilic.
Okay.
Yes, sir.
Okay, so this is like this.
Yes, sir. Yes, sir. Oxide formation.
No, this is fine, but okay, go one step back. This is fine. Yeah, this is attacking. So just nitrogen attacking?
Yes, sir.
Nitrogen attacking?
Yes, sir.
Lone pair of nitrogen. Okay, it has a lone pair. Okay, that lone pair is attacking. Is attacking, and then, okay, it's clear? So basically, you can do like this, it goes attacks, and this goes attack here, and this, right? Okay, let me go step by step. So you have here. So let me show step by step. So once I attack here, so you have minus and right, because lone pair is plus, then H and H. The next step, this minus will attack here, then so I was doing all together actually, right? Okay, this tautomerism. Does it? Yeah? No, this is the one I did all to that's tautomerism. Okay, so all the things are happening not like this. All the things happening like this. This goes there, this goes there, this goes there. Okay, so I did in 2 steps. Then H, and then you have so what is the name? This is hydroxymethylene, N-hydroxymethylene. Okay, so basically if you put too much of formaldehyde, if you breathe too much of formaldehyde, what you do? You modify DNA NH2 by hydroxymethylene. These NH2 of DNA are involved in, how those involved in? No. If you breathe a lot of formaldehyde, what will happen? Your respiratory tract cells will get a lot of formaldehyde, goes to the cell, and what it will do? It will basically modify DNA by hydroxymethylene, right? All the DNA will modify by hydroxymethylene. NH2 group of DNA will be modified by hydroxymethylene, right? In this way. So if you do that thing, is it good for DNA?
No, sir.
Okay, no. So in what way it is bad? No, go step by step. You are going on step. No, before that. So it's a DNA, and you basically modify the amino group. So you modify, not cross. You didn't. So far you didn't cross link. You just modified. You didn't cross link. You just modify the DNA by hydroxymethylene. So NH2 group of DNA is involved in what? Yeah, hydrogen bonding with another base. That's why you make double strand break. So DNA is double stranded because of hydrogen bonding G with C and A3. NH2 is getting modified. If you modify that, what will happen? Huh? Yeah. Yeah.
Double helix.
It will be disturbed, right? And if you disturb that, what will happen? The DNA will be non-functional, right? You basically accept, then if DNA is non-functional, what will happen? It will be affected, and there is no protein slowly, and then no protein means cell is dying. Cancer, so many problems. That's why say formaldehyde is really bad. Okay, that's why you should not smell formaldehyde. It's very toxic. Okay.
Methanol converted into formaldehyde when people take alcohol.
No, yeah.
Having the methanol.
Yeah. Okay, we'll get that. Very good point. Yeah. So tell me, I'll get back to you. What do you say? Huh? Yeah. Yeah, it's toxic. Yeah. Yeah, if you don't make it, eventually it will kill your cell, because if you destroy the DNA double helix, you don't have transcription. You don't have, after some time you won't have protein. So forget the mutagen. So mutation in some is still okay. That gene may not be essential. You can still survive, but it is basically killing the cell actually, because transcription will be off. There is no protein. If you don't have protein, cell will not function. They will die. Right? It's a toxic. Okay, mutagenic and toxic. Okay, it's a toxic substance. Now another thing she told very nicely, that when you look at alcohol drinking, make sure there is no methanol. Ethanol gets oxidized to acetaldehyde. Acetaldehyde also can do same thing, but the moment you put CH3 here, because of Plaza effect, electropositivity goes down here because of Plaza effect. So therefore, the efficiency of this attack is down. Therefore, the efficiency of formation of this product is down. So acetaldehyde is less toxic than formaldehyde. Okay, but still it's bad. Okay. If you do propanaldehyde, further less toxic, because you are putting more Plaza effect. That means you are decreasing the electropositivity. By decreasing electropositivity, you are decreasing this transfer, so you are decreasing the modification. It's clear? But formaldehyde is very toxic. So when you have methanol in the alcohol, like lot of alcohol you get in the village or the places, they don't do good. So therefore they have lot of methanol, and they really damage their health a lot. They get a lot of liver disease also. Liver disease. So many things. So basically what is going on there, methanol gets oxidized to formaldehyde, and you modify DNA, and also you modify the protein. Protein also has thiol has lone pair, that also can get attacked. Also they have lysine, NH2, that also can get attacked. So you also not only DNA, you also modify the proteins. So it's basically very bad for your health if you have formaldehyde. Acetaldehyde is to less extent, and propanaldehyde is much less. So alcohol actually is that's why when you metabolize alcohol, and how do you, alcohol dehydration is there, right? Okay, so and then you have all the enzymes are there, and if somebody is mutation, it's not good. So if you have too much of formaldehyde, it's very bad for your health, right?
Formaldehyde also damages optic nerves.
Anything, because optic nerves basically, if you damage these cells, fine. If you damage the nerve, okay, you have long-term effect, right? So non-specific you can tell that is globally, you can tell all the proteins and DNA will be affected. Okay. Huh? What?
Retinal cells
Yeah.
get damaged.
Yeah. No, any cell will damage, but you see bigger impact because neuron cells you don't regenerate, right? So that's why it's a bigger impact. But normal cell you kill, you regenerate, right?
Is this the same phenomenon we do by fumigation? We are adding KMNO4 plus formaldehyde. So this is the same phenomenon that goes on while we do fumigation.
Yeah, because you have to do under the hood. You never use that thing. When you do this experiment, we do a lot of this experiment.
This happens in the microbes.
Yeah.
Actually, when we do fumigation, this happens to the microbes.
Yeah.
Okay.
Okay, we do this experiment under fume hood. We do this experiment. Okay, so okay, let's coming back to this thing. So, like the glucose, if you have high level of sugar in your blood, why it is bad? You also have color blindness, everything, right? Whatever is the same thing. Whatever is actually non-specifically, all the potential will get glycosylated. Okay, same thing, right? Not only particular hemoglobin. You say hemoglobin A1C is up, but because you are measuring that, non-specifically, lot of potential will be glycosylated, right? And if you glycosylate protein, some protein may be non-functional, and therefore you have lot of side effects, right? You damage so many things actually in the body. Okay, is clear? So let's get back to this. So basically, by putting formaldehyde, it binds to NH2 of DNA. You make hydroxymethylene derivative. Then protein also has NH2. And exactly same way, you basically take the water out. Same way, right? So basically what will happen? You have protein NH, CH, NH, DNA. So that's why you cross link. This happens only when protein DNA interacts and then NH2 groups are closed. So that means these two have to be closed, then you get cross link. You understand point? So when you put formaldehyde in the cell, many DNA, many protein can be modified. That's why you put very less amount of formaldehyde. We don't put lot of formaldehyde. We put about 1% formaldehyde, very little, because we do not want to destroy other things. So very little formaldehyde we put for 15 minutes. And during that 15 minutes time, any protein DNA or protein are in contact, and they will get cross-linked because DNA, NH2 of the DNA gets modified this pathway, and then that hydroxymethylene will react with NH2 of protein, and that's why you make this kind of cross-link. Now this is covalent cross-linking. Okay, that's how you cross-link protein with DNA. So basically you fix the interaction in the living cell. Okay, that's why you basically take the snapshot of the process in the living cell. Now you detect by lysing the cell. Rest part is outside the cell, but you already fix the interaction in the cell. This part is clear? Now you have a huge piece of chromatin, right? That's the question you asked, right? So how do you basically pull down chromatin? Because once you do this thing, make the whole cell extract, your whole cell extract will be highly too much DNA, viscous. Okay, because long piece of DNA. Now if you use this antibody against A, you basically pull out the whole chunk in a viscous environment, lot of nonsense stuff. But you do not want whole chromatin to pull down. We want to pull down the fragment of the chromatin which is bound to this. How do you get the fragment of chromatin? That means you have to basically do sonication. If you do sonication, you use waves. By using waves, you can cut it here. You can cut here. Okay? But this cut is not very specific. It follows the Gaussian distribution. Gaussian distribution means not like Lorentzian. Lorentzian is more sharp. Gaussian is more broad. Okay? So basically, if you see that thing, some will be of this size, smallest size. Some will be further small. Some will be big. Okay, so some fragment will be this much. Some fragment will be this. Some fragment will be this. So you have a distribution. If you look at the size, you have all mixture. Okay, mixture with this. So basically, you get mixture of smaller fragment, but they are not one particular size. Some will be longer than this. Some longer. So but your peak will be most of them may be around say 250 or so nucleotide. Okay, but there can still some population can be maybe 290, 300, some maybe 350. Also you can get some maybe 225, 220, maybe some 200, right? This is size. So it's a Gaussian distribution. Is clear? It's clear to you? So basically you basically get this part. After sonication you can get this part. Sonication. So you have a sonicator, you give waves, and then you can fragment small pieces. So most of the things will picking maybe around the peak will be there, most of it. And now you give antibody. Antibody you cannot see by your eye, you just put antibody against which one? What is the protein here? This is the protein RNA protein, what is the name? No, this is, what is the name here? Yeah, we are using protein A. We don't know the name, just this is protein of your interest, which is A here. We are designating as A. So we are putting anti-A. Okay? So put this antibody for 3 hours. Okay? But this is in solution. Now after put for 3 hours. Okay? Is clear? What is the question?
Sir, clear. My question was, chromatin is a very long structure.
Yeah, that's why you cut into small pieces.
You told us chromatin is a very long structure.
Yeah.
How one can find out that a particular gene lies at a particular place?
Particular gene lies.
At a
Now you are randomly, you have other fragments here also. You have this fragment also here, you have another fragment. So you have all the fragments. You have in the wholesale extract, after sonication, you have all the fragments are there. They are all floating in the solution. They are all there. But this fragment did not get cross-linked with A. This fragment did not cross-link with A. This fragment did not cross-link A. Let's say, here say you have A binding site. So A can bind to multiple places, right? Say A bound here also, right? So although you have many fragments, but only these two fragments are binding to protein A. But these fragments did not bind. Now you put antibody against A. So you can only, this antibody go and bind here and here. Is clear? Now this antibody can be attached to some beads. Antibody attached to beads. Okay? The purpose of putting beads because you can separate the phase, otherwise you cannot separate. Okay, after 3 hours or 4 hours, what you do? You basically spin down slowly. You spin down whole thing in an append tube. What will go at the bottom? You will get all the beads. At the bottom, you will get all the beads, and beads will be bound to which one? A, and A is bound to chromatin. So the bead will contain which chromatin fragment? Because you are pulling, you are basically in the made the wholesale extract. In that extract, we put bead attached to anti-A. Anti-A will bind to this A, and which is basically bound to cross-linked with the DNA, this DNA fragment, chromatin fragment. And this A, same. So what will be pulled down? Which chromatin will be pulled down in this bead? Which chromatin? This chromatin and this chromatin, right? And this chromatin, they will be all in solution, right? And then you discard the supernatant, you get the just this chromatin here, right? Is clear? Okay. Then you wash the beads just by buffer, you clean it. So basically you have the beads, and beads basically contain, the bead is bound to antibody, which is basically antigen antibody interaction, got the chromatin. So chromatin is here. So you separate it, pull down all the chromatin here. Okay? Is clear to all of you? No, not clear? Is clear? Okay. Now, yes, sonication is before that. Sonication. Yeah, after sonication, you got this fragment here. Okay. Now you want to see whether this fragment. Now we know that if A binds here or not, you know or no, you don't know. If you don't know, what you do, you basically put protein A's, protein A's basically will destroy all the, now to the beads you put protein A's. To the beads you put protein A's. So basically all the, now chromatin will be basically, you pull down chromatin by this way. Now chromatin basically got the whole chromatin. Now you do not know what is basically pulled down, we don't know. Now what you do, basically you clone this thing and sequence it. That way you get, at the end of sequence you will find that protein A binds to this part of the chromatin and this part of the chromatin. That way you can find out genome-wide where the protein A binds. Is clear? Now if you know the protein A binds to this chromatin, then you don't need to do genome-wide, you can just do put the primer here and amplify PCR. If you put primer here and amplify the DNA what you are coming here, and if you see the signal, that means you can say PCR signal, that means you can say that A bound to this chromatin during biological process in the living cell. Is clear? So two things you can do. If you want to check whether protein A binding to the gene promoter, you can basically do the chromatin IP. How? You basically grow the cell, put the formaldehyde, cross-link protein A with the DNA by formaldehyde. If A binds to the promoter, then it will happen. Then sonicate the DNA, put the beads bound to antibody, put for 3 to 4 hours. After that, spin, put the whole thing in the append tube, spin down, and this bead will basically contain this DNA if protein A binds to the promoter DNA, right? And then after that, take the beads and put in the protein A's, which will destroy the protein, and you have clean DNA. Then amplify this DNA, because you know that you want to see whether this promoter is bound to protein. So therefore, you know the promoter sequence, put the primers, and then do PCR. And after that, run the gel. If you see the PCR band, that means that protein A pulled down this DNA fragment. So that way you can say that protein A binding to this promoter element or DNA element in the genome. Is clear? Now once you know, now I know how many genes are bound to protein A. We do not know, but we know only this, you know, that's why we tested can through targeted approach. Then you have to take unbiased approach. For unbiased approach, we pull down, say this binds here, or many other genes. We don't know. So basically, once you get the DNA, we basically clone those DNA fragments by putting universal adapter, and then you can clone this using universal adapter. You can clone it, and you can sequence it, right? Then you can find all the DNAs bound to protein A. Is clear to all of you? No? So basically, this is how chip works. Immunoprecipitation works, and also you can do chip-seq genome-wide to see global genome-wide analysis. Okay. Now somebody say that when you sonicate, you get such a big fragment, but protein A does not interact with such a big fragment. So can you basically narrow down the binding site? Then instead of sonication, because sonication gives you Gaussian distribution, right? So you can put MNase. MNase basically hydrolyze the DNA. Okay, so you can basically cut it. So basically instead of big fragment, you get a very small fragment, right? Okay, very small fragment DNA, right? Okay, and you pull down this fragment, very small fragment, and sequence this same way. Is clear? Is clear? So this is known as chip exo. Chip exo, you can basically use exonuclease, and first you MNase and exonuclease, then you get very close to the binding site. So whatever you get it, that is the binding site. Is it clear? So far we will discuss the technique called chromatin IP, we discuss the chip-seq, we discuss northern blot analysis, we discuss western blot analysis, we discuss primary extension, we discuss RT-PCR and RNA-seq also. Okay. So these are the various techniques people use to study gene regulation. There are many other techniques people can use. Okay.
Sometimes students ask questions like in a long piece of chromatin, long length of chromatin, how can we spot our gene of interest, where the gene is present? So one method is by digesting it with the restriction endonuclease and that particular method. Is there some other?
Yeah, those are things people use before genome sequencing. This is we are talking. Okay, there are two things. We are now post genome sequencing time, and our whole genome sequence has already first genome sequence came out in '96 or so. Then 2001 human genome sequence came. Now we know all the sequences. We know how the genes are located.
We can just put the primers and
Yeah, yeah. But the one people used to do that way before the sequence was known. Okay?
It was making chromosome maps.
Huh? Yeah.
They were making generated by Morgan and Sturtevant.
Yeah, but we are much ahead. Because we are basically much ahead of that. Like a lot of things are, even now we are doing NMR course. Okay, just look at, okay, so I'll tell you something. Tell.
So there is a long piece of chromatin, and let's assume hypothetically there is a gene of color.
Gene of color.
Gene of color on a chromatin. At which site that is present? How a person can target that this is the site?
Right now, you know the whole sequence. You know the sequence. You know whole sequence, right? You know that centromere. You know the sequence. So you can just look at the sequence. You can find what the gene is. Because right now you know the sequence. The question actually, you are asking, this is the question maybe before sequencing. Because we don't know sequence, that time you can do. But right now we know sequencing. Why you have to think anymore? The whole sequence is given to you. Yeah. The whole human genome sequence came out in 2001.
In fact, these things comes in the basic genetics.
Yeah, because that was the old genetics. Because that time we did not know anything. Now we know whole sequence. We can find how the gene is located, right? Before that, you don't know anything, right? That's why gene fishing experiment, fishing gene. Get one gene, big thing. Now you know everything is there, right? Okay, so yeah, those are the questions, important question 20 years back, 30 years back, 25 years back. Like in the same context, like NMR, today we are whatever NMR talking, NMR field was really high demand because in like 1960s, 70s, especially when to the NMR, so very hot area. So that's the time, like now we are 50 years down the line, now here cryo-EMs are now exactly same hot actually. So timing is very important actually. Now let's say same thing, oligo microarray, we are talking 18, 20 years back, very hot, now nobody looks at that actually. People are doing RNA-seq, many other more advanced techniques. Okay, so like 6.
Craig Venter,
Huh?
who sequenced the whole genome, human genome, was able to sequence whole genome in a short span.
No, it was, I think it's a long project. I think this project was started, I think late 80s, I think 89, I think the whole project started. I think they got first sequence out, I think from East first, I think 95 or 96, and then human. No, I think first one, I think East genome. I think 95 or 96, and then human thing came out in 2001. Now later many more sequences have been out. Okay, this was the project. A lot of money has gone in that, I think. Yeah.
But he did with his private.
No, this is, I think it is NIH did actually. NIH. So it's a sequencing thing. Okay, so so this is, so any other questions on this? Okay, so like NMR actually when this what all the things are telling, 1950s something new technique is coming out. Okay, and then people like chemists are using a lot. Then when you made it so simple, FT NMR became much more, right, that time. Then 2D, people are starting applying in biological molecule. Those are the time is very hot area NMR. Now people are using in 80s, the 500 megas NMR came. They are now solving DNA molecules, DNA protein complexes, protein. Then 800, 900, so those are very hot time for NMR. And but then it got stuck because you cannot go beyond certain size. Okay, and then you cannot go beyond certain size. Okay, X-ray you can go certain size, but the another bottleneck that you have to crystallize, and that's another problem, right? Now you got another technique, both problems are solved. You don't have to crystallize, and you can go to bigger size, and you can see everything quickly, cryo-EM. Okay? So how things are evolving? Okay, so now cryo-EM actually got Nobel Prize, I think, in 2017, and I think 2016 that technique became, I think, method of the year. So it's a now very hot technique actually. A lot of people are using cryo. Okay, so this we talk about a lot of tutorial for gene regulation. Now, any other techniques you want to discuss carefully? We didn't discuss in any other techniques you want to discuss? Chromatin, metabolism, any other technique?
Sir, like people are doing metabolite NMR,
Mhm.
and there are number of metabolites in the cell. Then how do they proceed for it? Like someone is taking serum sample, and are they putting the whole serum in kit, or are they diluting or something? How they do this metabolite NMR, and how do we analyze that these metabolites?
So that actually I'm putting tomorrow, because you can study. Okay, what this thing also I have done. Actually, my first publication on in vivo NMR, using NMR you can study the metabolism. That was my first publication in my life. That came in 2000. No, this came in 1994. 1994, I think 94, in Journal of Bacteriology, where we wanted to know the halophilic bacteria which lives in high salt. How do they metabolize? Because halophilic bacteria lives in very, very high salt in sea, right? And how do they metabolize? How they survive? Okay, so that's the purpose, because a lot of people try to understand metabolism of halophilic bacteria. What they do, they lyse the bacteria and try to see the enzymes are there or not. Now those enzymes actually work at very high salt. Now once you lyse, you may miss some of the enzymes. So therefore you are not getting a lot of connections. That's the problem, right? That's it is not very clear what is the metabolism. Do they really have TC cycle? Do they really have a glycolytic pathway or something else? You cannot draw any conclusion, because many enzymes you cannot detect it by RSA, because you cannot mimic the physiological condition of halophilic bacteria, because it lives in high salt, right? So therefore, that is in that time when I started my PhD, that is a big question: how the halophilic bacteria metabolize? Do they metabolize like the way we metabolize, or something else is going on? So that's the time we have to do the experiment that without lysing the halophilic bacteria. So therefore, we don't lyse the halophilic bacteria, study the metabolism in the cell of halophilic bacteria using NMR, so that you mimic the exact physiological condition. Okay, what we did actually, maybe that was the topic I want to talk today. I can tell what we did actually. We basically put the halophilic bacteria cell in that NMR tube. Okay, and what we did, we basically put level glucose, level pyruvate, C13 level. So we discussed yesterday that if pyruvate goes to TCA cycle, right? Pyruvate goes to TCA cycle, right? And then you get, so what we did, pyruvate, what is structure of pyruvate? So we use the C13 level, this C13 level. You also use this C13 level, C13 level. So just you basically isotope. This you buy the compound, they can label this compound. What you do, you grow the halophilic bacteria at high salt in a culture flask, and then you spin down, clean, and then you put in medium, growth medium containing only pyruvate, and in the same tube you pass the oxygen. You have oxygen, you attach oxygen cylinder outside, far away from the NMR machine, okay? Because this is NMR, because it's magnet, and you put, and then you have tube here, oxygen gas is coming from here, and you are basically bubbling the oxygen here. Why? Because you are giving pyruvate, and the TCA cycle, your ETC has to go on. Okay, this is the experiment we did actually. So, and then what we did actually, we did carbon 13 NMR. Listen carefully actually. So we basically wanted to see where this pyruvate is going, as a function of time. So in the tube we have in the machine we have put all the halophilic bacteria, and what is the food we are giving? We are giving only food pyruvate, only food pyruvate. We are forcing E. coli to eat pyruvate and survive, and they can do that because pyruvate gives a lot of energy, right? And then after that we put the thing, whole thing in, and we can sim the magnet, everything is perfectly fine, and then we record the spectrum as a function of time. We record the 1D spectrum as a function of time. So at t equal to 0, we see pyruvate. Pyruvate C13 will come somewhere here. Let's see for our discussion, let's say pyruvate C13 is coming here. This is coming here. CH3. And you won't see any signal. After say 3 hours, you see this is going down and something is coming up. Like this thing. I'll show you those here tomorrow. Okay? So what is this coming up? These are basically submetabolites coming. Okay? It's clear. And what we found that something is getting stopped somewhere here actually. That's why we found that something is getting stopped. And why is it stopped also tell you, because we are putting parapyruvate. Parapyruvate can become converted to parapyruvate because you make a solution and the parapyruvate is inhibited to something. We'll talk that. Then what we did, instead of pyruvate, we just did the experiment with alanine. Alanine basically, and that is C13 level alanine. That will quickly get converted to pyruvate by enzymatic reaction, and then that will get into this thing, and then you don't see the same pattern. Because alanine, you put alanine cannot form parapyruvate. When you start with pyruvate, that can form parapyruvate, that is also inhibitory to alpha ketoglutarate. So that's why you're getting this signal. Okay? And then when you start, you don't see that thing, you see whole cycle is complete. So tomorrow I'm going to show, yes.
So you was doing this experiment real time, like
Yeah, real time.
every after 3 hours you was taking 1 day spectrum.
Yeah. To know, we are doing much lesser.
This tube was within an hour.
Yeah, in a machine. And then we are bubbling the oxygen.
You was continuing.
And we are sitting there also, whole night.
That was important.
Yeah.
But you was supplying
Yeah,
oxygen
oxygen.
even through
Yeah,
even during this
yeah,
experiment.
yeah. It's a special setup. Okay. This was we didn't. That is my first work, and that is my first publication.
This is real time.
Real time.
Going and taking it.
Yeah, yeah. So I joined for PhD and doing this thing actually.
So where you did this experiment?
TIFR, Bombay. Yeah, Bombay TIFR. Yeah.
But sir, my question was now different because people are extracting serum.
Yeah.
Like people working in AIMS or from the medical. They extract serum from human blood. And there is one standard subject who is normal, like a normal person. And someone having cancer or some other disease. So there must be some level of metabolites going down or some metabolites going down. So how do they do it? Like
Okay. I'll tell you that.
they use that crude serum,
Okay.
crude urine sample.
Okay. So the question is basically, so he said nowadays basically somebody in AIMS, what they are doing, they take cancer cell, lyse it and see whether some metal is there or not. Okay. Yeah, blood serum. You take blood serum, whether something is marker is coming or not. Okay. So the two things here actually our aim was to see whether whole cycle is there or not with the lysin silicate. Okay. Now you can take, because here actually we are not looking what is outside the cell. So now when somebody gets cancer, they pass out something in the urine you can use as a marker. When somebody gets cancer, they have some marker which is in blood. Okay, it's clear. So basically, they are looking at the blood to see whether some metal is there or not, right? They are looking at urine whether some metal is there or not, right? So now, if that marker is known, you can just do NMR and see the marker is there or not. Is clear? Now second thing, somebody got cancer. We want to say how many metabolites are up and down in the cancer cell in comparison to normal cell. How will you do this thing? In this case, if you know that in cancer cell this metabolite goes up, if you know that, then we can do this way, see whether take the cancer cell, see whether metabolite is up or not. We can quickly test it. Now if you do like global search to see how, not only that, there can be multiple metabolite maybe up or down. Can I do some unbiased experiment to find out how many are up and how many are down? What I'm doing more targeted actually. So we know in cancer cell this metabolite goes up, and I take the cancer cell and see by NMR see this is up or not. At the same time, there can be many down, many other can be up. I don't know that I don't have. So this approach is more targeted approach. If you want to take more global approach, unbiased approach, what you do, you lyse the cell. Okay, but you start with you give the start with the C30 level stuff. Okay, and then you do NMR, 2D NMR, multi see what are the metals are there. But people are using basically mass spec for that. They are doing mass spec. There is a person in Toronto. They are doing a lot of mass spec analysis to look at the metabolites. Okay, it's clear. So that way, from their mass spec, you know different metabolites, and then you know that in cancer this goes up or down. Then with that knowledge, you can do NMR much better here, right? Because why? Mass spec you need very little sample. NMR you need a lot of samples. Some metabolites can be very, very low. Some metabolites can be slightly high. So metabolites you are very low, you miss it in your NMR, right? It's clear?
This was the more exciting and interesting experiment because you are doing it in real time.
Yeah.
So I have one more question. People doing protein structures in NMR, what do? They keep their proteins at -4 or something. But when it's come to NMR, they put their sample into NMR tube and they do experiments at RT, room temperature.
No, they don't store. I think what they do, they lyophilize, and they.
Some people are
No, I think because sometimes if you leave it at 4 degree, and they must be putting some thiazides, because sometimes some fungus can grow, that can basically put protease and destroy the protein. So they may be putting some thiazide. Thiazide basically make free radical that will kill the microbes. Okay.
My question is, when doing structure, they claim that their protein degrades at room temperature. But while doing its while doing their NMR, they keep it on RT. So doesn't the protein get degraded during NMR?
Okay. Okay. So the question actually, you all get the question? Okay. Let me just do you have any question in NMR? I think that I saved some time. Tomorrow I supposed to talk, and I only talk it. I'll get to that question. So do you have any question in NMR?
I have some different question.
Yeah.
Since you had worked on
Yeah, so I'll get back to this question. Keep in mind. Let me finish so that I can save some of my time from tomorrow from NMR and metabolism.
since you had worked on the respiratory cycle TCA cycle,
Yeah, yeah.
and you told us that for TCA cycle to operate, ATS must be on. Must switch on.
Which one?
For TCA cycle to operate, ETS must be on.
ETC.
Transport chain, ETC,
Yeah.
ETC must be
Okay. Yeah.
and where the oxygen meets with the cytochrome oxidase.
Okay. We discussed that yesterday. Yeah.
I have a different question. Why do people die so fast after consuming cyanide? Since it binds to the iron part of the cytochrome oxidase.
So you block that transport chain.
Yeah, for every cell to block, it should take long time. But we have heard that people die very fast after consuming cyanide. Why this happens?
Okay. Any answer from anybody?
Thyroid gets transported when
Anybody from Bhopal? Anybody from Bhopal? Okay, I was coming from Delhi to Chandigarh. The person, the one girl who was basically giving me boarding pass, she is pretty, I think she may be born maybe 90s maybe. So she is asking me, where are you going, Chandigarh? I said, then she asked, are you going for touring that area? Asking. And then just we chatting, then I asked her, where are you from? She said, I'm from Bhopal. And I asked, then she asked me, do you know where is Bhopal? She asked, I said, no, of course I know. They had huge, apart from that name, also there's huge gas tragedy in 80s actually. Yeah, She said, no, it happened in 1957. I said, she was telling. Then she's telling confidently it's 19. I said, no, it is in early 80s. And then she's talking to somebody else next to her to confirm that she thinks I am wrong, she's right. Then that person also couldn't remember. That person was young, maybe also born in 90s, maybe early 90s or late 80s. Then I said, no, then he said, no, you are right. And then I asked her that still a lot of problems they have actually in that area actually. So basically, what does it do the cyanide?
To the best of my knowledge, it is a cellular phenomenon. It's a cellular phenomenon. So persons should die. Must take long time to die. Instead of so fast.
Okay. Iron. If iron, we discussed yesterday, right? When you are talking hemoglobin. If iron, what will happen to oxygen binding?
As a rule, cyanide is a respiratory inhibitor.
Yes.
It should kill a person by inhibiting the respiratory pathway. More specifically, the electron transport chain.
Okay. Anywhere else?
What?
Anywhere else? We discussed yesterday, right? When you make hemoglobin, what you have? Because hemoglobin, iron, heme has a hexadentate, right? One position oxygen binding. Do you think it binds there also in place of oxygen? Okay. Yeah. Yeah. And you quickly, therefore, can you get the oxygen to head immediately? If you just hold your neck completely, you cannot breathe. Within 5 minutes, you will go into coma. Right? Now, then if you block the iron, can you transport? So what will happen? Very fast, right? Okay. Coma and then gone actually. Okay.
Cyanide bind to iron or some other part of the No, Dr. Cyanide bind to the iron. तो आप देखिए इलेक्ट्रॉन ट्रांसपोर्ट चेन देखिए तो उसमें लास्ट स्टेप जो है the last step है cytochrome oxidase. Iron act is a cofactor of that. Oxygen reversibly bind to
No, I think she is talking that iron, it binds to iron in hemoglobin.
No. Cyanide bind to the iron or some other part of hemoglobin. Cyanide bind to the iron. Cyanide is highly electronegative. उसके ऊपर नेगेटिव चार्ज है काफी. तो वो ठीक है. वो आयरन इज इलेक्ट्रोपॉजिटिव. वो उसके साथ जाके बाइंड कर देगा. ऑक्सीजन की रिवर्सिबल बाइंडिंग जो है स्टॉप कर देता है. सर वो दूसरे तरीके से तो हीमोग्लोबिन की हो सकता है किसी और पार्ट पे बाइंड करता हो. नहीं, लेकिन उसको डिस्टोर्ट कर देता है. कोई देन इट कैन नॉट बाइंड विद ऑक्सीजन. हीमोग्लोबिन डिस्टोर्ट होता है, इट विल टेक टाइम. बट ए पर्सन हु कंज्यूम्स साइनाइड डाइज वेरी फास्ट. जो हमने सुना है.
Okay, you can, I am giving clue to you. Okay. So you have how fast a person can die with carbon monoxide poisoning. I'll tell you one thing.
Not 5 to 6 hours.
Okay, I'll tell you this happened in 2008. There is a huge storm, snowstorm in the place where I live, and there's no power. Somebody in that, not everywhere, some house had no power. I think their tree fell down and no power. So that person, what he did actually, he put the generator in the garage, and then the door was open, something like that. So and morning he didn't get up. He died. You know what happened? Generator makes a lot of carbon monoxide. His house was full of carbon monoxide, and he died in sleep. Why he died in sleep? Okay, so he died. Okay, now you get the answer. Okay, what? It's a highly irreversible, that you cannot reverse it. Okay, हो जाता है. Okay, if you smoke, okay, smoke also makes carbon dioxide. The person who smoke, they also have some carbon monoxide also replacing this oxygen binding irreversibly, right? So now can you get answer? Because it's a problem. Can you now work out on that? If you replace by carbon monoxide, it's a problem. Now, can you get your answer now?
Cyanide is very, very fast.
Yeah.
Iron.
Yeah. So then what will happen?
Monoxide is little bit slow.
Okay.
So he dies very slowly.
Yeah.
Little bit. But cyanide is within a
Yeah.
second.
Even if you carbon monoxide poisoning, if you give oxygen gas, it won't help also. No, hemoglobin, we discussed that yesterday. Hemoglobin has 4 globin chain, and each globin chain has heme.
Very fast.
There are 4 hemes, at the center of each heme you have iron. And that iron binds to porphyrin 4, fifth one histidine of globin, and sixth one is oxygen. Right? That's what I discussed yesterday, right? Yeah, and that carries oxygen to different parts of the body. Okay.
वो मैं वही कह रहा हूँ ना कि अगर इतना टाइम होते होते the person who consumes cyanide it
Sir,
should die
if you
slowly.
consume very little bit, the cyanide number of molecules in that amount is very, very high according to your Avogadro number, and
Yeah.
that much is not, it is very much enough for our hemoglobin. Iron. Iron is very, very less compared to that. So it is very fastly absorbed at very fast rate. So all the hemoglobin, all the iron get bind to the cyanide. So very fast like within
Okay.
a second.
पहले के जमाने में मर्डर ऐसे होते थे ना
हाँ,
Cyanide killers
Or potassium injection.
potassium.
What potassium injection does?
Cyanide.
No, you only give potassium versus problem. Potassium. Because if you look at electrical conduction in the heart, electrical conduction in heart,
Hard to.
yeah, if you basically disturb the electrical conduction will be affected also. Huh? Huh? What?
Professor Chanakya.
Oh. Okay. Okay, we are getting a little bit off topic. Let's focus on the. Do you have anything on in vivo NMR? Any question? So you can basically put some label things and you can study. Okay, you can put if you can take some level stuff. You can study metabolism in living cell. You can study metabolism in plant also. Okay, sometimes actually you can basically lyse the cell. Suppose you want to see whether cell is cancerous or not. Suppose in cancerous cell accumulate this metabolite. Cancer cell accumulates this metabolite, right? So this metabolite come from Y. So you take the cancer cell biopsy, take the biopsy, and grow the cell in the plate. Okay, put the cell in the NMR tube, and then you give these C13 level metabolites food to those cells. Okay, and then you basically do NMR, and this gives signal say at this X signal. And initially you will find Y, and after some time you are finding X. And you, as a control, you have normal cell also. If you see this thing, that means this cell is cancerous. You can screen that also, right? Okay. So this is one way people can do in vivo NMR to diagnose disease also.
So, what is the concentration of cell we need for in
No, you don't need very small amount, but you are culturing that.
because they are getting cultured?
Yeah, you,
You will
no, you culture outside in the plate. You get enough cell. You get biopsy gives very small amount of cell, and you culture it, and then you basically get a lot of cells, and some cell you can store also for other analysis.
Now my question is, like these metabolites are produced in a very small amount during the process.
But if somebody has cancer, let me tell you this thing. Yesterday I talked about the whole pathway, say so many things going on, you get product, right? So A goes to B, goes to C, goes to D, goes to E, goes to F, and then gets product, right? Now there every stage just has enzyme. Now if somebody got cancer, this is the enzyme 1, enzyme 2, enzyme 3, enzyme 4, enzyme 5, right? Somebody got cancer, that means this enzyme, this gene for this enzyme is mutated, okay, or somehow is not expressed or underexpressed. That means this step will be affected. If this will be affected, you accumulate B, right? Is clear? So now you basically give the C13 level food to the normal cell and cancerous cell. Normal cell you won't see B, cancerous cell you will see B. Is clear?
So for initial hours, the concentration of B might be low, but after 5 to 6 hours,
Yeah. That's why may not be 5, 6 hours, maybe 2, 3 hours you can see it. Okay, I'll show some of our results. Okay, that is my result, and then after that, what I did, I look at the enzyme. You see a whole cycle. Now I want to see whether the enzyme involved in the metabolism in Halophilic bacteria is same as ours. and you will be surprised that enzyme kinetics is identical. So only thing that it is leaving high salt, but enzyme kinetics, kinetic parameters are same. Okay, so I will show some of the results tomorrow, because morning you are doing theory, no GE and 2D NMR, and some of the things. Morning 3 hours you spend, you have fresh brain in the morning, and then after lunch we will do all the applications. Okay, and I will also try to do other application tomorrow. At the end, if I don't get time, I will do in 1 hour on Saturday morning, because same day I will be leaving also. You all same thing. You also are leaving. Yeah. Now I'm going. Actually, I'm leaving from here on Sunday. I'm leaving from here to Jalandhar to Amritsar, and from Amritsar I'm leaving Sunday. Sunday I think 10:45, and I'm going back to USA on Wednesday. Yeah, going home for a few days, and then from there going back. So basically, I'll try to do as much as possible tomorrow, and then whatever left over I'll do on Saturday morning. Okay. So any other questions you have? Tell me. What is time now? 6:15. Maybe we can go for another 5-10 minutes if you have something else, or maybe we can go up to 6. We have 6. Maybe we can 10-15 minutes. We can, because tomorrow will be overloaded actually. So if you have discussion, you can talk.
Here's one thing, like if we lower down the temperature
Hmm.
during NMR,
Oh yeah, that's the question I didn't answer. Yeah, he asked another question also. I didn't answer that part. So his question was that, so protein degrades. So why protein does not degrade during NMR? That's your question, right?
people are putting their sample 24 to 48 hours or even 72 hours in the machine, and they are doing it at the room temperature.
Mm-hmm.
But room temperature, I think in the NMR it is around 30, 20,
Even that's
30.
25.
So protein never degrade at this temperature. Don't
They
get
are
denature.
they are sensitive. They are
If it is
Why
sensitive
protein
to the
degrades? Can you tell me?
solvent,
Okay, we'll go step by. Before I say something, why protein degrade? Why does protein degrade?
its bonding get breaks, hydrogen bonding or ionic
enzymes,
bonding or
proteins,
glycosides.
enzymes,
If we,
they are very sensitive to physiological conditions.
yeah, physiological.
Now go more molecular inside. So why protein should be degraded?
Fully degradation is at the higher temperature because their hydrogen bondings break, so it cannot be denatured. But when we are doing the NMR, if the salt concentration is very very high or something is there, then only it will degrade. Otherwise, I don't think it will degrade.
In vivo conditions, why protein degrades?
No, he is talking in vitro condition.
In vitro.
Yeah. Similarly, if you leave DNA inactive for a long time, also you destroy DNA also. Okay.
But every molecule
Oxidation.
For DNA, it might be oxidation.
What oxidation? We are putting tube for oxidation.
No, they are, so for a long time if I keep my DNA, I purge it with nitrogen, so that inert environment is gone.
Okay. After that, even after inert environment, you destroy DNA also.
DNA,
Hmm?
if there are some DNAs in,
No, there is no DNA actually. Okay. Let me just answer this thing. Okay. So we'll discuss both actually, DNA and protein. So what you do, you make that DNA and you lyophilize. You basically you make a DNA solution in a solution, and DNA is basically floating in solution. And then you make a protein. You purify the protein and floating in solution. Then what do you do after that? You lyophilize. What is the purpose of lyophilization? So that you can get the water out, right? Okay, you can get water out, and so that you get only protein, and the corresponding salts are basically will be dry material. Water will be evaporated, right? So why you have to do lyophilization? You can basically heat it. You can heat it actually. At 60 degree, you heat it or boil at 100 degree. Water can boil out. Then why you have to basically lyophilize?
by heating we will destroy or we will denaturate the structure.
But there is a speed vacuum system. You can basically decrease pressure, and you can by decreasing pressure, because you know this plot, you have, I think all of you know this plot. There is a, okay, this is the plot. This is basically the plot. You have pressure and temperature, right? Plot. And this is basically every point is a boiling temperature. Okay, this is the solid, liquid, this is vapor, right? Right? And this is the triple point, right? Okay, triple point. So if you increase the pressure, what you are increasing? You are increasing the boiling temperature, right? Now by decreasing pressure, you can basically decrease boiling temperature. So you can, there is a speed vac machine is available. So which basically create a vacuum. So say this is the this is atmospheric pressure. And atmospheric pressure, your boiling temperature is 100 degree. Now by speed vac, you decrease the pressure here. You decrease the boiling temperature to say 30, 40 degree, or say 40 degree, say, or 50 degree. Okay, say 60 degree, or 50 degree, right? 50 degree you can say. Okay, so you could use speed vac to dry the protein. Why don't you use that? By speed vac to dry protein, to dry protein.
We never dried protein. I dried GIAN with speed.
But you do you try the protein there? Okay, so then how do you dry protein then? How do you evaporate protein?
I do not dry protein.
So okay, so lyophilize. That's how you lyophilize. So how lyophilizer works? Look at this diagram.
Phenomenal, triple point.
Triple point. How lyophilization works here?
Because there is pressure, so at triple point, all three states of solvent are coexisting. So like pressure is low, so vapor phase is getting some, so liquid is
No,
equal.
no. Yes, look at the diagram. Basically, look at the diagram. You'll get it. Look at the diagram. Basically, you have decreased the. You basically, if you are sitting here, if you decrease pressure, you will come and hit here. Do you think this is a good way? Or before lyophilization, what do you do? Before lyophilization, what do you do? Take the sample and dip in liquid nitrogen. What is the purpose? Take the sample. Your sample is here at room temperature. Put in liquid nitrogen. This is temperature. So that means you are bringing temperature here. So you are moving from liquid to solid state by putting liquid. That's how you do. Before putting sample lyophilization, you move from liquid to solid by putting liquid nitrogen. Then lyophilization also creates vacuum. Okay, that means you are decreasing temperature. You are coming here. Okay, you are coming here. You cross this is sublimation temperature. Sublimation temperature. You come here. So go from solid to vapor directly. And this is happening at very, very low temperature. And you don't do anything to protein. Protein is very, very safe. You are doing, okay, it's clear to all of you? So basically, that's why before lyophilization, you have to make sure you move from this to this stage. And then decrease pressure, because then after that you put the thing in lyophilization machine, then you start generating vacuum. You are moving directly here and crossing this barrier, which is every point of this barrier is sublimation point. So basically, you directly go from solid to vapor. So water getting solid directly sublimes. So what is left? You get puffy stuff, puffy protein, puffy DNA, okay, and salt. So that's why once your experiment is done, don't store your sample at 4 degree for 20 days, 15 days. Just once experiment is done, just lyophilize store it. That's the best way to do this thing. Because if you leave it outside, that protein or DNA will be bad. So you do DNA exactly the same way. Because when you study structure, you do not know at 60 degree, you can break, as you mentioned, some bonds can be broken, hydrogen bonds can be broken, and also some other things also will happen, I'll tell you. So best thing, once you are done, experiment, lyophilize, make a heavy stuff, store it, nothing will happen. So state. That's much better than doing the way, that is a wrong way of practicing. You do experiment after 20 days, come back, you don't get same results. Get something else, right? Okay, so now if you don't do this way, if you just experiment is done, you leave it outside, at 4 degree for 15 days, 1 month, what will happen? So now if you do for DNA, DNA has phosphate backbone, and then This point is clear to all of you? Then you have purine or purine, right? Now, if you have pH slightly acidic, slightly acidic pH, you will have depurination, right? And this process is very, very slow. If you have done experiment like 5.5, pH is slightly acidic. If you have more acid, process is faster. And you put, the experiment is done, leave it in tube. If you leave it at room temperature, this process will be much faster because this is a depurination, chemical reaction, there is no enzyme. And if you leave at room temperature, then because for this reaction your activation energy is this. If you leave at room temperature, that means the room temperature also trying to basically promote the reaction. If you leave at 4 degree, then it's difficult to overcome. But still, over a long, that's why you store the sample at 4 degree or freeze it. So therefore, you can basically don't allow this reaction, right? Because to have this, you have to cross the barrier actually, and because you are not taking any enzymes. So if you leave the sample after the experiment at outside, that's bad actually. So slowly, you lose some of the purines actually. Then people may store at 4 degree DNA. That will still better, but make sure you use the gloves because you have a lot of DNAs. Okay, they can somehow go and they can destroy it.
How long DNA can be stored? How long?
No, you can store a long time, no problem. Yeah, that's why people do DNA fingerprinting from after many years, right? Okay.
Sir, we are treating the sample at -20.
Yes, fine. -20 should be fine. And 4 degrees should be fine. It will be fine, but some hydrolysis can still go at lower rate. That's why if you freeze some chicken or fish in the -20 or freezer in shop, they sell in 2 years, 3 years. They don't keep stuff store for 20 years and selling to you, right? Because it will be still going bad slowly.
If I have some sample in my NMR program, I have to do experiments like I have NMR timing this week, NMR timing next week, then next timing next week. So I cannot always take the sample out, lyophilize and then again.
No, it's not a problem because lyophilization will take much time.
So it's not
Okay, another thing I'll tell you. Sometimes again one limitation is here. You can do, lyophilize whatever water you put. After lyophilization, you put water, half ml water you put. Again, lyophilize, put exactly half ml, that way you maintain the concentration. Okay, that way is not a problem. Now I'll tell you sometimes what people do, when they put water, they also put salt also. Okay, I'll tell you one person got accidental, I won't tell the name. One person actually got accidental results. So basically every time they do experiment, they lyophilize and they dissolve it, they use the buffer again. So you understand this thing, but you should not dissolve in buffer, you should dissolve in water because all buffer constituents are there in that lyophilized product. Just put water. So that's why when you do experiment, you should do you should go much deeper into the experiment. What is going in the tubes? So sometimes people don't think, just keep on doing, every time you dissolve, put in buffer. So this person kept on putting buffer. And here this person is doing experiment using DNA structure. So if you keep on adding buffer, every time you have salt, so that person accumulated a lot of salt. And that basically gave a lot of wrong results. And they claim that this structure is formed, published it, other people cannot reproduce it. It's a big problem. Okay, let me finish this. That's why when you, I won't tell the name. Okay, I won't tell the name, but it happened actually. Because that's why when, okay, so basically when you do the experiment, you have to understand all molecular things. Like for instance, you all do lyophilization, you should do how it works, right? And so basically that happens. So it's a good idea to basically lyophilize and dissolve, okay? And
Lyophilization DNA remains in native state.
yeah, it's a powder actually, solid powder.
But the basic structure remains the same.
Yeah, but structure means you solidify. Once the moment you put water, the salt is there. Again, you have solution is there actually, then you can do same NMR again. So whatever NMR you did, you can do same NMR again.
Because from biological point of view, DNA is very important,
Huh?
especially DNA is very important molecule from biological point of view. And applications are in forensics. So how accurate are the DNA fingerprinting results?
Yeah, they're accurate actually.
Accurate.
Yeah, because CCMB, what is his name? Laljit Singh. So he was the one of the yeah. So he is one of the early person who did a lot of things in India. Okay, I think he died right few years back. He's alive still, Laljit Singh.
No, he died few years
Back I think. Few years back. Right? Oh, okay. So basically. Okay, but you are getting voice there? No. I didn't get you. What are you saying? It basically degrade. Okay. So hydrolysis, you form the peptide bond. Can they undergo hydrolysis?
only under strong basic conditions.
Even if you put ester, if you put water, will you hydrolyze? Yes, but hydrolysis is very slow, and that hydrolysis is promoted by esterase. Like the way you talk about yesterday, by taking tea, coffee, you feel very excited. Why? Because cyclic AMP, it has esterase bond also, right? Ester bond. This is what is it? A, right? And then you have CH2. Okay. So where is the ester bond? This ester bond, phosphodiester, there are two ester bonds, right? This ester bond can be hydrolyzed by phosphodiesterase. Phosphodiesterase will hydrolyze this thing, right? When you take caffeine basically inhibits actually. So therefore you accumulate more of cyclic AMP. And cyclic AMP is basically, as I said yesterday, that it leads to activation of protein kinase A. Okay, that also leads to phosphorylation of myosin light chain kinase, which will inactivate the activity of the kinase. So myosin light chain will not be phosphorylated, actin myosin interaction will work, so it will lead to vasodilation of smooth muscle. So muscle will be vasodilated, and then also it will increase the heartbeat. So your heartbeat, you are pumping the blood going to, and you feel so good, right? Yeah, you feel good, energetic, feel good, right? So that's why you are asking that. Okay, I'll tell you after the coffee, but I forgot to tell you. Okay, and now coming back to your, because this hydrolysis actually happens even if you put cyclic AMP in the just water, it will hydrolyze, but very low rate. By putting the enzyme, you basically promote the reaction, catalyze the reaction by lowering the activation energy, occurring fast. Similarly, if you protein, peptide bonds can still hydrolyze at low level actually, not by enzyme protease degrading, just something slowly processing. Okay, so but it's not a lot. But if you store at 4 degree, hydrolysis will be much slow because kinetics of the reaction depends on temperature. Because rate constant A is proportional to the temperature. If you increase temperature, rate constant increases. Okay, you know the RNS equation. Okay, what is RNS equation? If you increase the temperature, rate constant at every 10 degrees centigrade, rate constant is about 2 to 3 fold, right? So every 10 degree increase, you increase rate constant. That means you are increasing the rate of hydrolysis. So therefore, if you decrease the temperature, you decrease the rate of hydrolysis, therefore you can process it slow. If you leave it outside 48 hours, 3, 4, 5 days, then problem, right? So yeah, to be safe is better. Just if you do not want to use for next 1 month, lyophilized, store it. And before the experiment, put water and dissolve it. Okay, sometimes people put D2O. Okay, they put D2O. So they say, okay, I do not want to use another D2O. I can use same sample. Okay, but if you store it at low temperature, it should be fine for short time. But for long time, it's a good idea to lyophilize. If you want to do after 3 months, 4 months, if you do next week, maybe 5 days, 3 days, maybe fine. Also, you can look at the spectrum. One spectrum look perfectly fine, and again after 20 days looks perfectly fine. After 1 month looks perfectly fine for that protein. When you do the experiment for that protein, you know that based on your experience, nothing happens. You can do that thing. Different proteins behave differently, right? For your protein, if it works perfectly same for over a period of 2 months, you can keep it at 4 degree for 2 months.
I can take 1 day, I can compare with the previous one.
Yeah. If it's same, then it's fine. Okay. And you also can look at toxi also. Toxi also, if it's some kind of other conformations are coming, you can see other additional peaks. So you can, if you see this is working fine, when you want to work in future on this protein, you know that this protein is quite stable at this temperature for over a period of 5 months, 4 months. Okay. But for some protein it may not be same. So you cannot make a general rule for all proteins. It goes by experience and nature of particular protein also, right? Okay. If protein is very unstable, we have to lyophilize store it.
When
Huh?
we decrease the temperature, so exchange of some protons or NMR times will get
Yeah.
decreased. So we get their peak.
Yeah. That's what we discussed today, right?
Yeah. But at lower temperature, we get splitting is not that sometimes.
Okay. Which splitting? J splitting? Yeah.
Splitting of the signal is that.
Okay. Okay. So do you understand? Okay. Okay. Let's see. So what is the question going on? Okay. That's a very good question he asked. Okay. What is discussion going on?
Actually, we are talking about the stability of DNA.
Okay. So let's talk and then what is stability? Now, what is the question regarding stability?
No, I was just saying that DNA is very stable molecule as compared to proteins, and also DNA, it can be called a very boring molecule because it has only 4 nitrogen bases which are differing.
Which are?
Which are differing AGTC, only 4 purine, 2 purines and 2 pyrimidines are there. And
Do the permutation combination, you can find out how it is boring.
reactivity and stability of DNA.
Yeah, do
Because people are doing DNA fingerprinting and other experiments on the DNA which have been extracted from the fossils of thousands of years past. So that's what we were talking about.
Okay.
Great control over the proteins.
Great control. Now the thing is that it depends actually. If you get acid rain, the 2 things you remember. The area where DNA will be preserved for a long time, there you don't get a lot of acid rain. There are areas where you have limes, you get a lot of acid rains, right? In that area, DNA will be not be equally stable because acidic pH will do a lot of depurination. So, okay, so it depends on the condition. Okay, so here if you don't have acid rain, it's fine. DNA will be fine because they said somebody committed some crime. Okay, some hair is or something is there, some blood is there, so that's dried. You can basically recover from there, right?
Some fossils have been found in the bogs where there is acidic environment, and DNA of those fossils is also perfectly fine.
Yeah. Now question is basically you had in the fossil maybe.
In a low temperature areas like Siberia regions.
Okay, let me start. So DNA is fine does not mean that 100%. So you had like a 10 kg DNA, and when you found it, you have maybe 100 grams DNA. Over the years, you have lost maybe 80% DNA because of depurination. Okay, so you cannot conclude that DNA is perfectly fine. You understand my point? Yeah. And you need very small level DNA for the analysis, right? Okay. Okay. Now coming back to your question. Okay. So he is asking that. Okay, the splitting at lower temperature. Okay, more splitting or less splitting? Small number of splitting. Why?
At lower temperature, less splitting, he's saying less splitting.
We get if there are some exchangeable protons like in DNA, at lower temperatures we can detect them, like NH. So although at lower temperature we get, there is less exchange rate on NMR.
You're getting this, you should be able to explain. Because you discussed in the morning, at lower temperature, you freeze the exchangeable protons. That means you get sharp band of the exchangeable proton. And that means that is staying more of the time to that right place, right? And then that can undergo JJ coupling with the neighboring protons. So you will get more splitting. But when lines are very broad, exchanging very fast at high temperature, they do not undergo spin-spin coupling, right? Okay. I think I gave one example, right? That one example was there, right? Yeah, I think okay, let me just show that example. I'll just show. So basically, line is broad like this, and this line, this is external proton, okay? And then when decreased temperature, this line is basically coming here, sharp, because we discussed that in the morning, right? Now this can basically undergo JJ coupling with the neighboring proton, right? Right? So then means this line again will be split, and the neighboring proton will be further split, right? That example I gave in the morning, remember? We had one example, right? We have done experiment at minus 40, something like that we have shown. So that's why if you decrease temperature, you basically decrease the exchange rate of the external proton and you have more splitting. Okay?
At low temperature, yes, you can detect the exchangeable protons like NH proton
Yeah.
or any other exchangeable proton. But splitting pattern is better when temperature is higher.
Splitting pattern is better.
Good splitting at higher temperature for some, for DNA.
Hmm.
When we do experiment for DNA, so at less temperature we do experiments for NH proton, but rest of the experiments we do at higher temperature to get good splitting. So why, how we can?
But is it your observation or this is a fact actually talking? There are two things actually asking. The fact which is established, is it established fact or you are basically presenting your experience? If it is because if you increase temperature, the relaxation will be very high for all of them. I will show some of the data tomorrow. If you increase temperature, you have increase the relaxation, fast relaxation going on. Because I said temperature is also playing a role. That means T will be slow, line will be more broad. So it will become more broad line will be there if you increase temperature. Okay. So that's what I'm saying. What we are saying is this one actually is very clear. What we will explain. I will give the example. Other thing we are saying that you get more fine structure at high temperature. Okay. But actually at high temperature relaxation increases. You should see broader line. But you are telling opposite thing. So that's why I'm asking. Is it the fact is established you read somewhere or you are telling?
I'll get back to you with.
Yeah. Read that and show me. Is established fact. Usually increasing temperature, you increase the relaxation, right? And then you should broaden the line at high temperature. Okay? And also you broaden the external proton. You also lose this kind of splitting also. So at low temperature you get additional splitting and also have sharper band also. Okay, that's how we discussed today, right? Okay, so find out those things whether somebody has published something on that or it is written some in book or you are telling from your own experience of your NMR. Because sometimes what can happen actually, if you are telling from your experience and you said the experiment, it depends how good swimming you did. Maybe when you did the experiment at high temperature and low temperature, that you did very bad swimming at low temperature, very good swimming at high temperature, so line became more sharp actually. You understand my point actually? So you understand? So basically you have to make sure how good is your swimming. Okay? If you have bad swimming at low temperature and very good swimming at high temperature, line will be very sharp also.
Swimming should not be an issue because at that time, if I would have done bad swimming at lower temperature.
No, I do not know, but I just like that.
For example, I would have done bad swimming at lower temperature.
I'm not doubting anything. I'm just telling that there are so many things are there, but I'm telling that is it the fact you found? Just you find the fact, we can discuss it. Okay? So.
Sir, one possible reason may be like some molecules exist in rotameric form or some functional group with the rotameric forms.
And he's talking about the proteins. DNA. Okay. At high temperature, you say lines become sharp actually.
At certain temperature, not at
Because tomorrow I will show you some DNA result actually. I have done experiment at different increasing temperature. Lines become broader and broader. So, okay, that's what I have. That's why you are taking opposite thing. Okay, and those are published actually.
NH peak always get broader.
Okay,
NH peak,
okay, and also I'll show other inside peak also. Those things I'll show you.
NH peak always get broader.
Yeah.
With temperatures, they also get shifted on NMR temperature.
Why they'll say
Field
shift?
or they go down.
No, because as you increase temperature, hydrogen bonding is broken. Therefore, you won't see those signals actually. And, okay. So I have those data actually. I have done this experiment on DNA. I have done a lot of experiment on DNA. So I have experiment at different pH and different temperature. I'll show those data tomorrow, and then we can discuss. Okay. And you in the meantime also see whether you have found some results with surface signal at high temperature. We can discuss those. Okay. Because I think we have to look at the particular conformation, particular structure. Maybe you are talking different structure or different. You have to discuss. So check your what you have, and I'll talk other things, and you can discuss that. Okay. Okay. Today so we have done a lot of tutorial today. So this tutorial was supposed to be